A very good morning. We are much elated to welcome the gatherings congregated in APJ Hall, the celestial atmosphere built in the remembrance of our Honorable APJ Sir. A great pleasure in welcoming you all to the National Conference entitled Current Trends in Chemical Sciences under the Ever Dynamic Chemical Research Society of India, organized by School of Chemistry, Madurai Kamaraj University. A beautiful homage of Tamilians, Tamil Thai Valthu, motives us to honor our culture and prosperity. Let's all rise up together for Tamil Thai Valthu.
நிலமடந்த கிளியொலி சீராமென திகழ் பரத செக்கனமும் அதிசிறந்த திராவிடனன் திருநாடும் திருமுதலும் தரித்தனரும் திலகமுனி அத்திலக வாசனை போல் துலகும் இன்பமுத எத்திசையும் புகழ் மனத்தில் இருந்த பெரும்
There is a rule in the government of Tamil Nadu that everybody should sing at around. If you have no correct person, please don't invite them or tell them exactly what should they do. Print out எடுத்து வந்து எழுதி வச்சு படிமா தெரியல. What are you doing? என்ன படிக்கிறீங்க? என்ன எம்எஸ்சி படிக்கிறீங்களா? என்ன பிஹெச்டி படிக்கிறீங்களா? It's not the way to do things. They are not kids here. Okay? You are not a second standard kid.
Wholeheartedly.
Who is she? Hello. We கூப்பிடுவாங்க பொண்ணு.
Wholeheartedly, we bring forward the elegant person, Dr. Shivakumar, Department of Organic Chemistry, Madurai Kamaraj University, to welcome the gatherings.
Good morning, all of you. First of all, I welcome Professor J. Kumar, our Honorable Vice Chancellor. With a lot of difficulties, as is told, with his support, encouragement, this meeting is going on. Thank you, sir, and I welcome you. And next, I invite Professor S. Chandrasekharan, Senior Professor, Honorable Professor from IISc Bangalore. Always his support for all the good things. Always with travel with us. I welcome you all, welcome you, sir. And I welcome Professor S. Natarajan, IISc Bangalore, and I welcome Professor Ramaraj, our mentor, former convener, CRSA local chapter. I welcome all the speakers and students, participants, my dear friends. Good morning, all of you. Thank you.
Thank you, sir, for a kind welcome note. Before we dive into this occasion, let us reflect on the power of mementos. Far more than just in objects, they are the bonds that unite us. We invite our notable Vice Chancellor, Dr. J. Kumar, to share the everlasting reminder of the event to Dr. Chandrasekharan, Indian Institute of Science, Bengaluru. We invite our Vice Chancellor Dr. J. Kumar to honor Dr. Natarajan, Indian Institute of Science, Bengaluru. We invite Dr. Shivakumar to share the token of happiness to Dr. J. Kumar, Department of Chemistry, IISc Trivandrum. We invite Dr. Suresh to honor Dr. Ramraj, Professor of Eminence. Through this act of sharing, may we deepen and strengthen the bonds of community. Thank you very much, everyone, for the same. May the memories continue to warm our hearts and inspire us in the days. Join us in welcoming Dr. Chandrasekharan, Indian Institute of Science, Bengaluru, to deliver the inaugural address.
Good morning, Professor Kumar, Vice Chancellor, MKU, Professor Natarajan, my colleague from IISc, Professor Ramraj, Professor Eminence, Dr. Shiv Kumar, and Dr. Suresh were the conveners of this conference. Indeed, a great pleasure for me to be here this morning to participate in this conference organized by the Department of Chemistry or School of Chemical Sciences at Madurai Kamaraj University under the auspices of the Chemical Research Society of India. CRSA, as many of you know, has been in existence for over 25 years. It in fact happens to be the Silver Jubilee year of CRSI. In fact, earlier this month, I think the first week of February, we had the first meeting in the so-called Silver Jubilee year of CRSI, the meeting that was held at BITS Pilani. Now this is the second meeting under the auspices of CRSI that we're having at MKU, and the formal celebrations of the Silver Jubilee of CRSI would actually take place sometime in July in Hyderabad, where the formal programs are being planned for the Silver Jubilee. As many of you know that Professor C.N.R. Rao is the founder, president of CRSI. It is his brainchild. We started off in the first year, for example, about 100 members, life members. Now it has grown over 3,000. So there has been a steady growth, and over the last 25 years, CRS has become a brand. Every practicing active chemist in this country, they would like to be part of that. They would like to attend meetings of CRSI wherever they are held. But also everybody also would like to be recognized by CRSI. Many young people, people who are in the mid-career, they all would aspiring to have a recognition from CRSI in the form of medals and so on. With the result, it has become part and parcel of chemist activity in this country. As you know that the CRSI conducts 2 meetings in a year, one in February and the other one in July. One of the things that happens in the general CRSI meeting, which we are kind of constrained because most of the lectures in the normal national meetings of CRSI, we have only speakers who are medalists, special lectures, or something of that kind. With the result, there is very little opportunity, very little slots available for inviting people to give lectures in that sense. With the result, many people who actually normally attend the CRSI meeting, either in February or July, they only get to listen to people who are medalists or special lectures. But this is where I believe the concept of local and regional chapters of CRSI has come out to be good, mainly because the local chapters or regional chapters have the freedom. And most of the time over the years, what the local chapters have been doing is to organize a lot of outreach activities for school students, college students, and occasionally some meetings. But this is the first time that I see that Dr. Shivkumar and Dr. Suresh has taken efforts to arrange a meeting of CRSI at the same level like what the CRSI conference has done. That is very remarkable, because only this morning I had the opportunity to go through the program of this conference, and it is very, very impressive. Practically all the active, very good chemists of this country, they're all giving lectures in this conference, which is as good as your normal CRSI conference. That is very creditable. Therefore, we have to give a lot of credit to Dr. Shivkumar and Dr. Suresh for organizing this meeting. Next, I come to MKU. The MKU as a place and the School of Chemical Sciences as an institution, I've been visiting for over 35 years now. There are many people who are seniors I've been fortunate to interact with in the earlier years, and many of them have retired now. But until recently, it was Professor Ramaraj who was probably spearheading the activity here and arranged a lot of meetings, conferences of not only CRSI, but also for the Indian Academy of Sciences. In fact, my friend Professor Natarajan would agree that both of us have been the visitors to this institute and to Madurai, and many of them are doing well. They are doing extremely well, publishing papers in international journals of repute. And so there is a good sign the department probably will go places from now on with all these new people, faculty who have joined in recent years, able to contribute to the growth of chemistry in this department. Then we come to the topic of this conference, which is current trends in chemical sciences. When you talk about current trends, really you're talking about something new, something different. That's probably what one talks about. Otherwise, the current trends is a kind of a platform where you talk about significant transformative concepts that are discussed all the time. That's probably what it's all about. Therefore, what one keeps in mind is very often one would like to do some what you call as incremental advances to science. That may be good in certain situations, but that would not be enough to talk about in terms of a trend or the new developments in chemistry. Therefore, one should keep that part in mind. And when you talk about the current trend as far as chemistry, in general, you have to know that sustainability is the mantra, key mantra in the 21st century. Everybody talks about sustainability, sustainable development, as to how chemists can contribute to sustainability. And again, many of you are probably aware, the United Nations has a charter. That's around 2015, they came up with this formula of what you call as Sustainable Development Goals. There are 17 Sustainable Development Goals that have been put forward by the United Nations, which should be or expected to be implemented by the world by 2020. Out of these 17 SDGs, as we call them, there are at least 5 or 6 of them are very closely related to chemistry. For example, you talk about affordable clean energy and sustainable product development, clean water, for example, human health and well-being. So these are all things that you all know that are very important, and also the ones where chemists can actually contribute to large extent. And in all these cases, you have to remember that chemists alone, individually, cannot probably do full justice to make meaningful contribution. This is where you talk about collaboration and cooperation with other bordering areas, either in biology or in material science. Therefore, one can make something very meaningful, and always keep that in mind as to how, in the process of practicing chemistry, whether in terms of development of energy, sustain renewable energy, clean energy, hydrogen energy, photovoltaics, or what have you, or looking at catalysis in chemistry. For example, all of us know about homogeneous, heterogeneous catalysis, biocatalysis. You talk about hybrid catalysis, metal catalysis of main group or tungsten metal, what have you. In all of them, although they've been practiced for many, many years now, still there is very little understanding about the catalyst and how they function, whether you can actually have a predictive way of looking at catalysts as to how they function and so on. Therefore, there are a lot of things that still remain unanswered in our mind, and therefore, one has to be looking at a situation where chemists not only contribute in their own so-called comfort zone of doing in their area of expertise, but also have to interact with other people, including chemical engineers and physicists and biologists and material science as well. And therefore, this platform that you have today, and I also looked at the program, and it turns out that many of the lectures that are listed there, they're all in so-called cutting-edge areas of chemistry. And therefore, this is going to be a good opportunity for many of the particularly students who are sitting there, young people. This is a very rare opportunity for you, because not only you listen to some of these people who are very active, many of them who are young, and many of them who are passionate and motivated, you get an opportunity to listen to them, ask them questions, interact with them, and therefore you learn a lot about the current trends in chemistry in general sense. I wish the conference all success. Thank you very much.
Many thanks for you, sir. We are honored to have our Vice Chancellor with us today. Join us in welcoming Dr. J. Kumar to deliver the presidential address.
Very good morning to all of you. Thanks to Professor Sureshkumar for organizing this event. I, on behalf of the university, take great pleasure in welcoming Professor Chandrasekharan, the Honorary Professor from Indian Institute of Science, Bangalore, and Professor Natarajan from IISc, Bangalore. I also would like to welcome Professor Ramaraj, a long-time friend, a distinguished professor of the university, as a Raja Ramana professor. I also would like to welcome other invited speakers from different institutions, including NCL. Remember the fundamentals, the water molecule, which is of very significant interest to all of us. And there are a lot of efforts within this state itself. I have read several papers on water splitting using various methodologies, and particularly to clean industrial polluted water has been one of the key problems in this state, I guess, because I have read a lot of papers in this particular area which should enthuse youngsters who are sitting here. There has been localized efforts, I should say, because I talked to a couple of them, whether they are really going forward in taking some efforts to clean a given area of water. They were all saying something, because they are all people with a lot of experience and they try to project themselves in order to foster growth in their discipline. You might have also read in the recent articles in the newspaper, there is one Dr. Pradeep in Indian Institute of Technology in Chennai, He has been honored with a fellow status by the Academy of Engineers in the US. He is a chemist. He has done considerable amount of work in water purification. So one can take some kind of a lead from such experts and then get forward. The other thing is, in the last couple of years where there was corona prevalent, there was a lot of efforts by chemists in order to understand the molecular structure and then subsequently find a vaccine. So that's another green area for youngsters to take some initiative. There are a lot of computer tools wherein you can design molecules, or you can understand the structure of molecules with respect to these computer-aided tools. There is a website like materialscience.org where you can download n number of inputs, or there is a huge data bank with which you can predict a structure, predict a chemical formula, and thereafter you should go behind it in order to understand the formulation. There were also a couple of dialogues I had after assuming office. One director from NIPER, National Institute of Pharmaceutical Education and Research, came to us and asked us if there are groups which can help him in certain specific formulations of pharmaceutical drugs in order to keep them intact and then subsequently use it whenever there is a demand, like the corona situation. So be prepared for all this. It is sometimes we believe that we are doing an extensive work, as Dr. Chandrasekhar said. There is always a science which is incremental, and particularly in Indian environment, we claim that we have some deficiency in equipment, and to a larger extent, there was a good effort by Indian Institute of Science, Bangalore, which tried to pool all the scientific equipment throughout the country. They sent messages or inputs to all the good institutions throughout the country, asking them to give a data about the equipment and facilities which are available, which can be shared by others. And this was done at the initiative of the scientific advisor to the Prime Minister. And subsequently, it is being put forward in the website, so you can Google and see. If at all you want a particular equipment so that you can do your analysis or whatever you want to do, you can look for those informations, because these are all pooled informations from all the best laboratories in the country. So this is one important information I should share with young minds. The other thing is, for example, there are a lot of efforts in different quarters, and as was told, sustainable energy systems or sustainable energy related area is another big challenge for young minds. But there are also good opportunities. Even just a couple of days ago, one of my students from UK wrote to me that he has been working on sodium ion battery and he has been very successful in the results, and he had sent the paper he has published also. Parallelly, there has been a group in Bangalore which has come up with the battery itself in a prototype, and therefore there is a lot of enthusiasm in this country. Whenever there are good reports available in the world, it is not just an incremental publication, one more. It is also sometimes an output which gives happiness to us. So as I said, when an English or a British researcher publishes a good review article saying that it is best of the best and all that with a very high index value, etc., but we have already the battery in the market, and many of you know India is one of the biggest, one of the countries, or rather the only country which has the largest reserve of lithium. We did not declare for various strategic reasons, and we have one of the biggest reprocessing plant in the north. The reprocessing plant of lithium. So all the batteries that we inherently use in our mobile phones and other storage systems, we just discard without realizing what it means to us. But we should be little careful. For example, in Europe, when I was there in the 85 to 90s, I could see in the photo shops where I went there to buy some photo films or rolls, they will also sell the batteries. And they had a small collection system wherein you can discard the batteries and those batteries will be sent to the process systems. We should have such methodologies. One of you should kindly think about such methodologies. It's a very simple methodology. It's not a complicated methodology. It's just like a waste basket. You just throw the unused battery, which is no more of relevance. Of course, when you go and give it to service centers like mobile phone service centers, they invariably take that battery and then put a fresh battery. So you do not know what happens to that. But we can create some awareness. This is also part of our life culture. So there are three things I just wanted to share. One is about the water. The water is a very important thing for all of us, and so you should have a serious thinking in terms of this water splitting, where there are a lot of literature reports, particularly from Tamil Nadu. I have seen many reports. So one of you should analyze all these things and then give a critical output so that somebody focuses in a very relevant way. Second, as I said, is the possibility of batteries for various storages, and there are a lot of opportunities in that. People, our own faculty, Dr. Kumar has been contributing very silently, and he has been working with the Nobel laureate good enough. So people who are youngsters here can track him, talk to him if you are interested in this. And one last thing which I didn't want to reveal or discuss in deep is the hydrogen energy. There are a lot of interesting things. For example, graphene, when it was put forward, the very purpose of graphene was told that it can take up hydrogen storage. Because when you spray hydrogen on graphene, it absorbs hydrogen and it converts into an hexane structure. So it is called as graphene. So that's how graphene, and graphone are in place. So the another opportunity was considered to be very fast growing, but somehow it did not take place. And though there are many groups which are working at a modest scale in terms of this hydrogen storage, particularly in Sikri Karaikudi, we have a strong activity in a large scale of hydrogen storage. One Dr. Vasudevan is working on this. If somebody is interested, get connected. There are also challenges for hydrogen storage in a modest way or in a point of use methodologies. There has been several attempts, and all these attempts at the end of the day are laboratory outputs, and they are not really taken to an industrial scale or to any other level. So just kindly consider all these. These are all due to fundamental advances in chemistry, not just because somebody thinks out of the box and makes some inventions which are extraordinary, all that. There are a lot of inventions and so-called evolutionary thinking which has happened in this country itself. There are very good chemists in BHU and other places I have interacted. So the only point is we don't really see an output as a major issue. As Dr. Chandrasekhar highlighted, we try to find out some incremental methodologies so that we can publish a paper in a better index journal, or we can even go to the extent of patenting. That's fine. That's very important. But Government of Tamil Nadu and Government of India is taking a lot of efforts in startups and giving a lot of hope for those who want to create new establishments. So if somebody is interested, we have within this university a framework with which we can support you if you have a new formulation, or if you have something which has to be taken forward by handshaking with some kind of establishments. We are very ready to give you a support, a modest support. But subsequently, we now know the Government of Tamil Nadu has different mechanisms in order to support your initiatives through funding. And there are also industries which I know of who can be of certainly some support, particularly if it has a value system. Most of the time we have some enthusiasm, but it may not have the value system. So you kindly look into the value system in terms of the value addition And then if you tell, we are here to handhold you and see if you need any specific assistance. See, most of the times we don't understand as young minds or as prototype makers or as startup thinkers, we don't really think in terms of the product marketing. That is one thing which we don't have the strength, or we should not worry too much on that. You should handshake with a good group of people and you should rely upon them, but you should protect yourself in terms of the formulation mechanism or the tools you have in hand in order to make that particular product. So with these few words, I really appreciate the efforts of Dr. Sureshkumar, and I thank Professor Chandrasekharan for coming all the way from Bangalore to inaugurate this program on current trends in chemical sciences. There has been some small unrest, as many of you may know or may not know, but we have been fortunate to have you amongst us today, and I thank the Almighty very comfortably for this program to be a successful one. Thank you all.
Thank you, sir. Thank you, sir, for gracing us with your presence. I request our Vice Chancellor, Dr. J. Kumar, to release the book to Dr. Chandrasekharan, Indian Institute of Science, Bengaluru. My dear attendees and distinguished speakers, welcome to the session 1 of National Conference entitled Current Trends in Chemical Sciences.
So this is a formal vote of thanks. So very pleasant good morning to everybody. ஸோ சங்கம் வைத்து தமிழ் வளர்த்த மதுரையிலே இன்று வீதியில் வளர்க்க வந்திருக்கும் அனைத்து அறிவியல் பெருமக்களுக்கும் எனது அன்பார்ந்த வணக்கத்தையும் தங்களை அன்புடன் வரவேற்பதிலும் மகிழ்ச்சி கொள்கிறேன். ஸோ இட்ஸ் அ ஃபார்மல் vote of thanks. First, I would like to record my sincere thanks to our Honorable Vice Chancellor, Professor J. Kumar. So as he stated that in between the lot of hurdles and difficulties, he permitted us to conduct this conference because it's we arranged before 6 months due to the meticulous effort of the Dr. Sureshkumar. Now it's successfully inaugurated and it's conducting. So on this occasion, I would like to record my sincere thanks to our Honorable Vice Chancellor. Thank you, sir. So next, I would like to record my thanks Professor S. Chandrasekharan, Indian Institute of Science, Bangalore. So he traveled in the all ways to inaugurate this CRSI local chapter conference. So it shows his interest towards the chemistry as well as the Indian science, and also he is so interested to motivate, and also he is inspiring a lot of our Indian young budding scientists. So I interacted with the several meetings, and also today morning his inaugural also he stated that the importance of the chemistry and what is the recent developments. So thank you, sir. Thank you for coming and inaugurating this function. Thank you, sir. So next, I would like to thank our honorable alumni and also best advisor mentor, Professor S. Nadarajan. We always have in our university several times, but however, each and every time we will feel so fresh by his way of interaction and his talk and his motivation. Thank you, sir. Thank you for presence here, sir. So again, I want to thank our mentor, Ramaraj. So he is our colleague and teacher, and he is acting as several roles. Each and every day we are interacting with him. So we are doing lot of discussions, lot of controversy and everything. But however, through all his discussions, he is continuously motivating us. So thank you, sir. Thank you for presence, sir. Because he is the first extended the local chapter of CRS in Madurai. He conducted several meetings. So after his, now we, Dr. Sureshkumar started. So I hope we continue and we successfully develop the same things in Madurai. So apart from next, I would like to thank all the invited speakers from the different part of the in India in all the esteemed institutions, because around 47 speakers are there. So I welcome and also thank you for your gracious presence and going to share your recent research developments among our students in Madurai and in and around colleges. Thank you, all the speakers. Finally, I would like to, not finally, but it's very important. So thank the Chemical Research of India, CRSI, for considering Madurai as a local chapter, and also they are extending their support to conducting such type of the seminars, conferences in Madurai. Hope it will give the good inspiration, and also it make a lot of opportunities to interact our students to the national level, professors, scientists and everything. It may be a pathway to travel the greater heights, travel to the India or else the international. So we are looking the such type of the continuous support from CRSI in India for in the future endeavors also. Thank you, all the office bearers and also office of the CRSI India. So finally, I would like to thank the student participants from our university and different parts of Tamil Nadu and in and on Madurai. Thank you for your active participation as well as your interest. Hope this conference, because we arrange around 47 speakers from the diverse areas, so it will satisfy and it will give kindle your knowledge in chemistry research. So welcome all the participants. And finally, I would like to thank one and all for presence. Thank you.
Many thanks for you, sir. My dear attendees and distinguished speakers, welcome to session 1 of National Conference entitled Current Trends in Chemical Sciences.
Table எடுத்துருங்க. Chairs. Good morning, all of you. The first scientific session going to start. The first speaker is Professor S. Natarajan from IISc Bangalore. We can talk about him, whole day. So that much level is achievement and our relationship in scientific and personal also. Straight away, I will invite Professor S. Natarajan to deliver his talk, and we are very eagerly waiting. Yeah, thank you.
Thank you very much, and Sureshkumar, and very good morning to all of you. I know that the lecture is being delayed a bit. I will try to adjust my time in such a way that there's not undue delay any further. Okay, and one of the areas which has been of interest is Professor Chandrasekharan also mentioned is catalysis. So I'm just going to try and introduce the heterogeneous catalysis using metal organic frameworks. And I will try and give a very small introduction to metal organic frameworks and what kind of modifications one can do in metal organic frameworks, and then try and talk about the bifunctionality and how do you introduce bifunctionality in those compounds, and try and give a few examples of classic known studied name reactions in organic chemistry, which you can use also with metal organic framework. And for some of you who are interested, please look at a review. It's a very comprehensive review on bifunctional heterogeneous catalysis in MOF. It's a very large review, something close to 39, 40 printed pages, and it's again an open access one which just appeared, or somebody who is interested may want to look up in this particular thing. And now, if you are looking at metal organic frameworks, and I will try and take you along the small history of it, but if you look at the actual research really took off in terms of now what we call it viral is around this time. 1999, this is a paper which appeared in Nature by Umar Yagi. If you take it, you take any zinc salt, zinc acetate, zinc chloride, zinc nitrate, zinc carbonate, zinc sulfate, any zinc salt, along with you look at 1,4-benzene dicarboxylic acid, and then you put them in dimethyl formamide, and you carry out a reaction for about few hours at 60 degrees in a laboratory oven, you get beautiful, nice single crystals, and this particular compound was determined by single crystal X-ray diffraction. And round around the same time, if you look at this paper also was published slightly later than that in Science, where if you look at the instead of 1,4-benzene dicarboxylic acid, they used 1,3,5 tricarboxylic acid. So you have a terephthalic acid here, you have a trimesic acid here, and the metal which is used here is zinc, and the metal what is used here is copper. I just wanted to tell that the idea behind it, this is a very well known structure of copper acetate dihydrate, which probably you look at even in your high school. Okay? And if you are looking at, this is your acetate moiety, and these are now replaced by carboxylate because the methyl group is terminal. Now the methyl group is extended by a dicarboxylic acid of benzene. So you have one carboxylic acid connected to two copper center, and similarly two copper center go here, two copper center go here, and it also has this water molecule, which what we call it a very labile water molecule. So you can remove the water molecule from a square planar copper, you will have a square pyramidal copper, you get into square planar copper. Whenever you have a square planar copper, you are looking at a coordinatively unsaturated metal center. And these are earlier one, and again this is a reaction you can carry out even at room temperature by having trimesic acid and any copper salt at room temperature. You can immediately form the compound very easily. Then came, if you look at with a small gap, the materials. This has come from Hong Kong University of Science and Technology. This is a metal organic framework. The name was originally given by Yagi. And then Material Institute Lavoisier in Paris. This particular compound was prepared. Again, you look at in terms of connectivity, it is again terephthalic acid or 1,4-benzene dicarboxylic acid. And then this is bivalent zinc. It's a bivalent copper. And the people, Ferrey, unfortunately is no more, And he decided, why only a bivalent compound? Why not we look at a trivalent compound? So if you look at a trivalent compound, a stable trivalent compound, those of us who have been studying, there are many examples of it. You have aluminium, gallium, chromium, indium, iron, a few of them. All those compounds are forming with this particular structure. It is extremely robust in terms of the temperature, etc. Then you have the divalent, a trivalent. Then Carl Peter Lilleward, he decided that why trivalent, why not tetravalent? And he decided to react it with zirconium. And again, the carboxylate linker of choice is 1,4-benzene dicarboxylic acid. And today, the UiO 66, University Institute Oslo, and if you look at this compound, is the most studied compound, and it was discovered in 2008. If you go and look at it, this compound probably was the earlier one, has something like a 20,000 citation, and this probably around the same, and this again same, and this one, even though it started in the last 15 years, there is even more than 30,000-40,000 citations, because this is one of the most robust structure which is stable up to 550 degree. It also can take a lot of defect, so defect based chemistry can also be studied with this particular compound. So if you look at the brief history, it's I just wanted to get into the act. So the original idea of this kind of metal organic framework was coined or studied like any other major discovery in the world come from a corporate research laboratory in the US. Majority of the discovery of either advancement in terms of chemical sciences, you would find the origin not in an academic research laboratory, but you would find majority of them come from a corporate research laboratory in the US. And again, it's no surprise that you have it in DuPont. In 1965, people started looking at thermally stable, original name given as zinc coordination polymer. Then, of course, if you look at it, Hoskins and Robbins, and he looked at by that time a lot of structures and proposed a lot of hypothetical scaffold or framework of 3D structure. Very important review was written by Hoskins and Robbins. Many of them has been realized later. And if you look at by the time people started looking at all these, there is an exponential growth from 1999. Just it's not that it's a sheer coincidence. 1999 was the year when CRSI was created. So 25 years we are celebrating of basically the word MOF, metal organic framework. And since we are talking about heterogeneous catalysis, you need to look at, I mentioned about the copper, majority of them, the metal node or the metal center with which the carboxylic acid is bound is normally a Lewis acidic center. So all the metal organic framework structure which are known will have a Lewis acidic behavior. Irrespective of it, the acidity or the level of Lewis acidic behavior would change depending on the kind of coordination geometry which you are having in the structure. Okay, so remember that. And then the Lewis basic centers normally come from the organic ligand. So if you look at a benzene dicarboxylic acid, you have 4 carbon with a hydrogen that can be functionalized, or you are looking at pyridine carboxylic acid, the pyridinic nitrogen, if it is free, you can use it, or you can also use a very good, well-known secondary ligand like 2,2-bipyridine, 4,4-bipyridine, and many other azobipyridine, etc. Okay, and remember also that in the carboxylic acid, not all the oxygen need to bind with a metal, and if you have an uncoordinated oxygen, that oxygen center also can behave as a Lewis basic center. In a way that the Lewis basic center is similar to the many of the organocatalysis, metal-free catalysis, which normally people study in organic chemistry. So you can have the metal center, which is kind of a default Lewis acidic center in MOF, and you can also have the organic ligand, a Lewis basic center. So you can look at different catalysis in the same compound. Now, so I would take you through a few examples. I'll probably skip a few for lack of time, but look at the porphyrin. Usually porphyrin has been very famous. A lot of people studied as an alternate to understand how the heme protein in the biological system work. There are a lot of studies in the 60s and 70s, definitely very, very popular kind of study using porphyrin. Now, if you look at a tetrapyridyl porphyrin, so you have a central core is a porphyrin, you have functionalized the porphyrin core with a 4-pyridinic group. And you react along with another ligand. The ligand could be 1,4-benzene dicarboxylic acid, naphthalene dicarboxylic acid, or any other. We'll give few examples of it. Then you react it with a metal. We have done with zinc, and we prepared a number of compounds. And these are the conditions. Again, if you look at majority of the conditions are very simple glass beaker kind of reaction. Okay. And so you prepare and you form compounds where you look at the porphyrynic ring here. So you can see the connectivity. You have the porphyric tetrapyridyl porphyrin, and the porphyrin group is connected with the zinc. And of course, the zinc is further connected on that side with 1,4-benzene dicarboxylic acid, forming a very nice open structure. And when we were formed, of course, it's a new structure, fair enough, but we were looking to see whether we could use all these open area for any useful catalysis. And of course, we find that the zinc, which is 4-coordinated, is not very brilliantly catalytically active. So we thought, is it possible, because there's a lot of work which happened in 2009, 10, etc., doing exchange of metal ion after the compound is prepared. So you prepare the compound first and you have the zinc element, and then you want to replace the element through another post-synthetic modification. So we picked up this with using copper. So we wanted to see whether we can exchange with copper. So you look at, and then this is the zinc compound, this is the compound with copper. You can very easily and very facilely exchange all the zinc with copper without change in the structure. So we have a structure which has got a reasonably large open area. We also have the structure where the zinc can be replaced with copper, and copper center, which is 4-coordinated. I mentioned that it would be a much more active Lewis acidic center. Okay, and we attempted many reactions. I'm just giving one example. I'll give you one more example for a further modification. An A3 coupling. A A3 coupling is a one where you are going to look at an alkyne, you have an amine and an aldehyde. So you take all of them. Normally the alkyne group here and then directly binds with the copper metal, forming copper acetylide, which is the first step before you go through this, forming an A3 coupling. Okay, so we carried out the reaction, and you see that it is reasonably good yield in the formation of an amine alkyne aldehyde coupling reaction with the copper center in this particular compound. And of course, the mechanism is something what we proposed is based on a well-established, well-known, reported literature. Okay. Now, so I will probably skip this. We'll talk about the click reaction a bit later, because copper and click reaction, Barry Sauer plus got the Nobel Prize, etc. later. So another modification, if you look at, we change the linker here. So in this particular linker, you see the middle, we have a 2 amino group. And I mentioned that if you are going to look at the amino group, I will give you some other example later. That amino group is already going to be a catalytically active Lewis basic center. But the student who was working, the postdoc actually was working at that point, decided to use this amino group as an anchoring point to anchor silver nanoparticle. There's a lot of reaction which has been carried out with palladium, platinum and various other things. So she wanted to attempt a reaction where you can use it with silver. So we put a silver nanoparticle. You see that's a very nicely distributed silver nanoparticle with a particle size which is very small. And of course, you can look at the electron diffraction images to show that it's highly crystalline nanoparticle. So we also realized that the silver is very close to the free amino group by carrying out a simple IR spectroscopy analysis. So we know that as soon as the silver is bonded or close interacting with the amino group, there is a significant shift in the IR band. So we carried out, normally if you look at, you take the carbon dioxide, and the carbon dioxide, a lot of people have done with the epoxide. We have also done an epoxide, another reaction. But in this particular take, we have used an alkyne group with a CO2 to form a carboxylation. So you can now take a CO2 and do a carboxylation to form a carboxylate product, which is probably a much more useful than a carbonate which is formed. Of course, carbonate is being used extensively in many of the batteries, etc., as part of the electrolyte. Okay. So again, if you look at reasonably good yield, in most of the cases, I just want all of you to know that we have carried out at least a 4-time repetitive experiment to make sure that the yield is maintained. Okay. And if you look at, we did a hot filtration study. A hot filtration study is something where you start a reaction, allow the reaction to go and remove the catalyst from the reaction and still allow. So if, for example, we already knew that it is a silver nanoparticle catalyzed carboxylation, and if the silver nanoparticle leaches out into the solution, then we probably the reaction may still continue in a more homogeneous way. But we find that as soon as the material, the catalyst is removed, the reaction does not give any yield, indicating that this reaction is purely heterogeneous in nature. Now, so I would look at another ligand, which is a ligand which is synthesized in the laboratory. So this is a particular ligand you can buy commercially and then functionalize the OH group here to form the 2,5-bis etc. terephthalic acid. And this is the acid which is prepared, because we are now in Madurai. I have to tell that a student who graduated in Madurai Kamaraj University School of Chemistry, Dr. Sureshkumar, he joined in my laboratory as a NPDF, and then he did this synthesis. And when he synthesized, and then it was looking attractive, then I told him, why don't you do a react with a metal and see whether we are able to get any compound. So he was successful in trying to make it with a cobalt and nickel. So we were able to prepare 2 compounds with an identical crystal structure. Okay. One, you have, for example, the carboxylic acid group here, which is binding with a metal center, forming a kind of one-dimensional arrangement. You look at it here, the alkyne group is terminal and it is not bound, is still terminal. And these one-dimensional units are connected by the 4,4 bipyridine, which was used in the reaction to form a simple 2-dimensional layer. The structure was looking reasonably interesting, but unfortunately we find that the compound is not brilliantly stable. The cobalt compound was really unstable in any solution. And anytime you put it in DMF, DMSO, DMA, any one of the solvent, immediately it starts decomposing. Whereas the nickel compound we found to be a bit more robust compared to the cobalt compound. Then we were thinking what to do. Again, Dr. Sureshkumar came up with that, said, sir, we would go and then heat the whole compound here in an argon atmosphere. And if people who had worked on nanomaterial would know that stabilization of a transition metal unsupported without any protective group around it as a nanoparticle is very difficult, because many of the transition metal nanoparticles without any capping agent is pyrophoric, it catches fire. So we heated that. I was not very confident about it, and he showed that a cobalt nanoparticle supported, because if you look at all these things, we have a lot of nitrogen, carbon, oxygen, etc. You have a lot of defect carbon structure. Okay. Then we looked at, and then we found that it forms a carbon along with a cobalt nanoparticle without any capping agent. Then we wanted to look at what kind of a carbon what we get. We can do by the time the graphene got the Nobel Prize, and people looked at whether graphitic carbon, which is very well known even before about this kind of Raman band. So one would be an amorphous carbon, another one is specific for a graphitic carbon. So we know that the compound carbon what we have is a combination of graphitic versus and amorphous, okay, supported with a cobalt nanoparticle. Now, of course, we have characterized all of them. We'll skip that part. Please believe that we have a very fine cobalt nanoparticle. And we wanted to go and look at what reaction, and then the student who just joined for PhD along with Sureshkumar started working on the catalysis part of it, and then we decided to do the selective reduction of nitro group to the amines. And we were very successful in that, and we get very good yield in all the cases in to form the nitro to amino group. Okay. Then we'll skip some of it. The advantage here is cobalt nanoparticles are magnetic, and you have a simple laboratory pellet in the mixture. You just put it, the entire catalyst just walks into the flow, so you can separate the catalyst from the reaction medium. So what do we do with the nickel? And nickel, what we did with, because nickel was very stable, we prepared a palladium nanoparticle and anchored it on top of it. So we wanted to use the metal organic framework as a support, and then you put the palladium nanoparticle, and we wanted to do the reaction on that. Okay. So if you look at palladium 2 at nickel MOF, so we characterized and found that it is palladium 0. Okay. We have the XPS evidence which tells that the palladium stabilizes in palladium 0. Again, if you look at, we did the high resolution transmission electron microscopy, and to prove that the palladium is in a very good crystalline nanoparticle state. And if you look at the particle size, we are looking at 5 nanometer, roughly 3 to 5 nanometer, which is again a very, very good. And whenever you have a palladium nanoparticle, irrespective of what is the support what you have, you should be in a position to look for a simple CC coupling, and that's the reaction we carried out, a Suzuki-Miura CC coupling reaction with very good yield. And to me, and using that, we found that the CC coupling is very facile if you are trying to do even with the chloro-substituted compound. See, normally the iodo-substituted compound is much more facile compared to the chloro-substituted in many of the reactions, whereas with this particular compound, we also were very surprised to see that even the chloro-substituted one gives 91-94% yield and high reproducibility and recyclability. Okay, so I'll probably skip a few of those things. I will take another 5 minutes to just look at what is a tandem catalysis. A tandem catalysis is an atom economy catalysis reaction where the product of the first reaction is actually the reactant for the second reaction. So a series or successive reaction you also called as a cascade reaction. Okay, so where one can look at a tandem or a cascade reaction proceeds by utilizing the chemical product. So if you want to use a cascade reaction, it is always advantageous if one step of the reaction is a bit slower compared to the second step of reaction. Okay, I will talk about it in a bit. So if you look at, we formed a compound with a cadmium sulfo-isophthalate. So you know the isophthalic acid, which is 1,3-benzene dicarboxylic acid. The fifth position now, because 1,3,5 is normally the tricarboxylic acid or the trimesic acid, whereas here 1,3 position is by the carboxylate unit. The fifth position of the benzene ring is a sulfonic acid group. So if you look at, we have sulfonic acid group, and you have a binding with the carboxylate group, and you have these oxygen which are free. So those oxygen which are not bound can act as a Lewis basic center. And here they have used azo-bis bipyridine. So you have the azo group, 2 nitrogen at the middle can also catalyze a basic reaction, and the nitrogen we found that both the nitrogen of the pyridine are not directly bonded with the metal, and one of them was found to be free. So the compound has a cadmium, normally is a very well known Lewis acid catalytic site, and you have a lot of Lewis basic center in this particular structure. So what we did, we just looked at a very simple Lewis acidic reaction, deacetylation. So if you take a benzaldehyde dimethyl acetal, which a Lewis acid catalyzed to form the acetaldehyde, which react with the dicyanometane to form, you have benzylidene melanonitrile. When we independently carried out the reaction, we found that this particular reaction takes a slightly longer 5 hours compared to this step of the reaction where you start the reaction with the benzaldehyde and would react further, it forms within 3 hours. Then we thought, okay, we have done independent reaction. If we put the whole reaction in one go, what will happen? So our idea is, if the deacetylation happened to form the benzaldehyde, then what happened is, immediately this reaction has to go on this side. So the reaction, so the concentration of one is immediately consumed on that, and continuously there is going to be a lower concentration of this particular species. So you can think of using that for the Chatelier's-Brown principle, where the reaction goes from left to right in one go. So we use that for this cascade reaction. The deacetylation is a Lewis acid, and the Navier-Stokes condensation is a Lewis base catalyzed, and because we have the sulfo-oxygen, terminal pyridine group, azo-nitrogen, we have more concentration of the Lewis base here. So we formed with reasonably good deal for one of the compounds with a slightly bit more open space. Okay, and we did a very detailed kinetics of the reaction to understand how actually the reaction proceed. We carried out a reaction for a much longer time than required, so that we would identify each one of the, if there are any other side reaction which did not happen. So we understand that a very good, a facile cascade reaction can be carried out using this particular compound. And so once you do that, the student decided that he is going to look at another particular compound where you use, for example, the naphthalene dicarboxylic acid. Again, you have the diazo group in the middle. So you see the diazo group, and except that it is not directly bound with the benzene ring and 2 nitrogen aldehyde. would react with a ketone to form a quinoline derivative. So basically a ring closure reaction, which is again very well known. If you look at this reaction as in 1882 was the first of the example. And these have been used before, and we wanted to check whether such a reaction can be carried out using the MOF. And we carried out the reaction, and we found that this reaction also can be carried out. Please remember that in many of these cases, the reaction happens at the surface rather than in the pores, because many of these compounds are larger enough to get into the pore to carry out the reaction, and MOFs have a much larger surface area, so the reaction happens only in the MOF. And then two well-known reactions. I already talked about the Neuvigel reaction, and you can also look at the Michael reaction. Both the reactions are the Lewis base catalyzed reaction. So the student went and then did these two reactions in a cascade or a tandem reaction, one after other. So if you look at, you take this, okay, aldehyde, you have the dicyanomethane, and you have the acetyl-acetonate. So you react all of them to form this reaction. So it is a way where you do the Neuvigel condensation as well as the Michael addition reaction in one step. In other words, in atom economy. So the wastage is minimized. You don't have to worry about isolation of intermediates, etc. And we find that the reactions are reasonably good in terms of the yield. And of course, the mechanism is purely based on the earlier reports on each individual step. We followed it up, and again we carried out a step-by-step reaction as a function of time to understand is there any other intermediate, and then we understood what kind of reaction mechanism it is there. This will be the last one which I would talk about, where since we are talking about tandem and cascade reaction, we wanted to go back and look at, is there possible that specifically we design a ligand so that we create an additional specificity in terms of we would like to have basically an amino group in a ligand, and then allow that amino group to participate and give a larger concentration of base compared to the acid. And we wanted to, once you start doing a few reactions, you wanted to explore how much of the capability for the metal organic framework can be utilized. So we carried out for the very first time a 4-step cascade reaction. So that you have in step 1, you form with a Lewis acid catalyst. Then from there you have 3 subsequent steps. All of them are Lewis base catalytic reaction. So for that particular reason, we created with amino triazole. So you have the triazole group with an amino which are bonded with the zinc center to form a 2-dimensional layer. So those 2-dimensional layers are now connected by the sulfo group with the 2 of the benzene carboxylic acid. So you have the 2 oxygens of the sulfo group, which should be a base. And if you look at the amino group which is projecting inside a reasonably open channel, you see here these oxygen, this amino group, this whole area would be a concentration of a strong Lewis basicity. Okay. The same thing is true even here. So you have the amino group, you have the base group, etc. So we know that this compound probably one can do a more than 1-step base reaction. We have already done the Neuvigel reaction, we have already done the Michael addition using another similar compound. So we not have to use the acidic group of the zinc and see whether we can allow the whole reaction to proceed. So what we did, so you take the dimethyl acetal like the earlier case to form the benzaldehyde, and the benzaldehyde was reacting. So every one of them was carried out in presence of the nitromethane excess. So the nitro addition happens, and then the dehydration step. then the Michael addition. So you have the Henry's reaction here, the Michael addition here, and then you have a dehydration, which is again a Lewis base reaction. So for the first time, we were able to show that by using in presence of excess nitromethane, using the benzaldehyde dimethyl acetal, you can prepare 1,3-diaminopropenyl benzene. So one can carry out a reaction, and of course you can see this, how the reaction proceeds as a function of each hour. Okay, and of course, see, as I said that we have done it as a function of every hour, what is the kind of individual product, to understand the mechanism based on that. I would probably stop it here. I'll just have to go to the acknowledgement because I didn't want to take much time on this. I'll skip a few of these. So what we try to do here? So what we are trying to do is we are trying to look at the metal organic framework. So we are synthetic chemists, inorganic synthetic chemists. So once you prepare a compound, you look at and try and identify what kind of functionalities which are available in the compound. So once you know of the functionalities, then if the functionalities are limited, as in the case of zinc porphyrin, we exchange the zinc with copper and added the functionality in terms of the metal-centered catalysis. Or if you have the later examples where you have a free functionality in an amino group, or you have the azonitrogen which are available for reaction, we can do that. And in another case which I mentioned, so you form a compound, the compound itself was very unstable, what do we do with it? So then we heated the compound and formed a carbon support with a very finely distributed transition element and without any capping agent. So the transition element is available for a catalytic reaction, and then we carried out the reaction. And of course, once you have a Lewis acidic and Lewis basic, we can do a multitude of catalysis now. Okay, and of course, I didn't have time to talk about the rare earth element. We have done many reactions, and we wanted to show some auto-annihilation product. And if you are looking at acknowledgement, I have to do that. And the work originally was started, and unfortunately, I didn't have time to talk about the work of Dr. Chanaya Kundu. And of course, Gargi Datta is the one who has a background on porphyrin and came back and started the porphyrin research. And Dr. Sureshkumar, who did PhD in School of Chemistry here, and he's the one who started a lot of organic synthesis in the laboratory. Actually, he made a lot of ligand, which was followed up by this particular student, Krishna Manna, and Anupam Sarkar, and he did a lot of this kind of cascade reaction. Most of the cascade reaction was by him. Of course, in terms of the initiative, in terms of research carried out by Dr. Anupam Sarkar for cascade reaction is very large, and of course, I'm very thankful for all the funding agency. And again, I would like to express my sense of gratitude and support to my alma mater, Madurai Kamaraj University School of Chemistry, for this kind invitation, and thank you very much for your patient listening. Thank you. And if you have any questions or comments, more than happy.
Thank you, Professor. Correct time, maintaining the time also. One or two questions from the participants, quickly.
I am around.
Yeah, you will be around anytime you can disturb him.
Because I know that
only scientifically. Yeah, please.
Good morning, sir. Sir, are there any challenges or limitations associated with the cascade reaction, sir? Any challenges?
See, first of all, you need to identify the kind of reaction what you want to carry out, number one. And number two, whether to carry out such a reaction, a series of reactions, you have the sufficient functional group which is present there, and availability of the functional group for the reactant. Okay, so that's why I said you prepare a compound first, look at the structure, look at the availability of the functional group, then you design what kind of reaction you want to carry out. Okay, so synthesis is the term number one. Then identifying the different functional group is number two. Then, okay, we have reasonable structure, reasonable functional group. Then these are the reactions maybe. Then normally what we do is we do individual reactions first. So 5-6 reaction means 5-6 reaction we carry out independently. then okay, let us put all the thing together and see what happens. So these are the various steps with which we do.
Okay, sir. Thank you, sir.
Yeah, thank you. Maybe you can, during the last question, Ganesan, tea time you can ask.
Told about the CO2 absorption. So it is chemical absorption, means chemisorption or
No, I didn't talk about the absorption part of it, though we have done the experiments. But what we did was the CO2 with a reaction, what we did was addition of CO2 into an alkyne group to form the carboxylate. And another case, what we did, I didn't have time to talk about it, take a epoxide and then do the CO2 to form the carbonate, cyclic carbonates. Okay, so I didn't talk about it, but we have done those experiments. And these are metal-centered reactions. In all those cases, it's a metal center which actually participate in catalyzing the reaction. If you are looking at an acetylide, we are looking at the silver nanoparticle. The silver nanoparticle actually interact with the acetylenic group to form the silver acetylenide first. Then the CO2 comes in. Okay, and many of the cases, even the CO2, what I didn't have time to talk about it, you can absorb the CO2. CO2 is acidic. So if you have a reasonable basic functionality, normally the CO2 goes there. One can look at IR and find it. It's reasonably easy. In addition to absorption, which tells you the total carbon dioxide which is absorbed there.
Thank you, sir.
Thank you very much.
Yeah, thank you.
Dr. Shivakumar said to honor Natarajan sir with a memento.
Yeah, the next session is going to be very fantastic. Another eminent professor, Professor G. Shekhar from Indian Institute of Science. Indian Institute of Technology. I'm very sorry, Chennai. Yeah. Professor Shekhar did his PhD from IIT Kanpur under the Professor V.K. Singh. Is another eminent professor. And after that, he moved to postdoc, JSPS postdoctoral fellow. He received bronze medal, CRSI silver bronze medal also. And also a fellow from Royal Society and Academy of Science, Chennai. And another thing is that he is a secretary of our CRSI. He has published nearly 140 research articles and guided 27 PhD students. Currently, 12 students are working. With these words, I invite Professor G. Shekhar to deliver his talk. Thank you, sir.
Thank you, Professor Shivakumar, for the introduction. Also, I would like to thank him, is all right, for inviting me to give this lecture in a very nicely arranged conference, and particularly by CRSI Madurai local chapter. So I thank them once again for the invitation and wonderful hospitality. Today I will be talking about asymmetric domino synthesis of chiral heterocyclic compounds using organocatalysts. So thank you, Professor Natarajan, for setting the stage for talking about catalytic reactions. So we will be continuing in the same direction, where he was talking about metal organic framework, where I will be talking without the metal. So that is so-called organic framework, or we call it organocatalyst. And also he was touching about the tandem reactions. We also call it cascade reaction or domino reaction. So the whole presentation will be talking about domino reactions. At IIT Madras, my research group is involved in organic synthesis and catalysis, mainly focusing on developing new synthetic methodologies. Also, my research group is working in the area of catalysis. So we also develop chiral catalysis and chiral metal nanocatalysts and halogen bonding catalysts. And today's lecture, I will be talking about one of our recent project, which we started around 2 years back in the area of chiral catalysis. And chiral catalyst we use for asymmetric synthesis, that's particularly for the preparation of optical active compound, preferably enantiomerically pure compound. In general, we use three types of catalysts in asymmetric synthesis. The first one is enzyme catalyst, also we call it biocatalyst, and this is known for several decades. Then later on, metal nanocatalyst came in the picture, and during 60s and 70s and particularly 80s, this area was explored, and 2001 Nobel Prize was given to the area of metal nanocatalyst. And the recent entry in this area is chiral organocatalyst, though it's known for more than a century. The breakthrough result was published during 90s and 2000, and 2021 Nobel Prize was given to asymmetric organocatalysis. Though this particular asymmetric organocatalyst is recently explored in asymmetric synthesis, but this is known for more than a century. If you see the first report, if you see the first report, in 1912, the first chiral organocatalyst was reported in the literature, and you can see it here. They use alkaloid based quinine and quinidine catalyst for the addition of HCN in benzaldehyde, but they got less than 10% anomeric excess. In 1928, the first book about the organocatalyst was published, and see the title is very interesting. Analysis in the catalytic action of enzymes and defined organic catalyst, organic substance. So they have published by the time quite a good number of organic compound as a catalyst. Then they have realized that its activity is very close to enzyme, but they didn't use the word organocatalyst. You can see they use the word defined organic substance. So it was far from in framing the word. And 1931 onwards, people started using amino acid as a catalyst. And the second edition about the organocatalyst published in 1949, now you see the title is quite close, organic catalyst and their relations to the enzyme. So now it's very close to organocatalyst. They use the word organic catalyst. In 1960, a good result, a reasonably acceptable result was published in this area, and they use this quinine based catalyst, and they added methanol in this molecule, and they got a maximum of 74% anomeric excess. And during 2000, the breakthrough happened in this area when Benjamin List, Macmillan, and Carlos Barber started working by using proline and proline type of organocatalyst, and for that work in 2021, they got the Nobel Prize. So these are some of the important or very popular organocatalysts. The first one is proline, used by, this is a new one, so I'm not used to these buttons. The first one is very popular proline, used by Benjamin List for his Nobel Prize winning work. But it's very important to mention that much before Benjamin List, this molecule was used by our Indian very popular late Professor Swaminathan, and he used this proline for the asymmetric annulation reaction, and he got somewhere around, in his first paper, 68% anomeric excess. Later on, he used for several reactions, and he got more than 80 or 90% anomeric excess. And this is oxazolidine type of catalyst used by Macmillan, and this is alkaloid catalyst used for more than a century. And this DMAP derived catalyst developed in mid 90s, and this is a PTC, chiral PTC, known for 3 or 4 decades. You can see it here, thiourea or urea based hydrogen bonding catalyst, and these are polypeptide catalysts, and this is She catalyst. These are some of the popular organocatalysts known in the literature, and most of the catalysts are used currently. So my research group, for the last 2 decades, we are working in the area of asymmetric synthesis, but particularly we are working in metal catalysis. So we have developed chiral copper complex, cobalt, iron, and palladium catalysts for enhanced selective oxidation, reduction, coupling, oxidative coupling, and several other reactions. Around 2 years back, we thought of started working in chiral organocatalyst, and this is the first target we wanted to synthesize this kind of pyrrolothiazine. It's a quite interesting molecule. You can see it here. It's a tricyclic compound having 3 continuous chiral center, particularly 1 quaternary center, of course, which is a bit labile one. It has a thioacetal, so which is a little bit sensitive, and we can further functionalize it for different compounds. And we, if you see the biologically active several compounds, we have this particular skeleton present in several molecules, and we wanted to synthesize this pyrrolothiazine from readily available this by a domino 3+2 cycloaddition. This is the first reaction, so we want to start the reaction from this salt and olefin by a 3+2 cycloaddition. So if we treat this benzothiazonium salt with a base, it will be giving dipole, and if we treat with dipolarophile, so it will be giving 3+2 cycloaddition for the preparation of this 5-member pyrrole ring. And if we have appropriately substitution, then we can have a nice 5-member ring. Then so once the 5-member ring is formed, if we are able to cleave this carbon sulfur bond, then thiolate will be forming. Then it will be going for intramolecular aldol reaction to give this 6-member ring, so that we will be able to make this tricyclic compound. So what we did before we start the project, just we wanted to further functionalize this olefin. Yeah, we wanted to further functionalize this olefin. So what we did, we have installed aldehyde here, so it's alpha beta unsaturated aldehyde. So this is further functionalized, and if this is the case, then we can use a pyrrole kind of organocatalyst, and we can do the asymmetric version. So that is the aim. If that reaction works, then we will be able to make this pyrrolothiazine. Sorry, I am not used to this pen drive. Yeah. So once we have this pyrrolothiazine, if we have aldehyde, then we can have an aldehyde molecule which can be further functionalized, and you can see it here. This is alpha beta unsaturated thing, so we can use functionalize this beta position also. So when we started the reaction, so first this is the first reaction, we used 10 mole percentage of the organocatalyst, and in this case the reaction took place. It gave 24% yield of the target molecule with 16% enantiomeric excess, and the diacetyl selectivity was almost more than 20:1, so we got a single diastereomer. But this reaction also provided a 10 mole percentage of this N aldehyde, which formed only from one of the starting materials. To improve the efficiency of the reaction and also to reduce the quantity of the byproduct, we have carried out several optimization, and some of the representative examples are shown it here. So initially when we started the reaction, so it gave 16% E and 24% yield with 1 equivalent of triethylamine. So when we increase the quantity of the base, the reaction, so the E was increased from 16 to 24 and yield was increased from 24 to 60. So when we change increase the quantity of the base further, the yield was increased from 60 to 75 and E was more or less same. Then we use several other catalysts, but all of them are not as good as proline. Then when we use the Jorgensen-Hayashi catalyst, which is diphenyl prolinol TMS ether, that really did a wonderful job. The EE was increased to 90% and the yield, we got the yield 52%. So when we replace the base by DMAP, the E was further increased to 98% and yield was increased to 72%. Then by changing the solvent from ethanol to isopropyl alcohol, the EE was further increased to 99% and yield was increased to 87%. And it's very important to see that the byproduct in this case did not form at all. We got just trace, which is negligible. So this is our optimized condition. Under the optimized condition, we are able to get the targeted product around more than 99% enantiomeric excess and single diastereomer with 87% yield. And the absolute and relative stereochemistry of the product was confirmed by single crystal XRD. And this reaction is having very wide substrate scope. You can see it here by making the variation in this benzothiazonium salt. We are able to make almost all the compound in enantiomerically pure form, and particularly E was more than 96% for all the cases. And when we have electron withdrawing group here, the yield is further increased, particularly when you have the cyano group here, the yield is increased to 92%. And similarly, we can make the variation in the alpha beta unsaturated aldehyde. You can see it here in most of the cases. Again, the EE was really excellent. Particularly, E was slightly reduced when there is a electron withdrawing group here, slightly reduced, not too much, but from 96 to 94 and 92%, particularly when the aryl group is replaced by a heterocyclic compound, the E was slightly reduced to 98%. When this phenyl group is replaced by aliphatic methyl ethyl isopropyl, in 1 or 2 cases, slightly the E was reduced, only in this case, but yield is really reduced to, you can see, a 56, 20 or 45%. So we have developed a new domino reaction for the synthesis of pyrrolothiazine, and we wanted to understand more about the mechanism. So we have carried out several control experiments. You can see it here in the first reaction under the optimized condition. When you use the pyrrole, the reaction gave 73% yield with 12% enantiomeric excess. When we use the same catalyst by protecting the NH group, the reaction further took place, but the enantiomeric excess of the product was just racemic, which shows that this NH is very important for the asymmetric induction of this domino reaction. Then the same reaction we have carried out by using the TMS ether. So in this case, when we protected the NBOC, again you can see it here, the reaction proceeded, but it gave the racemic compound. So the same reaction, when we carried out without base, there is no reaction at all. So it shows that the base is very important to carry out the reaction. Then the same reaction when we carried out without the chiral catalyst, the reaction took place, but it gave the racemic product with 30 mol%. So based on this control experiment, what we have realized that the reaction is very important. The base is very important. Without base, the reaction will not take place. However, if the reaction is taking place only with base, then that's called a background reaction. Then there's a very high chance that you will get the product in a racemic form. So if the reaction is catalyzed by the chiral catalyst, then that reactions, the reactivity should be much more faster than the background reaction. Otherwise, always we will end up with poor enantiomeric excess of the product. So that's what happening in our case. So when we carry out the reaction with the Aruna catalyst, we are getting almost enantiomerically pure product, which shows the rate of the reaction by the catalyst is much faster than the background reaction. And also it shows that the free NH group is very important for the asymmetric version of the reaction. Otherwise, the reaction is catalyzed by the base to give the background reaction. And also the bulkiness of the catalyst is very important for the better selectivity. Otherwise, it gives poor selectivity. Based on the control experiment and the computational study with the help of our senior faculty colleague, Professor Subramaniam is here. So we propose a possible mechanism. You can see it here. So initially, what is happening? The alpha beta unsaturated aldehyde will be reacting with the catalyst, will be giving iminium salt. Then the base will be deprotonating one of the starting materials to give this diazomethane, azomethylene halide, which will be stabilized by this kind of tautomerism. Then this particular, the enolate acting as a nucleophile, it will be attacking the electrophile here to make the first carbon-carbon bond. That's the first reaction or first bond formation of the 3+2 cycloaddition. That will be followed by the second CC bond formation to give the 5-member cycle. That's a 3+2 cycloaddition. Under the reaction condition, the iminium salt will be cleaved to give the aldehyde here. Once free aldehyde is formed, you have a acidic proton in the alpha position. Again, one molecule of the base will be deprotonating. Then the enolate will be generated. And the enolate, you can see it here, this electron will be going here. This carbon sulfur bond will be cleaved to generate this kind of alkoxide, thiophenolate, and you can see thio and S minus here. Then there will be a CN bond rotation, then followed by intramolecular aldol reaction to make this 6-member ring. And once this 6-member ring is formed, this is quite stable. We can able to isolate almost in an enantiomerically pure form. So in this reaction, the most important step is the first 3+2 cyclization, the dipole cycloaddition, you can see it here. And this is the, we call asymmetric induction step here. So what happens here? So this is one of the substrate. You have the iminium salt, and this is the other one where it's acting as a nucleophile, and this is electrophile. So here what happens? The iminium salt, which is almost a planar compound, and this is the electrophilic center, and the nucleophile, that is the first reaction of 3+2 addition is taking place, and there are two options. If it is the iminium salt, it can approach from the beta phase or it can approach from the alpha phase. The first will be giving one enantiomer, whereas the second will be giving the other enantiomer. And if you see carefully, the alpha phase is completely blocked by this bulky diphenyl, the silyl enol ether. So the nucleophile can approach only from the beta phase to give this CN bond formation, and once it is bombed, then later on it will be going for second CN bond formation to complete the 3+2 cycloaddition reaction. So this is quite interesting reaction. So we got very nice tricyclic compound with almost enantiomerically pure form. Then what we thought, if you see it here, this thiohemiacetal is a quite labile group. If you treat with appropriate base, then this will be deprotonated, and once it is deprotonated, the ring can be opened, and if it opened, then we will have a thiolate here, and if you are able to trap this thiolate, then we should be able to make appropriate electrophile, then we should be able to get or synthesize tetra-substituted dihydropyrrole, pyrrole. And when we tried this reaction, obviously it worked, and it gave, you can see it here, 96% enantiomeric excess. So it looks again very interesting, almost a diazo-selective reaction here. But if a typical organic chemist sees this transformation, though the E looks very impressive, but if you look at the starting material, it's a compound, chiral compound with 3 chiral centers, whereas we are destroying 1 chiral center, it doesn't look nice. So what we thought, instead of making the product and converting to another useful product, but this particular product we have synthesized from readily available 2 achiral starting material. So can we make the whole thing in one pot? So if that is the case, we don't need to isolate. So we can directly synthesize starting from readily available starting material, and we can end up with the compound containing 2 chiral center. So when we carried out the reaction, obviously it worked. It's a one pot manner. First we have carried out our domino reaction, and nicely it gave this product. Now we removed the solvent. When we added DMF and appropriate base and electrophile, the reaction really worked well, and we are able to obtain this particular the tetra-substituted dihydropyrrole molecule in 90% yield and 96% enantiomeric excess in a single diastereomeric form. So it was really working well in our hand, and you can see some of the representative examples substrate scope. I have shown it here. In all the cases, we got the same yield and EE as like the previous method, and just one example I'm showing it here. This particular case, you can see it here. The previous reaction, it gave 56% yield and 80% EE. So here the 80 became 82 and 56 became 48. In all the cases, whatever we got in the previous case, the yield and EE is more or less same. Then what we did, we have taken the molecule and we have derivatized into several other useful molecules. The first one you have seen it here. So when we treated with base and appropriate electrophile, we are able to open this ring and we got tetra-substituted dihydropyrrole, and we further functionalize this molecule. So we can treat with appropriate oxidizing agent DDQ. It goes for a complete aromatization. Then we are able to further functionalize this bromide by doing a coupling reaction. And another interesting reaction, you can see it here. When what we thought, this is a quite unstable molecule. If we treat with appropriate oxidizing agent, it should go for aromatization directly here. So it should give a chiral pyrrole molecule. So when we treated this molecule with DDQ, thinking that it will go for aromatization, it went for aromatization, but very interesting, another reaction took place. You can see it here. So initially this deprotonation has taken place, then the ring opened, then instead of aromatization, it went for a type of Michael reaction, to give the finally aromatized product, which is looks like achiral, but when we carefully analyzed it, and you can see it here, I have shown it as a racemic compound. So this is a chiral compound, and if the aryl group is appropriately substituted, the ortho position, it's a bulky group, then it becomes a chiral, the atropisomerism is forming. But as of now, we got the racemic compound, so now it's a very interesting project. We want to carefully carry out this reaction with appropriate catalyst to make this compound, chiral compound, with atropisomerism with an asymmetric fashion. Also, this molecule we have further derivatized. In case if we are able to protect this hydroxy, then the molecule becomes quite stable, then much more stable than the regular molecule. And also we have further functionalized by reducing the carbonyl group or the double bond. So all these things are working as we are expecting. So what we thought, so initially we have carried out this reaction by using, you can see this is our initial reaction. We have used benzothiazonium salt, and it is giving the tricyclic compound with 3 chiral centers. So what we thought, if we are carrying out the same reaction without this aryl moiety, you can see only thiazonium salt. So the reaction should work, and it should give a similar type of product without this aryl ring. Without this aryl ring, it should take place. That's what we expected. But when we carried out the reaction, to our surprise, a completely different reaction took place. This expected product did not form, and this particular ketothiol was removed from one of the starting materials, and we obtained tri-substituted ferrol compound. So again, as I told you, our group was interested in a different asymmetric version, but what we got is finally we ended with a achiral molecule. So when we carefully analyzed the reaction mechanism of this particular reaction, we came to know that this reaction goes through this type of tetra substituted dihydroperol, which can be synthesized in enantiomically enriched form. And this molecule is also very important. We have seen in several biologically active compounds that this kind of skeleton is present. So what we have realized that this aromatization is happening because the reaction is taking place at room temperature. So we wanted to control the reactivity, and when we carried the reaction at lower temperature, and as we expected, the reaction worked well, and we are able to synthesize this particular molecule in with the 2 chiral centers, and this reaction at 0 degree centigrade worked well, and we got up to 98% enantiomeric excess. Again, for this particular, if we are a little bit careless, this reaction again goes for aromatization, or if we heat or allow the reaction for the room temperature or keep it for very long time, again it goes for aromatization. So we have to carefully monitor the reaction at one stage, where before the aromatization happens, you have to isolate, and once you isolate and it's quite stable, but if you keep it open for a few days, immediately it isomerizes at room temperature. Otherwise, it's quite stable. It's immediately you have to isolate, stop the reaction, isolate, and store it is quite stable. So the substrate scope for this exam, I will not be discussing here. So the substrate scope is really very broad. We can use several substrates. Some of the examples I have shown it here. So the mechanism, whatever initially I discussed the dominant reaction is more or less same here. The same, this ammonium, the iminium salt will be forming, then 3+2 cyclization will be happening, and the 5-member ring will be formed. Then iminium salt will be hydrolyzed to give the aldehyde. Then there will be a deprotonation. The enolate will be going back, and you can see it here. This is a very important step where that difference is happening. So in the initial case, you can see it here. When the ring is getting open, so we get the aromatic S minus, which I am thinking is quite stable. Since aromatic thiophenolate, so it is quite stable. Then there is a chance for CN bond formation. Then it goes close to this carbonyl compound, and the intramolecular aldehyde reaction takes place to get the 6-member ring. But when the phenyl group is not attached, instead of when the phenyl is not there, then what we are getting is vinylate. The S minus vinyl, I think is not very stable. It's not as stable as this aromatic thiolate. Since it is not stable, I think it may not be having enough time to go for the intramolecular aldol reaction, it may be immediately getting protonated to give this vinyl thiol. And when that happens, then followed by one more protonation under the reaction condition, then we are getting this kind of iminium salt, water will be attacking, then one more here, this proton will be shifting here, that under the reaction condition, the CN bond will be cleaved to eliminate the keto thiol and the expected, the optically active, the chiral product, the dihydro tri-substituted product. But if we allow it for longer time or at higher temperature, obviously that will be racemizing to give the product. So to conclude, so we have started this project around 2 years back, and when we started, so initially we have synthesized this kind of a tricyclic compound in almost anatomically pure form, starting from readily available achiral starting material by using appropriate organocatalyst, and when we allow this reaction with base and appropriate electrophile, the labile, this hemiacetal bond is getting cleaved, the ring is open, and we are able to get a tetra substituted optically active compound with very high optical purity. And when we carried out the same reaction without this the benzene ring, and it gives a very interestingly a different type of reaction. And in this case, where when we use the initially the racemic catalyst, we are able to make this tri-substituted aromatic compound at room temperature. The reaction takes place. When we are able to control the reactivity of the reaction at 0 degrees centigrade, we are able to synthesize this optically active tetra-substituted dihydroprol in almost like 98% enantiomeric excess. With this, I would like to thank my collaborator, Professor V. Subramaniam, who is here, our senior colleague, and also I thank my student, Mr. Pondichery, who has carried out all the work, whatever I have presented for the last 2 years, he is carrying out this reaction. And mostly, we are yet to publish it. We have patented it. Soon you will see a paper out of this particular work. And also, I thank DSC, SCRB, IIT Madras, and CSCR for funding some of our research project. And finally, I thank you all for listening my presentation. And also, once again, I thank the organizers for the invitation. Thank you very much.
Thank you, sir. Thank you, sir, for the wonderful talk. It was very interesting. A lot of heterocycles with the chiral molecules. Very interesting, sir.
Yeah.
Any questions, please, from students? 1 or 2 questions.
Yeah, please. Okay. Yeah, can go ahead. Yeah.
Part you mentioned about the axial chirality. I was wondering the molecule itself, is there a possibility of a CN axial chirality? Go to the molecule.
CN axial chirality. Oh, it's not working. Sorry, this is not going back. I don't know why.
Oh,
350. It's correct only.
Yeah, it's
Yeah. Yeah. This one, I hope we're talking about this molecule. No, not here. Okay, the previous one maybe. Oh, here you are talking. Yeah, it may be, because it's very difficult to realize whether it is having the atropisomerism, because the molecule is already chiral. But if you go a little bit deep inside, then we have to find out whether any additional diastereomers are forming, then we can confirm. As it is, the molecule is chiral, so we cannot say because of the atropisomerism or the chiral center. But if you want to know that whether there is atropisomerism, then we have to further functionalize and see either additional diastereomers are forming. Then we can say that it's not only the chiral center, chirality because of the chiral center, also it has a chirality because of the axial chirality. that we may have to examine. And yes, there's a possibility, but the issue is this is not sp3 hybridized one, this particular thing, but because of that it may be slightly up and down. We have to check. There's a possibility.
Bigger group on sulfur made.
Hmm.
One thing, I mean, this ring opening thing, you said mostly used alkyl iodide.
Yes.
So can change to a very hard electrophile and alkylate oxygen and keep the ring, like maroon salt.
Yeah, it might work. We may have to try, which we have not tried. Yeah, it should work. Once we have S minus, which is reasonably good nucleophile, then it should work. Yeah, there's a possibility.
Thank you. Thank you very much. You can, during the tea time, you can discuss more.
Thank you.
Thank you. Thank you very much.
Sorry, actually, this pointer is a new one, so I was little bit, I was having a difficult time.
I request Professor Shivakumar sir to honor Dr. Sekar. Before we continue with session 2, we will have a short break for tea. And I emphasize here, speaker kindly exit through right door and dear participants use the left door and kindly gather by 12 p.m. The break is left for 10 minutes.
Okay.
Kindly take your seat of brilliance. Hope you all have used this opportunity to network and engage with the fellow attendees. I emphasize, kindly take your seat of brilliance. To continue our exploration of groundbreaking research in chemical sciences, we will now welcome our session chair, Dr. Ramesh, Department of Chemistry, IISER Trivandrum. Join hands for giving a warm round of applause.
Yeah, thank you, Professor Siva and Suresh for giving me this opportunity. So we have 4 speakers for the second session. The first one will begin with Professor Thilagar he's from IISc Bangalore. And then there are 3 more speakers, which includes Professor Nithyananthan and then Suresh as well as Arunachalam. So for that, let me please welcome Professor Thilagar from IISc Bangalore. So he's originally from Pondicherry, where he had his master program from Pondicherry University. And then he moved to IIT Kanpur for his PhD. He worked with Professor V. Chandrasekhar, and subsequently he moved to USA for his postdoctoral program. And then he came back to India and joined in IISc Bangalore in the year 2009, if I'm correct. And then subsequently he has been working on, so he's working in the IPC department in IISc Bangalore. So he's a receiver of numerous awards. That includes the CRSI Bronze Medal, and he's also in multiple editorial boards. For example, he's in ACS. He's in ACS Organometallics. He's the advisory. He's one of the member of advisory board. He's also an associate editor of a couple of Wiley journals. So with that, I welcome Professor Thilagar for the for the lecture.
Is it on? Thank you, Professor Ramesh, for your kind words of introduction. At the outset, let me thank the organizers, especially Siva and co-workers, for the invitation and also for the warm hospitality. So before getting to the details of today's title, I would like to briefly mention about what are the other research activities has been going on in our laboratory at IISc Bangalore. Let me start with the acknowledgement. I would like to thank all my students, those who have done all the hard work. Because of them, I'm standing in front of you and talking about their results. So these are the guys, earlier students. They established the basic concepts in my laboratory. The recent students use this concept and apply them wherever it's applicable. Okay. So today I'm going to talk about the work mostly carried out by these 3 students. Then, of course, my collaborators and the funding agency like IISc, SERB, CSIR, ISRO, and Solar Energy Research Institute for India and USA. So basically, I'm a main group organometallic chemist having special interest in boron-based compounds. So why are we interested in boron? Let's consider trivalent boron, in which the number of valence orbital involved in bonding are higher than the number of valence electron. As a result, it left with 1 p orbital which stands perpendicular to the coordination plane. Okay, it's isoelectronic to carbocation, isostructural to carbocation, and electron deficient, and also inherently Lewis acid. Also, it's a coordinatively unsaturated. Since it's coordinatively unsaturated, if you add a suitable nucleophile, it will form a dative bond. In the sense, this molecule, if you compare these 2 units, this is electron deficient, this is electron rich, this is planar, this is tetrahedral. There is a huge structural as well as electronic perturbation happening after the nucleophile binding. So we use this concept or the concept to develop a sensor for a specific nucleophile or to activate small molecules. Okay. So instead of capturing the isolated nucleophile, we are also interested in attacking a nucleophile which is a part of an enzyme and perform some functions. Today talk mostly about this one. For example, here I am showing the active site of a proteasome enzyme, which uses this hydroxyl group as a tool to cut down the bigger protein into smaller peptides and smaller peptides into amino acids, and those amino acids are used in the cell processes. We call them as enzyme activity modulators. If you deliver the Lewis acid selectively to that site, one can inhibit that hydroxyl group and modulate the activity of such enzymes. Okay. Apart from that, we also introduce this tricoordinated boron into a pi conjugated system where the empty p orbital and boron can have a nice conjugation. This conjugation is more facile in the case of LUMO. When this interaction in LUMO, when it has a strong interaction, it's going to stabilize the LUMO. When you stabilize the LUMO, you are making the molecule to accept the electron better. In this process, one can develop electron transport material. That's what we are interested in. Apart from that, we are also interested in exploiting the BNCC isosterism. When you say isostere, that means the number of atoms and the number of electrons involved in bonding should be the same. Here, the C double bond C, each carbon comes with 4 electrons. So that means 8 electrons, 2 atoms. Here, BN unit, where the boron comes with 3 electrons and the nitrogen comes with 5 electrons, the total electron is 8. Okay? But unlike this homodiatomic unit, if you look at this BN heterodiatomic fragment, there is a huge electronegativity distance. That means the nitrogen is highly electronegative than the boron center. So the sigma bonding electron density towards the nitrogen center, but the boron center is electron deficient. It can attract the lone pair on the pi system. There is a synergism in the bonding. If you want to compare it in a layman sense, you can consider a metal carbonyl unit where the carbonyl group donates the electron and the metal donates the electron back to the empty pi star orbital and boron center. What we do is we use all these concepts as a guiding principle in developing various materials and medicinal molecules. Our effort in this area is well documented in literature. I'm not going to discuss too much about into that. Let me quickly move on to today's title, where I'm going to talk about 3 different subtopics, but all the 3 subtopics are highly interconnected. For example, first part I'm going to discuss about proteasome activity modulators. Then if you are not able to modulate the activity of proteasome or the protein, we go one step ahead in the sense we try to target the RNAs, because the RNA is translated into protein. So then when you attack or when you modulate the activity of proteasome or the RNA, what will happen to the cell, whether it's die or survives? That's what we would like to study at the end. And using all this methodology, we try to develop a probe which can selectively find out a biomarker in our blood serum. Okay, let me move on to the first title. I kept this one for the sake of master students. This is a human cell anatomy. This is a cell membrane. We have a nucleus. Inside the nucleus, we have a nucleolus, and outside various organelles are floating. Okay, what happens in the nucleus? So this DNA, the non-readable, unreadable DNA getting transcribed into RNA. This readable RNA translated into protein near the in cytoplasm, and this protein has multiple function. Let me give you only 2 functions. One is structural and another one is functional. Functional in the sense it does some chemical reaction, it catalyzes some chemical reactions. We call them as a enzyme. So here I have pictured one such enzyme, which is proteasome. It's an intracellular protein degradation machinery, which involves in various cellular processes. Okay, this process were discovered by these 3 scientists. For that, they awarded Nobel Prize sometime in 2004. Before their discovery, people thought that the lysosome is the major catalytic unit which degrade the intracellular proteins, but it's not true. This lysosome is responsible for only 10 to 20% of intracellular protein degradation. However, this proteasome plays almost 90 to 80% of intracellular protein degradation. How does it work? I'm a chemist. Always look into the molecular level how this proteasome works. Basically, this chain represents protein tagged with the ubiquitin. Then it's translocated to the protein catalytic pocket, where they have 3 catalytic sites. One is beta 5, beta 1, and beta 2. And these are the amino acids present in those active sites. If you look at carefully, in all the 3 catalytic sites, one amino acid, that is threonine 1, that's a hydroxyl amino acid, is conserved in all those things. But this 3-1 is the catalytic tool. But what about the other, what is the role of other amino acids? They somehow play a role in the selectivity where these hydrolysis should happen, either it's a hydrophobic pocket or at the hydrophilic pocket. So this beta 5 is the major catalytic site. We are trying to develop a molecule which can selectively bind to the beta 5 and control the activity of proteasome. So this is what happening. It's a basic organic chemistry. So this hydroxyl group of these 3-amino acid attack the carbonyl carbon, which is the amide group. Then with assistance from the water, it cleaves the amine group first, then the acid part comes out. These are simple proteolysis processes. Okay, people exploited this concept and developed a new drug molecule which is called borizomib. It's currently available for multiple myeloma, treatment of multiple myeloma. The multiple myeloma is nothing but when your white blood cell become cancerous. Okay, but these proteasome inhibitors, whatever is commercially available or whatever is reported so far, they are not active against solid tumors. These are liquid tumors, it's easy to treat. It's easy to reach out the cancerous cells. But solid tumors comes with the complexity in the sense they have a tumorous environment. It's very difficult, the drug molecule will be very difficult to enter inside. And also the pH around the, around the tumor will be different from the intra and the intertumor environment. So it's very difficult to target solid tumors. We were interested in developing some boronopeptides which can attack the solid tumors better than the proteasome derivatives. These are the few molecules we synthesized. We have both the derivatives, ester form as well as the hydrolysis. This is a control, it's a commercially available drug. This is a synthesis process, because let me cut down the synthesis. So we did docking studies where we found that our molecule indeed won't bind to the catalytic site of beta 5 unit. And we also did computational studies to find out where this molecule get absorbed and what kind of metabolites it's produced and where it get distributed and how it get excreted. So these studies will give you the scores, and these scores will tell you whether your molecule can be a drug molecule or not. Okay, these are the recommended scores for the various parameters listed here. For example, hydrogen bond donor, hydrogen bond acceptor, then percentage of oral absorption. If you look at these parameters, all are within the recommended range. We believe our molecule can act as a drug-like molecules. With that, we did various studies. I summarized everything in this one slide, where this y-axis, x-axis represents the compound names, and this is the IC50 value of those compounds. Okay, this is for borizomib. This is for breast cancer cell line. So where this, if you look at our molecules, almost most of them are showing much better activity in the solid tumors compared to the commercially known drug molecule. And not only the breast cancer, we also checked the other cancer cell lines. Most of the cell lines, our molecule shows better activity. But the results, what I'm showing here, is not the actual solid tumor model we have used. This was a 2D model. Whatever we generated is a 2D. The cells are in two-dimensional. To get the right result, we have to go for a 3D model. For that, we went for the 3D cell growth. We grow the cells in tumor levels and in multiple size. When you treat those tumors, solid tumors, with the borizomib, you can see the cells are getting killed. You could see the necrosis site. But if you look at our molecule stated things, almost all the cells are getting killed by our molecules. That means our molecule diffuse into these solid tumors much better than the molecules known commercial today. So with this, then after establishing this, we thought that can we have a spatio-temporal control over the activity of our molecule? What do you mean by that? What I mean by that is that can we have where to localize our compound and when to activate them? Okay, for that we introduce a pendant, azobenzene pendant onto the peptide derivative, and also here we introduced a vinyl sulfone instead of boronic acid. The boronic acid can form a reversible bond. Depending upon the pH, it can coordinate it or it can cleave. But here, this one will be a permanent bond, permanent covalent bond. It will stay longer. And also we introduce here the P2 and P3, P1, P2, P3 are the substituents. We introduce specifically the hydrophobic substituents to enhance the selectivity towards the major catalytic site, which is beta 5. Okay, so these are the amino acids we have used. I'm sorry, amino acids, the P1, P2, P3, and these are the commercially available drug molecule, azobenzene based drug molecule. What is the story about this azobenzene? When it's in trans form, it's longer. When it's in cis form, it's shorter. That means we are going to change the length of the molecule. That means when you change the length of the molecule, this molecule can fit well inside the catalytic pocket or misfit inside the catalytic pocket. Okay. To do that one, we synthesize a series of molecules again, various substitutes. It's a tedious synthesis process, but at the end we are very happy. So here, if you look at that one, the first one is the isopropyl unit. The second one, and the third one, the P2 and P3, we changed systematically. The last one, the fourth molecule, has a smallest hydrophobic one. The third one has the biggest hydrophobic amino acid derivative. This is a moderate and the smallest hydrophobic units. Okay. So if you want to have a good activity, your molecule peptide should show good photoreversibility. In the sense, at ambient light, your molecule exists mostly in the trans form. The trans form will show a strong absorption in this region. When you shine UV light, this will convert this trans form into cis. This transition will go down. Okay, that means you are generating a cis molecule, cis, and this transition comes down. The intensity of this trans goes down. So we did it repeatedly, 2-5 cycles. Our molecule shows a reversible photoisomerization. Once we established this one, we went for, of course, we established through what is the HPLC as well. Let me quickly move on. This is the summary of the activity of those molecules, the cis trans. In all the cases, our cis derivative shows a better activity than the trans derivative. That means the cis may be fitting better inside the active site of this molecule than the trans isomer. So let me summarize again. If you look at this, 1, 2, 3, 4. The fourth one is the smallest. Has the at P3 position we have a very smallest hydrophobic amino acid unit, and which shows in trans form it shows the IC50 around this one. At cis form, in trans form it doesn't show any activity, but cis form it shows the activity. That means we can make the non-toxic drug molecule to a toxic drug by just shining a light, UV light, on this one. Of course, if you switch off, if you shine the visible light, we can reverse back it to make it inactive. So then we also did docking studies. We found that the trans form is not fitting well in the active site of the enzyme, but in the cis form, it fit well and also shows a better score on binding than the trans one. Once we established this one, we thought of moving on to a different thing, because all the proteins in the genome are not druggable. The reason, because thanks to this genome project, they established that this is the 100% of your RNA genome decoding, out of which only 1.5% is coded for proteins. If you consider this as 100%, out of this only 12%, only 3% is a druggable. In the sense, your drug molecule can go and bind to those proteins and modify its activity and cure your disease. The remaining proteins are not druggable. It's very difficult to target them. Okay, but if you look at the RNA, out of this many percentage, 70% of these RNAs are druggable. That means you can easily target the RNAs better than the proteins. Okay, and also if you look at the RNA structure, unlike DNA have a nice double helix structure, but RNA has various loops and space to accommodate the molecule. So here I pictured various structures, secondary structure formed by the RNA molecules. To further get some more information about this one, it's a tRNA, where you have the loops here, and this is the actual structure, secondary, ternary structure of this tRNA. If you are allowed to react your drug molecules with the RNAs, they can go and bind here and modify their, the activities. So these are the commercially available drug molecules. Most of your antibiotics, they are not targeting the proteins, they actually targets the RNAs of your bacteria and kill the bacteria. So with all the details, we went on to design a molecule. We thought of going with a very simpler system. So bi-hyphen unit, it's not visible here, I'm sorry for that. And we introduced hydrogen bond donor and acceptor moiety, which is a barbiturate acid, which is a very close analog of your uracil. When you couple these two, you are going to generate a functional luminophore, because we want to visualize where our molecule goes instead of just treating them with a non-luminophore. So this, again, the structure is not visible here. This is the two thiophene units attached to the barbiturate acid, these units, okay? So without any substituent on the thiophene, this molecule absorbs at 460 and emits at 560 nanometer. When we introduce one simple amine unit here, the absorption shifts to 600 nanometer and it emits at near IR region. The reason because these thiophene molecules are more susceptible for electronic perturbation than the phenyl units, because they have a very less resonance energy than the phenyl units. With this, we move on and did the docking. We found out our molecules indeed bind to RNAs and interact with the base pair as well as the sugar unit in the system. Then we titrated against the RNA. When it binds to the RNA, the fluorescence intensity of our molecule enhances, but it's not binding to the DNA. That means our molecule is more selective towards RNA compared to the DNA. Then we could able to see, we also characterized by self-assembly of those molecules. This was a simple, thank you. So this for only our molecular aggregates. It forms a very small aggregates of size. This one is with the RNA. It forms a very nice bigger aggregates, and also it's a highly crystalline. This is for only the TM image of only the RNA. So that means our molecule combined with the RNA form a bigger structure, nanostructure compared to it on its own. Okay, these are the in vitro studies. We also did fluorescent microscopy studies where our molecule binds. When it's bind to the RNA, the fluorescent intensity enhances, and also you can see the size of the particle increases. This is the fluorescent microscope studies. This is for the image for the molecule with the RNA. This is for only the molecule. It shows no particles. Here you can see the aggregation. When you add an enzyme which can cleave the RNA or hydrolyze the RNA, when you hydrolyze the RNA, you don't see any this self-assembly. That means our molecule interact with the RNA, form a self-assembly that gives a better luminescence. Okay, so then we did cellular level studies. When we incubate our compound with the HeLa cell, that means our compound goes to and decorates the cytoplasm, where almost 50 to 70% of the RNAs are present. Then again it entered to the nucleus and stain only the nucleolus. That means in the nucleolus contains the RNA, not the nucleus. So that means our molecule is more selective for the RNA. How do we know that? We did the co-localization studies with the commercially available dye molecule which can selectively stain the RNA. So this is for the co-localization of our compound. With this one, will give. If you merge those two, wherever these are merging, one should see the yellow color. Red and green should give the yellow color one. Once we establish this concept, we want to quantify whether it's actually going inside the cell and give the luminescence. Here I am showing the graph. The x-axis represents the intensity of the fluorescence coming from this one, and the y-axis is the number of cells what we used to count that fluorescence intensity. Okay, this is the blue color one represents the cells with our compound. The orange color one represents cells without our compound, and the green color one represents after digesting these RNAs with RNase enzyme. Once it disassembles, the fluorescent intensity goes down. That means our molecule binds to the RNA selectively and stain the cells more brightly than the other things. So whether the binding is functional binding or non-functional. What do I mean by functional or non-functional? If it binds to the RNA, if it affects its translation process, we know that the RNA getting translated into protein. Okay, it should affect the protein synthesis. We did some in vitro studies where what did you do was this is called a luciferase enzyme assay studies. So this luciferase enzyme is a protein, will catalyze this butyl luciferin to oxyluciferin. This is non-luminescent, this is luminescent. If you produce more and more amount of this enzyme, you are going to get strong luminescence. If you add your compound, if it inhibits the translation, the protein synthesis, the luminescence intensity should go down. That's what we did. we took a template, RNA template for the synthesis of this luciferase enzyme. So in the absence of our compound, you can see the large intensity of the luminescence. Okay, this for control thing without any template or something. I mean, amino acid supply. If you don't supply amino acid or the other ingredient necessary for the translation process, we don't see much increment. When you add our compound, this is for two compounds. One is methylated derivatives and a non-methylated. Both the derivatives inhibit the translation process. That means our molecule bind to the RNA and it inhibits the translation process. That's what we could conclude here. If it inhibits, it should kill the cells. That we followed it. So here I am showing two panels. The first one is we used two sensors to find out whether our molecule is killing the cells or not. These four quadrants, the first one is for necrotic cells, this one is for live cells, this one is for early apoptotic, this is for late apoptotic. Okay. In the absence of our compound, all the cells are live. When you inhibit our compound, you can see these two quadrants are populated more in the sense the cells are getting killed. It's going to the apoptotic and early and late apoptotic panels. That means our compound binds to the RNA, kills the cells more selectively. Once we establish this one, we thought of what will happen. 5 minutes. Sure, I will finish. Thank you. So we want to find out whether we can develop a probe which can selectively picture both apoptosis and autophagy. These two are the process determine the fate of a cell, whether it has to survive or it die. Okay. So this one apoptosis process is mostly a death process. This is a survival mechanism. Okay. The recent studies have shown that there is a complex crosstalk between these two in the sense they can cooperatively work together and kill the cell, or the autophagy phagosome first it will generate, then followed by apoptosis and kill the cell, or they can work against each other. This is much more dangerous than the other two processes. The reason because if the cancer cell, if it's the autophagy process interfere in the apoptosis and make the cells survive, that means you cannot cure the cancer cell or you cannot cure the other diseases. So we thought of developing a probe which can quickly, picture both the process in the single cellular level. So if you look at both the process in the initial stage, either it's apoptosis or autophagy cells are shrinking, then later it disintegrates and to form a small molecule. When it shrinks, that means the density of the intracellular region going to be increased. When you increase the density and viscosity are related, so you're going to increase the viscosity. So if you have a probe which can selectively sense those viscosity, then one can picture both the things. So we could be able to measure the viscosity of those tissues. This is a control cell, apoptotic process and autophagy. You can see the viscosity enhanced quite drastically. So let me quickly summarize this one. So this is what we did. So this is a probe we used. Okay, you have a boron, you have a RL unit, and you have a donor, amine. The lone pair should go to the boron via this pi. But this amine group can rotate freely when you have a non-viscous medium. If it rotates, the in-plane arrangement of this will be reduced, then the charge flow will be decreased, then you see the less luminescence. Okay, when it's restricted, then one can see the better charge transfer. That's what I pictured here. So increase the viscosity, your intensity goes high. So that's what happened in the tissues. In the normal cells, it's not, the intensity is very low. When you induce apoptosis, autophagy, this is a drug molecule which can induce autophagosomes in the cells. This is a cisplatin, well-known cancer treatment drug which can induce apoptosis.
1 more minute.
So then you can see in both apoptosis and autophagy, you can see the intense luminescence coming from our molecule shows intense luminescence in those condensed states. And we also used this Drosophila as a model organism to find out whether our molecules behave similarly in that one compared to the cell lines. Again, it happens. We isolated the gut of the Drosophila and incubated those cells. This with a simple cell. Then again, we induced autophagy process and apoptotic process. If you look at the normal cells versus the autophagy and apoptosis, you can see our molecules selectively get into those things and lighten up things. Okay, with this, let me quickly what we are conclude. So currently we have here, we have a probe which can capture the autophagosomes and apoptotic vesicles in a single cellular level, and we have a molecule which can go inside the cell and selectively decorate the RNA. What we want to do is combining these two, can we find out a biomarker from the blood serum. Our blood serum contains a lot of vesicles, extracellular vesicles. When our body in normal condition, the normal cells package the RNA and send it to other places. When it's disease condition, the disease cells package the other materials and send it to the other place to spread the disease. Can we use these two type of molecule to figure out and particular biomarker for a specific disease? With this, thank you all for your attention. Once again, I thank the organizers for the
so thank you, Professor Thilagar, for the very nice presentation. We have time for quick couple of questions. Yeah.
Thank you, sir.
Is it possible to distinguish between apoptosis, necrosis, and autophagy?
Because of time, I quickly skip to those slides.
Same probe. Can we use the same probe?
That's what I want to say. Here in the apoptosis process, if you look at that one, it forms a punctured things. In the case of autophagy, it forms a vesicles. Okay. I'm sorry. One. Yeah. So if you look at these late apoptotic cells, you have the both punctate as well as these vesicles. Okay, this is the apoptotic bodies. This is the punctates of autophagosome. At later stage of apoptosis, both the processes are happening. So our molecule, in the case of apophagosomes, it's going inside those phagosomes and decorate it. In the case of the apoptotic bodies, it's decorate only the surface. It's not going inside that. So we could be able to differentiate that. Necrosis, it's very easy because everything is cleaved, it can go inside.
Can peptide-bound hydrolysis be inhibited or modulated for therapeutic?
In our body all the time, there are multiple reasons. Either you want to regenerate the old protein, cleave the old protein, get the amino acid and reuse them for making new protein, or to control some catalytic process, whatever the catalytic process done by certain protein needs to be quickly cut down. For example, cell cycle, a lot of kinases involved in that. If one kinase is not cleaved, the second stage of the cell cycle won't occur. So each stage of the proteolysis occurs. It depends on the disease. If the proteolysis process is overexpressed in certain disease, for example, cancer. Cancer needs a lot of food, right? There many cells should grow. It needs more food. For that, it will cleave more amount of the proteins and get the amino acids done. In the case of neurodegenerative diseases, there the protein aggregates happen. In the sense the proteolysis process is blocked. There you have to activate the proteasome activity. In the sense the proteolysis process should be speeded up. In the case of cancer, you have to slow it down, cut it down. In the case of neurodegenerative diseases, where you have to enhance the things. So you have to have depending upon the disease, you have to have either a modulator, inhibitor, or a activator.
We can continue the discussion during the break time. So the time is running out. So again, thank you, Professor Thilagar, for the nice presentation. Let us thank him for the wonderful. Professor, we have a small memento.
I request R. Ramesh to honor Dr. Thilagar, Indian Institute of Science, Bangalore.
So the next speaker of the session is Professor Nithyananthan from NCL Pune. He is basically an organic chemist but transformed into photochemistry, as well as he is working on solar cells. With that, I welcome Professor Nithyananthan for the lecture.
Hello. Yeah. Almost good morning to all of you. I'm very happy to be here
and I sincerely thank the organizers, Professor Sivakumar, Professor Suresh, and Professor Ramraj for organizing this nice gathering, and thanks for the nice hospitality. And it's nice to see a lot of friends, and that's very nice to see after a long time. So today I will be kind of highlighting some of the work we have been doing for the last 6 years on developing the dyes for solar cells. As Professor Ramesh said, I'm an organic chemist. I look at the structures and for the applications and design the molecules and see how the properties looks. You can think of something like a structure and how I can correlate properties. Let's see how it goes. So as we know, considering the population and the modern life, and we are running sort of energy. And one of the things, okay. Can you check? I don't know where it works. That's a light, no?
Yeah.
No, I just want to move the slide.
This back.
Okay, sorry. Okay. Thanks. So as we all know that we are using most of this topic has been in our discussion for the last 20 to 30 years, as we are using mostly the carbon-based energy resources, right? And of course, very happy to see that in the last 20 years, there is a kind of improvement in using the renewable energy source. It comes from various, various part of, like, you can think of, hydroelectric or things. One of the major things is solar energy, because that's abundant. And one of the equation that I can say that this is the graph I kept it for the students to realize that when you are walking on the sun, like sunlight, you think that there is a lot of things are happening. Basically, the lights falls on from somewhere around between 400 to all the way from 2000 nanometer. But the intensities are different, based upon certain amount of energy is absorbed by the system. Okay, but that energy is sufficient enough. If you harvest, hypothetically think about, if you harvest the whole energy for 1 hour, that is sufficient to take care of the entire world energy for 1 year. So the sun is striking that much energy, and it is doing for billions of years, and it will continue to do so for some more time, means several billions of years. And this is a kind of one of the things when you're talking about solar energy. Of course, there are a lot of technologies one can think of where, we are aware about silicon solar cells. And maybe when you are in the childhood times, you can see from the watches and calculators, of course, that is a long, established technology. And there are other technologies. You can think of thin film technology and, and tandem cells. For example, the reason is that you can enhance the device performance. Of course, if it is not useful in a common usage, things that have been used for the satellite and other things. For example, some of the things have been reached up to 47% efficiency. That means it is one of the highly efficient solar cell, but that is used for high-end applications. Okay, but there are a lot of other of course you have the second generation and third generation solar cells. Basically, you talk about emerging photovoltaics, where the chemist, physicist, they can come together, then they can make better device performance in the sense of making it flexible, and even though the performance is lower, and it can work in the very diffuse light, all these properties, okay, you can think of. So the thing we are talking about is that, let's say, for example, dye-sensitized, you reach it up to at the max, kind of 15% now. And you can think of perovskite, that's all like a 23, even 25 by modulating the device architecture. But the dye-sensitizer offers a lot of flexibility in designing the molecules and making the device very flexible. And also, this third generation photovoltaics works in the diffuser light. It doesn't need very concentrated light. Even maybe in the afternoon, Dr. Sureshkumar will sum up the very nice, interesting results. It can work in very diffuser light. Okay. So I kind of confine myself to the topic of dye-sensitized solar cell. It's a device. Of course, when you have a device, you will be having an anode and a cathode. It's a photoelectrochemical device. And in the anode side, you have the TiO2, mesoporous TiO2. That's one of the Gretzel's invention in 1991. He came up with a way to replace the single crystalline silicon, single crystalline TiO2 to a mesoporous TiO2. Like one can make a paste and screen print, and you can do very easily. You can make electrode. Okay, this you can make a very nice, and you can sensitize the dyes. Basically, sensitize means you can anchor the dye on the TiO2 surface, like by means of chemisorption. You can make a bond between them, and of course, you have the electrolyte to regenerate the the oxidation. The way it works is, upon shining the light, the dye is getting an electron is promoted from HOMO to LUMO, and depending upon the energetics, like in the electron moved from that LUMO to conduction band of TiO2, and the third, immediately the charge separation happens. Basically, the electrolyte reduce the oxidizer dye so that you'll be having an electron in TiO2 and the oxidizer species in the electrolyte. So this process is very important. This is called charge separation. Okay, in the conventional nanoparticle, you cannot have this one because the recombination will be very faster. But having the dye, you can have the charge separate state very longer lived, and you can extract the charges. So basically, that's very easily you can do, but you can do catalytically. So this is why you produce the load. Okay, and of course there are other process involved in it. Basically, the energetics wise, the LUMO has to be slightly higher than the conduction band of TiO2, as well as the redox electrolyte that you use is slightly above to the HOMO of the dye, so that you have the charge injection as well as the dye regeneration can happen very efficiently. So, and of course, one can modify the various, of course, the conduction band of TiO2 is not a fixed one. It can change with the pH, and you can change with the dipole moment of the dye. So it's a lot of external, there are a lot of other factors that are associated with that. And also one can change, the redox potential of the electrolyte by using different redox shuttle. You can use iodine iodolite or cobalt or copper. There are several rooms by which you can enhance parameters called VOC, basically open circuit voltage, basically the difference between electrolyte and as well as Fermi energy level of the connection, the TiO2, so that you can have the very better photovoltaic parameters. Okay, and this is the way. To put it in a nutshell, that we make a lot of dyes. We design and synthesize, and we make it as we'll make a TiO2 photoanode and make the dye sensitization, and basically this is a chemical reaction that you do, and of course you have the counter electrode and the electrolyte. Then you fabricate the device and measure the parameters. Basically this IV curve, and another one is IPCE. This is where you will get more information about how your device works and whether it's a good device or you need to improve a lot and everything. And IPCE will indirectly give some idea about how many, what are the photons are contributing for the current generation. That's will give some idea. Okay, so of course these are the known dyes, basically the porphyrin dye, and as well as the inorganic dyes that have been widely used in this scenario. But there are a lot of challenges when you talk about DSSC. When you say, let's say you have a TiO2, it's an inorganic material. Then when you sensitize with the dyes, because when you happen to add more amount of dyes, it's eventually lead to something called aggregation of the dyes. Okay, that we will discuss briefly in the next slide. The another one is that recombination. Charge recombination is one of the very drastic things. Of course, even though it is as such in the nanoparticle is kind of reduced, but in the there are ways one can avoid the recombination, and also the VOC. Basically, as I told, the Fermi energy level of the TiO2 is not very fixed. It can vary with several other features. So how one can take care of all these things to come up with a better dye design for the better device performance, that's of interest. For example, here, the electron transport as well as interfacial recombination rates are almost same, in the sense that if one can modify the recombination, then of course you can enhance electron transport. Eventually, that will depict in one of the parameters. Okay, so this is a simple one. I think it's for the students, I kept it this slide. This is, you have the TiO2 nanocrystalline, and you have 5-coordinated as well as 6-coordinated titanium, where in the only 5-coordinated titanium side, the dye goes and binds with with it. As Professor Natarajan said in the morning, very nice coordination chemistry we talked about. That's what we are doing here, so that the dye anchors something like this. You consider the carboxylic acid, it can anchor in several modes, but the most preferred one is for the TiO2 surface, you have the like a binary kind of structures. And when you, as I said, when you have the more dye loading, what you are trying to do is that the dyes are coming together, like, that means together in the sense that coming nearby, then it's going back to your, MSc textbook, Beer-Lambert law, the Beer-Lambert law may not work in the higher concentration. So you'll be like deviating from the like linearity. So that gives, there are other forces. It's not no longer a monomer molecule, but the features are, different. Even though it aggregates, what happens is that you broaden the spectrum. Basically, for example, the monomer like somewhere absorbs here. Because of the aggregation, you can have a blue shifted or red shifted peak. This again, you can go back to the physical chemistry textbook. There's something called dipole-dipole interaction that is manifested in even the way you calculate the proton-proton coupling constant, proton-electron hyperpine coupling constant, and even that's also depends upon the diagonal angle. Again, we can take the textbook example of Corpus equation. Why how the coupling constant is varied with the the diagonal angle. Okay, and recently this theory has been proposed by Kasha in 1965. But recently, Professor Spano from Temple University has come up with an addition of charge transfer interaction. Yes, it's what I'm talking about, the dipole-dipole interaction or Coulombic interaction between the dyes. But there is a lot of recently, Professor Spano is also trying to include the charge transfer interaction so that the aggregated structure can be defined very nicely. It can fit into any aggregated structure that you exist in the literature. Okay. So that's something we want. Like, it's a good thing. We want the aggregation because aggregation helps in broadening the spectrum. Because you can take one dye, you can allow them to communicate with each other so that you can broaden the absorption spectrum, so that I can enhance the light harvesting efficiency. On the other hand, I'm killing the device performance because of the nearby. There's something called charge hopping between the molecules. That actually is not good for the DSS's performance. The way we can think of is that how to avoid. Basically, you can separate it. Now, of course, we are just across the COVID times. People always said that don't go nearby. Stay away from each other so that we can have better effect. Something like in the molecular level. The way we can do is that we can introduce some kind of steric effect and see how whether is there any betterment comes out of from this strategy. Okay. Basically, we have chosen something like dyes, and we thought of having the alkyl groups so that the dyes are kept far away, as well as having these alkyl groups also helps some kind of passivation. Basically, the iodolite is not able to reach the TiO2 surface. That will hamper. That helps avoid the recombination that we are talking some time back. Okay, the reason we just want to use this kind of moiety where indolene moiety or indolium salt or Fischer space based dyes. When we look at the literature, we have come up with one dye. The reason specifically we planned for this is basically you are introducing the alkyl group in plane or out of plane. Basically, the three-dimensionally you are increasing the steric, not like only two-dimensionally. Okay, and so we come up with this kind of dyes. When we looked at it, it's a very nice square-in dye. It has been widely used in different optoelectronic purposes, and it can form kind of like biosensors, biomedical applications, as well as photovoltaic applications. Because these molecules also aggregate, because you want to have some chromophore that also aggregates very well, so that we can see how we can control. Okay, and this is again a donor acceptor donor compound, and see this is again we can synthesize by condensing the indolium salt with the squaric acid. If you want to have unsymmetrical square-in dye, we can have a semi-squaric acid, and we can couple with the other indolium salt so that we can have this kind of unsymmetrical square-in dyes. Okay, this background, what we have done is that, of course, I will go to the, we have synthesized this kind of set of molecules. Okay, because we want to introduce the steric effect first before, rather than the electronic effect, which I'll talk about a little later. So what we have done is that we have taken the model dye and we systematically improved the steric around the dye. For example, SQ5, SQ6, they are isomeric, but the sterics are different because carboxylic acid helps the dye to anchor on the TiO2. Okay, whereas the sterics are slightly far away, and here the sterics are nearby. but this dye is completely kind of isolated. Like even though you can have the dye, it won't communicate with each other. And how do we know that? Well, we do the spectroscopy of this molecule. This molecule absorbs around 640 nanometer. Since we don't have changed the electronic property of all the dye, basically, all the dyes absorb in the similar regions around 640. And so that's why we don't have any change in the energy levels or something. Further, we do the cyclic photometry to understand the energy levels, HOMO and LUMO, so that to fit whether the charge injection as well as the dye regeneration can be of this type can do, so that the device photovoltaic action can happen, right? And let's say this is a spectroscopy on the, for example, of the synthesized molecules. For example, SQ1 doesn't have any alkyl group. This is a black in color, and by just sensitizing it for TiO2 for a short time, you see a huge peak around 550 or 570. Okay, that's a kind of blue shifted. So that it's because of the molecular interaction or dye-dye interaction or aggregation. Okay, but when you add something like a CDCA is nothing but like a kind of molecule, but it's a transparent, optically transparent. Okay, but when you competitively you coordinate, you mix these two CDCA as well as SQ1, and if you record the photoanode spectrum, basically you can kill the aggregation. So basically the CDCA competitively coordinate with the TiO2 surface so that you can avoid the aggregation of the dyes. For example, in SQ5, if you see, of course, in the solution, of course, it's a monomer, but on the surface, you kind of reduce the kind of aggregation because of the steric around the dye. It's even kept far away on the TiO2 surface. Okay, and even the SQ7, it's very easy because it's slightly highly crowded, so the dyes are really kept away. There is no, but in the case of SQ5, it's something different because you have some space for the self, dye-dye interaction, even though you have the alkyl group. So eventually, what the outcome is that you could be able to control in a molecular level so that the dyes are kept far away on the TiO2 surface. That serves as a photoanode. Okay, and we know that on the TiO2 surface, the dyes are anchoring on the surface so that there's no, the dyes are hanging in the solution. Okay, for example, you can see the disappearance of acid group on the TiO2 surface, right? But now this is a very interesting to see that if you see, consider the device performance, right? Like when you have SQ1 and SQ5, basically you have without any alkyl group and with alkyl group, you see a drastic photocurrent generation, and almost 3 times, kind of 3 times you can have. This is because of the aggregates are there, and it's kind of controlled because that we came to know by that we'll describe by the IPC response. Because IPC, as I told, that will give some idea how the photons are converted into current by looking at the IPC. That you can see basically in the terms of SQ5, you can see that even around 550 also you can see the very good photocurrent around 70 to 75. Whereas in the case of SQ1, even you have the photocurrent generation from the aggregated state, but it's very low because of the exciton migrates in the TiO2 surface by which the device performance is killed. Because we need the electron to be injected on the TiO2 surface, not the hopping between the monolayer. Okay, and this also validated by if you add the CDCA, then you can convert this peak into kind of monomeric action. So now the purpose of avoiding the aggregation is kind of achieved here, but you compensate the energy or efficiency. Whereas in the case of SQ5, it assembles very nicely on the system, and you have both aggregation also helps, giving more photocurrent, as well as by EAS studies and everything, we studied that the charge recombination also kind of reduced in the case of SQ5. Okay. Of course, we kind of screened so that what is whether a substitution at N site or sp3 site is very important, and we felt that this SQS4 is a very optimized structure that you can have, and there all these things you can see that you can have very nice contribution from the aggregated state. That's one of the nice things. It is not in the literature always it is reported that aggregation is not good for dye-sensitized solar cells, but we are the first one to show that okay, if you control the dye aggregation, you can control it. Okay. Again, you can think of by looking at the kind of model dyes, we attribute to the a kind of photocurrent generation by the tetramer, and also Of course, this is the result. But of course, if you change the dye sensitization solvent, again you could be able to change the the whole things, because the solvation of the dye and the interaction between the dye and the TiO2 or interaction between dye and dye, all these things are going to be matter. So one has to be really careful in the sensitizing, what kind of solvent that you choose and everything. Okay, of course, and also we have checked the we have controlled the orientation of the dye. Okay, whether like orientation of the dye is very important. We systematically changed the anchoring group, and we felt that even though there is no coupling between the dye, it's not very efficient in the case of meta-coupled, but still the aggregated structures are very important, so that we can have very good control over the dye organization on the surface. That leads to the very good. And also, coming back to the electronic, we kind of substituted all the dyes with the different electron donating and withdrawing, because the HOMO and LUMO levels are very important. And the results says that the electron donating groups are very important, because the electron withdrawing group, like nitro, we found that the charges are moving in the opposite side. For example, this is the nitro group. We want to have the LUMO to be nearby, so that the charge coupling will be very efficient. Okay, of course, now we know where to keep the electron withdrawing group in the while developing the squalene dye. Of course, these are the things, and we also use the halogen bonding interaction to enhance the dye regeneration, because the dye regeneration is basically interaction between oxidized dye as well as electrolyte. That can be done by having this kind of you have the halogens. This is getting oxidized, but then you have the electrolyte. Electrolyte can have some kind of point contact, and that can enhance the dye regeneration. And further, of course, in the photochemistry, there is something called a heavy atom effect. We also make sure that the introducing halogen atom is not disturbing the electronic X-ray state. It's not going to the triplet state or something. Then we have done the systematically the photophysical studies on this one. Okay. Of course, this is the one, and of course, there are a lot of other dyes we have designed so that we want to cover the whole area. Because one dye covering the entire spectrum is not difficult, but by kind of controlling the aggregation or interaction between the dye, we can have it. Not only having it, but extracting the photocurrent generation, right? So yeah, this one dye, you can see that we can have the IPC response from 400 to almost like 800. There is no this is purely because of the way it organized it on the surface. Okay, of course we also changed these various donors and everything, and see that there is something interestingly we have seen that this particular set of dyes we can see the J aggregate. We can promote on the surface, and and we can see the electronic, and also we have seen the coupled dye. Like it's basically we were interested in how to communicate between the molecules and how one can take advantage of it. We made these kind of spiro dyes, and we showed that. Still, it is possible to have, even though the efficiency is not very high, but we could be able to see the, the panchromatic nature as well as photocurrent generation. Last, I think, this is something electronic. We can do the truncation of the double bond. Basically, instead of, if you truncate one double bond, you will get this kind of dyes. Then it will be very active in the visible, and we can have very nice, photo efficiency conversion in the visible light area, means visibility region, and we can do the post sensitization. Basically, you can couple two different dyes so that you can cover the entire spectrum. So that's something came out very nicely in this class of dyes. Basically, this is a visible dye, this is a forward dye, so that you can have very nice system out of it. Of course, we also develop a lot of dyes with that is compatible with other electrolyte, having deep HOMO levels, and I think I'll just go to the final stage. Maybe, of course, just one more thing. Recently, what we have seen is that we could be able to make a similar family of dyes that covers entirely from visible to forward to NIR. That's something we are very happy to see the dye, but the photovoltaic actions are very low because we are compensating the energy of the HOMO. Basically, when the energy of the HOMO is very near to the HOMO of the dye or electrolyte, basically when the energy level matches between the electrolyte as well as the dye HOMO of the dye, your regeneration is not going to work out. Even though the efficiencies are very low, but still we have hope that by using other electrolyte, we can have the better photovoltaic action. And with this one, I think I'm kind of summarizing. I think we have showed that if you if you control the aggregation of the dye on the surface, I think we can have a better photovoltaic action, especially for the square dye that aggregates very nicely on the surface. Okay. Of course, there are a lot of other spectroscopic issues we can talk about it, and these molecules also can be utilized in other area, especially the one that I have showed in the last, especially NIR active square dye. Yeah, thank you, and thank you for the opportunity again. I sincerely thank all my students and the funding agencies. And yeah,
thank you, Professor Nithyananthan, for the nice lecture. We can have only one quick question. Only one. Okay, student. Can you stand and speak louder? Yes, speak louder.
Yes, stability that can be circumvented by, for example, that's a very nice question because there are a lot of research is going on for developing a photocatalyst to degrade the dye. Okay, but here the dye is rightly sitting on the next to the TiO2. Okay, but one of the way to arrange is that how to avoid the moisture or oxygen or water. Because the mechanism, if you see carefully, the photoinduced electron transfer happens from your one of the moisture or oxygen, other things to the oxidized dye. So if you avoid these things, of course, there is an issue, but it can be tackled very carefully. Yeah.
Let us thank Professor Nithyananthan for the nice lecture.
Yeah,
so any further questions can be discussed during the break. So the next speaker of the session is Professor Suresh from... Oh. Yeah. Professor Nithyananthan, momento.
We invite Dr. Ramesh to share the everlasting reminder of the event to Dr. Thilagar, to Dr. Nithyananthan, NIC, Pune.
So the next speaker is Professor Suresh from IISER, Kolkata. So he is basically an organic chemist and he works in the area of photoredox catalysis. So with that, I welcome Professor Suresh to take the stage.
Yeah, thank you, Ramesh, for your kind words. Let me quickly start my presentation by thanking the organizers, particularly Shiva and Suresh, for nice invitation and the fantastic hospitality from MKU University. I am also happy here to present my talk in front of my PhD supervisor, Professor S. Chandrasekharan. So it's a kind of, mixed feeling. I'm a bit afraid as well as, it's happy. So today I'm going to talk about photocatalyzed functionalization of cyclopropenes. Basically, photocat means we are going to use visible light, okay? So before I start, let me quickly tell what we do at IISER Kolkata. We are working on 4 different topics. One is photoredox catalysis, another one is fluorination, the third topic is functionalization of sp3ch bonds, and the fourth one is tandem multi-component reactions. Basically, we use this photoredox catalyst as a tool to address all these 3 problems. Okay, so with that, let me start my presentation. As Professor Chandrasekharan pointed out today morning, the modern transformation, why light? As you can see, solar spectrum, 44-46% available in the nature. So our idea is to use the sunlight. For practical purpose, whatever I'm going to show today, we're going to use, commercial light so that it's easy to control the reaction and reproducibly and so on. The ultimate aim is to use visible light to do your transformation. That's the light. Okay, so as you all know that organic chemists or any scientist who is always inspired by nature, am I right? We want to make the molecules the way nature does in plants, using sunlight to make complex molecules. But the challenge, if we want to use sunlight, most of the organic molecules that we deal with in our life, they cannot interact with the visible light. Am I right? So that is the challenge. The modern research, what they do is that we are going to modify or improve the visible light absorption capacity of the organic molecules or complex. As a result, what we can do, we can use these molecules as a photocatalyst. Am I right? That's the aim. Okay. If it acts as a catalyst, then we can do different type of chemical transformation. This is a kind of typical photocatalyst, how it functions. Okay. As you all studied that, when you shine a light on the photocatalyst, it gets excited. It undergoes different type of physicochemical properties. To make it short, it goes to singlet and then intersystem crossing to go to your triplet. Most of the chemistry that is happening from your triplet. Am I right? So this you might have studied. If you look at the reaction of this photochemistry, you can classify it into three types. When molecule get excited, it can does energy transfer process. As a result, one can do cis-trans isomerization reactions, or one can do pericyclic reaction, for example, cycloaddition reactions. Okay, that is the one kind class of reaction. The another type of pathway that is going to do what it does is that excited photocatalyst, it can reduce the substrate. The AI is nothing but your co-catalyst or additive, whatever you can call it as, that we use in the reaction. What it does is that, as you can see that, it reduces, as a result, photocatalyst is getting oxidized. As a result, it forms radical cation. This radical cation, we'll call it as oxidant. It is going to oxidize your substrate. As a result, you will get oxidized substrate in the radical cation form that undergoes different transformation to give you a product. This cycle, we call it as oxidative cycle because it acts as oxidant. Okay. On the other hand, if you look at the photocatalyst, that is excited state, that is there, it can oxidize the substrate. As a result, photocatalyst is getting reduced. Now it can act as a reductant. It reduces your substrate. As a result, you will end up with a radical anion that undergoes different type of reactions to give you a product. All you have to remember is that photochemical reaction is not single-step reaction. It's a multi-step reaction. There are several processes that is going to happen. As a result, what you are going to see, this is one of the challenge, how to control these so many reactions to get your final product. Okay. So, as you know that I will show you one typical example. You might have seen that one. This is the typical ruthenium photocatalyst. When you shine a light, what happens is that it undergoes excited state. Now this excited photocatalyst can, as we saw, it can act as oxidant as well as reductant, so that one can do several type of reaction. The another thing is that not only inorganic complexes, you can use simple organic molecule. For example, I have taken here usine Y. It's a simple dye. It's a very inexpensive. You can get it very less price. And this one also you can see when you shine a light, visible light, it gets excited, intersystem crossing, and forms diradical. Now this diradical acting as oxidant. As a result, one can do several type of reactions. Okay. So in our lab, one of the ongoing project is that how to functionalize different type of cyclopropane derivatives. Today, I am going to stick to the cyclopropenes, how we can functionalize the cyclopropenes using your visible light photocatalysis. So as you know that this cyclopropane shows different type of reactivity. I don't want to get into the details. And why cyclopropenes? I can summarize in one slide. It has a lot of applications in chemistry and biology. I don't want to get into details. So if you look at, there are different methods to make the cyclopropenes. Okay, these are our classic methods. Our approach is that how to use this visible light catalysis to do radical addition to cyclopropanes in a regio and diastereoselective manner to functionalize polysubstituted cyclopropane derivatives. This was our aim. So to summarize, we do, as I told you, we do different type of transformation. For example, you can see here, we have shown that as a hydroacylation reaction, again, highly diastereo as well as regioselective fashion to get this kind of tetrasubstituted cyclopropanes. The another method is we can do aryl hydrosulfonylation reactions, again, diastereoselective and regioselective way with a lot of substrate scope using simple organic photocatalysts. That's what I am going to show some of the results today. And the next one is that you can do hydrotrifluoromethylation reactions using simple organic photocatalysts. The fourth one is, it's a very interesting in terms of sustainable technology and green chemistry point of view. What is that? We are going to do iodo-tosylation reaction using tosyl chloride or any sulfonyl chloride and sodium iodide. Here this reaction works without any photocatalyst, just light is important, and here it forms EDTA complex, thereby you are generating sulfonyl radical that adds regioselective fashion to cyclopropane followed by iodination reaction. The key highlight of this reaction is that we can do this reaction in water. photochemical reaction in water. Okay, that's the special advantage of this reaction. And other example, we can do sp3 alkylation reaction through sp3CH bond activation, and to get this kind of trisubstituted alkyl derivatives. The another one is that we can do keto alkylation reactions and thioesterification reactions. Okay, if you look at the reactivity here, sometimes you see that your cyclopropane is retained. In some types, you see cyclopropane is reopened, and you will get substituted alkene derivatives. Okay, that is the kind of observation we can get from this slide. One slide you can see it acts as a cyclopropyl synthan. In another case, it's a vinylsynthan synthan. The interesting thing comes into picture now. If I take, instead of aryl sulfonate salt, if we take alkyl secondary sulfonate salt, the interesting things are happening here. You can generate S-centered radical as well as C-centered radical. As a result, you can see that you will end up with this kind of cyclopropyl moiety, or if it is C-centered radical, you see C-alkylation to lead to ring open product, you will end up with a trisubstituted alkene derivatives. So today, this is what we are going to talk about today. Why, in case of secondary sulfonate, there are two types of radicals are possible, and why in one case the cyclopropane is retained, in another case it's undergoing ring opening reactions. Okay, that's what the thing you are going to learn from this presentation. So with that, let me proceed now. So I no need to tell why sulfur. Sulfur is the, if you look at the FDA approved drugs, it is the third most element next to your oxygen and nitrogen. Okay, so it has a lot of applications and so on. So with that, let me start with my work. So always in catalysis, the right thing is that you have to choose the right model substrate. If your model substrate is wrong, then everything will be end up with lot of issues. You have to choose the right model substrate. We have chosen here this phenyl substituted diester cyclopropane as the model substrate, and this toluyl sodium sulfonate salt as a sulfonate reagent. As you all know that in catalysis, most of the time we spend in screening and optimization reaction in order to get the ideal or the best reaction condition for your transformation. As you can see here we got the best result in terms of methanol, 94% yield. Here you see the reaction again, as I told you, is highly regioselective. It adds less up to that site of the cyclopropane. Again, it's highly diastereoselective. Both the substituents are trans to each other, and again, it's a very clean and high yielding reactions. Even you can do this reaction in ethanol, no issues in the green and solvent. And the catalyst that we are going to use, erythrocene B, is a simple organic dye. Okay, once you got the optimization result in photocatalysis, not only in any catalysis, the challenge is how this optimized condition is going to work with n number of substrate. You may be having the reaction good condition, but it may not work with wide range of substrate. That means that is one of the drawbacks. The second one is, what is the reproducibility? Whether this reaction can be reproducible. When you do the reaction same time for 10 times, whether you can get the same yield that you are reported. Okay, these are all the kind of challenges in photochemistry. The third one is scalability, whether this reaction can be done at larger scale, for example, in gram scale. Okay, these are all the kind of challenges. The first thing we are going to address here is that the substrate scope. As I told you, you see it works with a number of substrates, no issues. Okay, first let us start with the different ester cyclopropane derivative, methyl, tertiary butyl, isopropyl, and so on. And here, instead of 2 esters, we can make phenyl and 1 ester. And again, you see all the cases IDR. You will not see another DR in crude NMR, okay? Unless few cases which I have come to in a minute. The second one, we tried different substituent on the aryl rings, tertiary butyl, methoxy, fluorine, chlorine, and so on. All are fantastic, no issues. Even you can use, instead of phenyl, you can use naphthyl derivatives, no issues. The another interesting thing comes here, we can use this kind of fluorine substituted cyclopropane. These are all biologically very, pharmaceutically very interesting molecules. Again, you see very good yields here. And it works with a different substituent, no issue. And these two substrates, pay attention here, not only aryl here, you can use alkyl cyclopropanes. Alkyl cyclopropane, no issue. Now, you take here this substitute, cyclopropane. Here if you see, it's a penta-substituted cyclopropane derivative. As a result, the starting cyclopropane is tetra-substituted cyclopropane. Upon introduction of sulfonate salt, you will end up with penta-substituted cyclopropane. Only drawback is you are compromising the DR. You are getting 60:40. Again, it's a your tetra-substituted cyclopropane works nicely, no issues. And this is another two things. It's again tri-substituted. Here you see simple diphenyl substituted cyclopropane can be used as a substrate with a moderate yield. Okay, that is one of the challenges there that maybe we can discuss during the discussion, why yields are low there. Okay, so next, let me quickly go through now. Now we change different sulfonate salt here. Okay, you see variety of sulfonate salt, no issue, fantastically it works. You can use aryl, alkyl, no issue, fantastic. Now comes the challenge. Okay, before getting into the challenge, as I told you, one of the challenges is that whether we can do this reaction at large scale. It works in gram scale, no issues. We can get fantastic yield with a 2 mole percentage catalyst loading. Okay, that's the beauty. And we have done some kind of functional group transformation, whether this can be converted into some useful intermediate. Yes, of course, we can do that, no issues. And second, the interesting topic comes now. This is the thing we are going to address. This is the problem that I told you. Nah? So when we use secondary sulfonate salt, this is what we expected. This is what we want. It works with aryl sulfylate. If you take simple alkynyl salt, it works as a sulfonyl radical source, and it adds to your less substituted cyclopropene site and in a highly diastereoselective selective fashion. Yes, this is the expected product, but low yield. What is the rest of the material? The rest of the material is that this is the material. It's a cyclopropene. If you see it, if you look at it, it's a tri-substituted alkene. Cyclopropane is gone, and again you see the yield is 63%, slightly more. And what's going on here? Then to address this one, if you look at the sulfonate salt, sulfonyl radical, and for example carboxylic acid radical, for example, you take this one, carboxylic radical, and if you look at the structure, both are same structure. No, you all know that. The minute if you generate carboxylic acid radical, it simultaneously undergoes carbon dioxide elimination to give you 5 minutes, okay? So alkyl radical, okay? This you know. When it comes to your sulfonyl radical, the story is different. So it's depending on the substituent that is there on the sulfonyl radical substituent here. If it is aryl, methyl, then the sulfonylation won't take place. If you put electron withdrawing substituent like CF3 and so on, the sulfonylation is facile. As a result, you will see kind of C-centered radical formation. This is a kind of, there is a theoretical support for this one. So based on this, we try to optimize our reaction condition. Yes, we can selectively make either by using this condition in DM up at 10 degrees Celsius, acetic acid condition, you can get this product as a major one. By changing the temperature from 10 to 40, you can get this ring open product selectively in highly diastereoselective fashion. Okay, that's good. So we have the control now. We can, then the next aim is to test with the several substrates. As I told, we tested with several substituent. It works fine. If you use condition A, that is nothing but if you do the reaction at 10 degree, you can get ring retained product in a very good yield and selectivity. Again, if you do the condition at a slightly higher temperature at 40 degree, you can do ring open product with the elimination of SO2. So this is some of the control experiments we have done. Maybe I will skip this one. I think we just do systematic study, quenching studies, and radical trapping and so on to prove the reaction mechanism. So this is the set of experiments we carried out, and we have studied some cis-trans isomerization studies during the reaction. Whenever you get C-alkyl radical, you will end up with a tri-substituted alkene. There we have seen whether there is any cis-trans isomerization. Yes, there is a cis-trans isomerization is happening. That leads to, under photoelectrical condition, the more Z type of alkene. That kind of studies we have done in NMR and so on. Here basically what happens is that, let me come back to the main slide. This is the substrate scope. So computational study I can skip. So otherwise Ramesh will be angry. So maybe this is the final slide. Okay. So to summarize, you know that catalyst, it's undergoing single electron oxidation to generate the sulfonyl radical. Now here comes the catch. If you do at low temperature, your sulfonyl radical is retained. As a result, it adds to cyclopropane. If you see, there are two types of diastereomers. The trans one is more stable, which further undergoing single electron reduction to generate anion protonation gives your hydrosulfonylation product. When you do the reaction at higher temperature, at 40 degree, what happens? SO2 elimination takes place, and then your alkyl radical adds to this cyclopropyl. Again, here there are two type of cis trans isomers are possible. The energy difference between these two is very close. As a result, these both can lead to the corresponding. I'll conclude my presentation. Maybe I am a bit fast because of lack of time. So to summarize, what we showed is that we can do, if you use secondary sulfonate salt, using your temperature and solvent, you can do selective S alkylation versus C alkylation reactions. With that, let me finally thank my group. They are the one who is, really doing all the work. This entire work is done by Dr. Chandu, who is recently graduated. So with that, I thank IISER Kolkata, SARB for financial support. Finally, thank you for your
Thank you,
kind
Professor
attention.
Suresh, for the kind presentation and finishing within the time. We have time for only one quick questions. Yeah, please, you can just give her a chance. Yeah. Yeah, you can.
Yeah.
Wonderful chemistry.
Thank you.
At the end, I would expect that the sulfone would be easier to reduce, okay, than the alkyl derivative, and yet the chemistry seems to be more important on the carbon ion chemistry from the alkyl side. Could there be a 1-2 shift? So you had this negative proton, and then it goes and stabilizes through the sulfone, and this is your ready state.
We did not observe that one, 1,2 hydrogen shift, because that benzyl radical, though in principle, carbon ion, because radical has to shift first, am I right?
Then you reduce easily the radical.
Yes, that's right.
And then you're resting state.
See, that's why I showed simple substituted diphenyl, even simple CH2. It's a symmetrical one. It happens. Anion reduction happening. It need not to be like on sulfur side. We'll discuss.
Okay.
We'll discuss later.
We can continue the discussion during the break.
Sir, for photocatalysis, you use ruthenium bipyrrole, right? How do you think about its availability?
I did not use here. It's easy to make from your ruthenium trichloride and your bipyridyl ligand. We can make all these ligands. We catalysts we make. We never buy them. It's very particularly iridium and ruthenium ones. Ruthenium one okay. Iridiums are very expensive.
Yeah. So let us thank Professor Suresh for giving a very nice presentation.
Yeah.
Thank you. So here is a small memento.
Thank you, Professor Ramesh. And now I will break for the lunch. Then after lunch, we'll continue the session. உங்க பசங்க இருக்காங்களா?
இவரையா நான் யூஸ் பண்ணி
இவரை பேச கூட்டு போய் அவரை அனுப்பிச்சு விட்டுருங்க.
Hello, hello.
Next session?
Session 2.
Session 3 ma.
Listen, session 2 continue.
Okay. Announcement. Master.
Everyone would have enjoyed the well-deserved lunch. Hope you enjoyed the stimulating session this morning. Let's continue session 2. We invite Dr. Ramesh IISER Trivandrum for the further proceedings. Session 3.
Yeah. 1 minute. I invite Professor B. Ashokkumar, School of Biotechnology, Madurai Kamaraj, to share this session. Yeah, thank you.
Speaker introduction.
Just introduce me. Ramana from Arunachalam. Brief just introduce me.
Okay. It's okay.
Arunachalam.
Glad to meet you all in the afternoon session. This session, the lecture will be delivered by Dr. N. Arunachalam from Gandhigram Rural Institute. So since we are running out of time, without any further delay, I just invite Dr. Arunachalam to deliver a talk on unveiling molecular recognition and functionalization strategies. Thank you.
Okay, very good afternoon. Am I audible?
Yeah.
Okay. So very good afternoon to all. So the title of my talk is Pillar 5 Arenes, Unveiling Molecular Recognition and Functionalization Strategies. So actually the area of my work is supramolecular chemistry. But in today's lecture, we will not only focus on supramolecular interactions, but more on functionalizing the supramolecular hosts. So here the molecular hosts we generally focus is pillar arenes. Okay. So supramolecular chemistry is defined as chemistry beyond the molecules. So which mainly deals with non-covalent interactions, such as hydrogen bonding, electrostatic interactions, pi-pi stacking interactions, anion pi, cation pi, and in recent times it also deals with halogen bonding interactions. So inspired by nature, many scientists have developed artificial receptors for the recognition and sensing of cations, anions, as well as neutral molecules. So these people, Jean-Marie Len, Cram and Pedersen, so they are the pioneer in the field of supramolecular chemistry. By recognizing their achievements, so they have been awarded Nobel Prize in the year 1987. So after that, the field has bloomed a lot, and they have shown that initially they have shown that molecular recognition by crown ethers. So it is a well-known supramolecular host. So later on, they have also modified it. They functionalize crown ethers into cryptons. So the functionalization is very, very important because crown ether is just a macrocyclic molecule, but when you functionalize it with another arm, so just augmenting another arm to the supramolecular macrocycle, so it binds better because there are 3 arms, so the gas can be tightly bound into the cavity. Okay. So we might have seen like this mechanically interlocked architectures in our ancient temples. Say for example, this one, this you can, this you can see it in the temple at Uttarakosa Mangai. So here you can see a rolling stone inside the yali. So this is the mechanically interlocked architectures. And again, this particular stone chain that is available in Kanjipuram, Varadarajar temple. Scientists have thought of making this type of mechanically interlocked molecules by using their synthetic chemistry knowledge, and they have also achieved, and they have also made molecules like this. So here it is an example of rotaxanes. It is one of the mechanically interlocked molecules. There a cyclic molecule is threaded by a linear axils, and the axils are functionalized further with bulky stopper so that the ring cannot dethread from the axle. So this type of architectures are called as rotaxanes. And if you functionalize two different rings together without any covalent linkage, if you can make it, then we call them as catenanes. So due to these, especially Fraser Stoddart, he has contributed more on rotaxanes, and Jean-Pierre Savage, he has focused more on this type of molecular architectures called catenanes. So, and this particular gentleman, Ben Feringa, he has developed molecules, he has developed molecules like nano cars, okay, so molecular robots or something like that. So for their contribution in making mechanically interlocked molecules and nano devices, they have been awarded Nobel Prize in the year 2016. So there are these type of macrocycles like crown ether, cryptans, calixarenes, and cyclodextrines are well explored as a supramolecular host for molecular recognition purposes. And recently, not very recently, even it was synthesized long back, but they have characterized this molecule, a pumpkin-shaped molecule called cucurbituryl, which is also explored for host complexation in aqueous media because the molecule is soluble in water. But the problem is we could not functionalize them further. So say for example, crown ether, even cucurbituryl, cyclodextrine, so they all have the problem of functionalization to get the desired applications. And we at IISc Calcutta, I have also worked on this type of acyclic molecules, tripodal receptors as well as hexapodal receptors for the binding of anions. And here at Gandhigram Rural Institute, our focus is mainly on pillar 5 arenes. So the name itself tells that this molecule contains pillar-shaped architectures with 5 arene motifs. So this can be easily synthesized from 1,4-dimethoxybenzene and boron trifluoride as a Lewis acid. So when it is reacted with formaldehyde, we can make this type of cyclic oligomers. Either the cyclization may take place with 5 arene units, then we call them as pillar 5 arene. If it cyclizes with 6 arene units, we call it as pillar 6 arene. The pillar stands for its shape, pillar-like architecture, and 5 arenes. 5 arene units are there, that's why we call it as pillar 5 arene. The specialty of this molecule is it has the internal cavity of 4.7 Armstrong, so which is which can very well accommodate smaller guest molecules, especially cationic guest molecules, because this arene is pi electron rich, so the cavity can include cationic guest molecules. And moreover, we can see here there are 10 alkoxy subunits, 10 alkoxy units are there. So we can functionalize them to make our desired molecules. So if you add boron tribromide, we can easily dealkylate that one. So we can convert it into OH groups that can be further functionalized. Maybe even we can make it water soluble by attaching either cationic or anionic functional group. We can make the molecules water soluble. So what we have done, we have used we have prepared this one, the monocarboxylato pillar fibrine molecule. So we have selectively dealkylate the O-methoxy group there. So we have converted it into OH group and further functionalize it with carboxylic acid group. So we have prepared this monocarboxylato pillar fibrine and attached it with a RAMP monomer, ring opening metathesis polymerizable monomer, oxonarbornine based monomer, so that we can polymerize them using Grub's first generation or second generation catalyst, olefin metathesis catalysts. So we have made this type of polymers by just functionalizing one OH group and attached it with some polymerizable functional groups. So this polymer material can be used for making, we can use it for different applications. So before going into the applications part, so let me tell you that monomer, just we have studied the monomer and studied its complexations with a biscationic gas molecules like this. So the biscationic gas, bispyridinium cation gas will bind with the electron-rich aromatic systems, so that the NMR can be used to monitor the host gas complexation studies. So you can see here there is a huge change in their chemical shift. Since the pyridine unit goes into the cavity, it experiences a shielding effect. So the NMR spectrum shows shift in the shielding region. We have also probed the host gas complexation in using 2D NOSI NMR experiments. So it shows that a clear correlation between the host as well as the gas molecule. And to establish the stoichiometry, we have carried out a proton NMR titration experiments, so which clearly shows that more than 1 ppm shift in the signals of the gas molecule, and the Jobs plot analysis shows that it binds with 2 equivalents of host and 1 equivalent of gas. So 2:1 host-guest stoichiometry was observed as shown here. So this type of pseudo 3-rotoxane assemblies are very important in the sense that we can make supramolecular polymer materials by using this type of pseudo 3-rotoxane assembly as a cross linkers. Then we have studied the host gas complexation experiments with the polymer synthesized using Grub's olefin metathesis reaction, ring opening metathesis polymerization reaction, and the bisgest, upon adding bisgest to the polymer, then it shows again clear correlation peaks. So it indicates that even in the polymer also it forms complexes. Then we anticipated that again the assembly shows 2:1 host-guest stoichiometry, which again confirms that this type of supramolecular polymer assembly might be occurring there. You can see here the polymer attached with the pillar fibrine unit. One pyridinium unit is complexing here, the another pyridinium is complexing with another polymer, so that it may leads to supramolecular polymer network. So we have also confirmed it with dynamic light scattering experiments, which shows that there is a huge change from 15 nanometer to 1900 nanometer, so which again supported the cross-linking supramolecular polymer network. So when we dilute the supramolecular polymer network to 10 to the power minus 6 molar concentration, so slowly the diffusion constant increases. It indicates the size of the polymer network is slowly decreasing. Again, which also supported the intramolecular cross-linking, which leads to decrease in size. That means the linear polymer chain are cross-linked intramolecularly, so that they can form a single chain polymer nanoparticles. So we can reduce the size of the polymer nanoparticle by using non-covalent host-guest complexation as the cross-linker. So again, next we have functionalized the pillar fibrine. Here in the arene units, we wanted to make substitution. So what we have done, just by adding ceric ammonium nitrate, we can selectively reduce one arene unit. Of course, we will get mixers. We can isolate the monoguinone as a major product by just then again by using Michael addition strategy, we have functionalized with some hydrogen bonding motifs. So before that, we have also studied the host gas complexation with the pillar fibrine and the monoguinone and the ethanolamine functionalized pillar fibrine, but this shows a better molecular recognition property compared to the other one, because this ethanolamine functionalization impart hydrogen bonding functional groups to the macrocycles. So we have studied the host gas complexation with the bis imidazolium gas, and which shows that the 2:1 host gas complexation is preferentially formed over 1:1 complexation. That means pseudo 3-rotoxin is preferentially formed because of the hydrogen bonding interaction between the macrocycle. So after the binding of first macrocycle to the acyl, the second macrocycle binding is even facilitated by the first one, because it shows the hydrogen bonding interaction between the fragments that we attached with the macrocycles. So this we call as cooperativity, as we have observed in the case of hemoglobin. Okay. So again, next we in our attempt to functionalize pillar fibrine with amine motifs, so we have tried with perfluorylamine, because that furan group can be again Diels-Alder, it can undergo Diels-Alder reaction, so that we can make polymers. So in that aspect we tried this one, but during the Kalam purification itself, this compound has been crystallized. Okay. So we have used hexane and ethyl acetate as the eluent. Then during the Kalam chromatography itself, in the test tubes we formed very good crystals. So analyzing the structure of crystals shows the hexane molecules entrapped into the cavity of pillar fibrine. So which shows that it has a very high selectivity towards that hexane. So we wanted to make this polymer, sorry, not this polymer, we wanted to make this molecular tube. So you can see it forms an array of pillar arenes stacked together to make a columnar tubular assembly. So we wanted to make it as a useful material for the molecular recognition purposes. Then we have exposed the crystals into iodine vapors. It shows a tremendous absorption of iodine. Almost per gram of material, it can absorb 4 gram of iodine. So 4 gram of iodine per gram of the supramolecular host. So we postulate that the iodine may also enter into the cavity of pillar fibrine, because this experiment we are doing at elevated temperature, around 100 degrees. In the oven we used to keep the iodine, and inside the vial we used to keep the crystals. So the vapor has to come and adsorb on the crystals. So it shows that there may be the inclusion of iodine into the cavity, as well as there is also a exterior cavity, maybe in the crystal lattice also iodine may be adsorbed, because this huge adsorption shows that it can be used for iodine vapor capture studies. So this we have confirmed by SEM-EDAX elemental mapping images. Yeah, we are fortunate to, we can see this one. So iodine is showing, iodine is adsorbed over the polymers, and again we can also reuse the material. So once we add hexane, again that trapped iodine is coming out, and the hexane solution shows iodine into the solution. So again further functionalization using Friedel-Crafts alkylation. So we can take pillar fibrine and functionalize with some benzyl chloride derivatives. So we have done several compounds, but I am selectively showing this one. So stilbene based benzyl chloride. So what we have used is ferric chloride as the Lewis acid, so which undergo Friedel-Crafts cross-linking polymerization, Friedel-Crafts polymerization reaction, which gave a cross-linked polymer. The polymer material can be used for water remediation applications, because we have also studied this one. It can absorb iodine and also methylene blue dye from water. Just pass through the methylene blue aqueous solution through the polymer material, the effluent water will be completely free from dye as well as iodine. So in this presentation, so we have demonstrated that the importance of pillar fibrine and the appropriate functionalization of pillar fibrine could be used for making desired applications. Maybe we can use it for supramolecular polymer materials, we can make supramolecular nanoparticles, and also we can make environmental remediation applications of these polymers as well as small molecules. So with this, I would like to thank the organizers for giving me the opportunity to share some of my research work that we are doing in Gandhigram Rural Institute. Thank you. Thank you for listening. Thank you.
Maximum 2 questions, please. Yeah. What's the driving force of going inside the cavity?
Yeah, that electron-rich pi-aromatic systems,
Yes,
they
it's a
stabilize the
donor acceptor thing, right?
Pardon?
It's an electron donor acceptor.
Yes, sir.
Okay.
Yeah, we have
have you ever thought about or observed the follow-up electron transfer?
Yeah, there is a chance also, sir. Because iodine, only it will not absorb iodine as a molecular iodine. Even it will also convert iodine into I minus, I3 minus, I5 minus also may be absorbed. But in the vapor phase, it shows
that's particularly interesting. You can use it as a catalyst. Okay? So if the electron transfer process is possible.
In aqueous media, it absorbs I3 minus, I5 minus, because iodine is converted into iodides.
So the methodization is to using light. So after formation of the complex, put some light, visible light or so, appropriate light, and then you may see the electron transfer process. Okay. So have the potential to have as a photocatalyst.
Yeah, that we are not focused on, sir. We take your points.
Okay, fine. Thank you.
Yeah, this cavity can be used for drug delivery applications. For that, we have to functionalize the macrocycle with water-soluble functional group. Either we have to make it as a cationic as well as anionic. Then we can use it for drug delivery application. Otherwise, it may be a toxic one. Because we have to make it water-soluble, and also we are also working for drug delivery applications, especially biofilm inhibition properties of that polycationic pillar fibrines. That we are working actually.
Thank you. I have a question. Yes. And you have synthesized a synthetic polymer for environmental application. Is that toxic to environment?
It is not soluble in water, sir.
Oh, it's not soluble in water?
It will not be soluble because it is hyper cross-linked polymer. Okay. So it is not soluble in water or any solvent.
So it can be easily recovered from the environment?
Yeah, even it won't be soluble in DMF, DMSO, so no problem. So it will not be soluble. Highly cross-linked polymer. Okay. And during the synthesis procedure, we have purified the polymer by using extraction with all available solvents, because mostly chloroform, methanol, so that to get rid of all the monomer units. So the polymer will be stable enough. Even it is stable up to 300-400 degrees Celsius, because it depends on the polymer. Sure. So even based on thermogravimetric analysis, we come to know that even 300-400 also they are stable.
Yeah. Thank you. Thank you so much.
Thank you for giving me the.
Thanks. So with this lecture, the session 2 talks almost completed. You really, okay. So you would like to share it? No, sir. Okay. Yeah. Dr. M. Arunachalam, I think. Arun, yeah, I invite you to receive this momentous moment. Thank you. Thanks. Yeah, right. Thank you. Now the session 3 starts. In this session, we have 5 lectures, 1 plenary lecture and 4 invited lectures. The time allotted for the plenary lecture is 30 minutes and 25 minutes for the invited lectures. I request all the presenters to strictly adhere with the time. And the first session of a lecture will be given by Dr. C.V. Ramana from NCL Pune. He is going to deliver a talk on total synthesis-driven methodologies. Dr. Ramana, he is associated with NCL Pune since from 2001 as a scientist. Right now, he is a chair of principal scientist in the organic synthesis, organic chemistry division. And sir has received many awards, and a few I would like to highlight. You know, he is the recipient of CSIR Young Scientist Award in the year 2003. And another prestigious award I would like to mention, CNR Rao National Award in the Chemical Sciences Division. So with this small introduction, I invite Professor to deliver a lecture without further delay. Thank you.
Thank you, Dr. Ashok, and also Dr. Sureshkumar for the invitation and the great hospitality. Today I will be talking about some methodologies that we have developed in the context of your total synthesis. Coming to what we do at NCL, down here. Okay. Yeah, coming to what we do at NCL, since for CSIR scientists, it's not only the basic research, but we have to work with many of the industries. So this gives us a lot of scope to explore many areas, and you can see actually my group works in different areas like starting from the carbohydrates to total synthesis, methodology development, peptides, and also nucleic acids, apart from the developing the process development. So when it comes to highlighting our group, whatever the output so far, so we have completed almost 54 total synthesis, out of which 20 are first total synthesis. And in most of the cases, what we try to do is we try to use as many catalytic events as possible in your total synthesis. That is one of the key aspects actually whenever we want to select a natural product as a target for the total synthesis. And one more important thing, what we see, especially when we want to select a natural product for any total synthesis, we would like to see actually that natural product has an unprecedented skeleton. The advantage of having an unprecedented skeleton is, so you get an opportunity to develop a method to address actually how this skeleton could be constructed. Yeah, today I'm not going to really bother you by showing you a linear sequence of 20, 30 steps and finally completing with a natural product. But what I would like to show you is, I would like to show you how one of our total synthesis has inspired to really delve into the methodology, really develop some new methodologies or new transformations. See, say about 15 years back, actually, we started the total synthesis of a class of natural products which are known as pseudo-indoxyl class of natural products. Pseudo-indoxyl means actually say, okay. Yeah. So this is the pseudo-indoxyl scaffold. If you make a dimer of this thing, actually that is simply indigo. This was a intermediate that has been isolated during the structural elucidation of the indigo by Bayer. So anyway, you have a range of pseudo-indoxyl natural products having alkaloid units or the sugar units attached. And we were particularly interested sorry. So if you see actually whatever the total synthesis that have been reported for the synthesis of this class of natural products, what generally people employ is you take a 2,3-disubstituted indole and treat with peroxide or peracid, and you will be getting a epoxide like this. This actually, when you heat with a base or acid, actually it undergoes a rearrangement to get this pseudo-indoxyl scaffold. This is one of the common reaction that has been used by many of the scientists for the total synthesis of this class of natural products. However, what we have asked is, if I have a simple cyclic nitron like this, this gives me a chance to add the nucleophiles at the C2 position, whatever the nucleophile I would like to have, and at the same time actually it also gives a chance to develop a asymmetric methodologies. So with this idea actually we have looked at the methods that have been reported for the synthesis of this estrogen, and here you can see actually this estrogen has been synthesized almost 120 years back by Bayer. So one of the first reported conditions for the preparation of this compound actually using concentrated sulfuric acid or hot pyridine as a solvent. So then actually this transformation has been simplified by photolysis or doing actually Sonagashira as well as heating in the copper sided. And very recently, Yamamoto has reported a catalytic method where actually you can use the gold bromide as a catalyst and do the same reaction in toluene at room temperature. It gives the estrogen, but at the same time actually it also gives a side product which is isomeric to this estrogen, which is anthranil. And this reaction is facile when you have a R is equal to aryl group, but when you have a R is equal to alkyl, it gives exclusively the other undesired product which is anthranil. And later actually even Crabtree also tried the same reaction with employing iridium complex. Again actually here you have the exclusive formation of anthranil. Without much delay, what I would like to show you, sorry. We have screened various complexes and actually realized that actually this transformation can be diverted exclusively towards the estrogen, whether you have a R is equal to aryl or alkyl, to get completely estrogen by using a palladium complex. And then, as I told you, sorry, I have not yet told, sorry. So, what we have proposed as a part of this mechanism is this reaction involves the formation of a nitroso-stabilized alpha-oxo gold carbene. In case of the palladium, this is a carbene which is stabilized by the nitrogen. In case of the gold, actually it is a carbene which is stabilized by the oxygen. In both the cases, it's a 6-member ring. These two are isomeric. In one case, actually, the cyclization leads to anthranil. In other case, actually, the same cyclization leads to estrogen. So then actually, after establishing this simple method for making the estrogens, the next task is actually how to use this in the context of the photosynthesis. So here what we have done is we have selected the estrogens, especially whose structures having a C2 indole substitution. So if you see all these things, actually you have a C2 substitution here. So now the next question is how to add this indole to estrogen, and this we have addressed by developing various transformations. First, actually, we have employed indium chloride as it's not a catalyst, but actually we had to use stoichiometric amount to add the estrogen to indole, and we completed the total synthesis of that 13-deoxyacetylcysteine A, and also by using the same transformation, we have completed the total synthesis of acetylcysteine A, and later actually we employed a gold complex to add actually the C2 of the indole to the same estrogen, and this allowed to complete the total synthesis of tricholamine C. And very recently, we have established a catalytic method by which actually you can add the indole to this estrogen, but at the same time, actually you are also reducing the NO bond, by which actually in one step we can complete the total synthesis of the cephalaminone C and halenochromone A. Now, apart from this, whatever the addition of indoles, we also combined actually this cycloaddition, this cycloisomerization along with the cycloadditions, like if you keep a allyl or butynyl or pentenyl, actually you can make a 5 or 7 or 8 member fused ring. Actually, this method we have developed in the context of the total synthesis of ostomoideae. Although the whatever the model studies, they gave the requisite tricyclic scaffold, the ostomoideae, but when we went for the total synthesis, what happened is actually it didn't give the required this bridged bicyclic skeleton, but it gave a linearly fused cycle, which is not the required one. And later we also, later we also combined actually this cycloisomerization along with the 3+3 cycloaddition, and very recently, when we employed a benzene as a dipolarifier in this cyclization, what we expected is a isobenzoxazole scaffold, but what happens is this isobenzoxazole scaffold initially formed, it undergoes a 1,3 sigma tropic shift, and then actually a retromagnetic reaction leading to an anion. This adds to the, again, this iminium ion, and finally leads to a isomeric benzoxazole scaffold. I think the confusion is always there actually. So coming back to the our mechanism, as I told you earlier, actually, we have proposed the formation of 2 isomeric alpha-oxo gold carbenes in these nitroalkyne cycloisomerizations. Very recently, we tried to understand actually why these isomeric gold carbenes are formed and also how stable they are. And what we have realized from the DFT studies is whatever the carbene that was formed from the 600 dig cyclization with the gold complex, this is quite stable. And this asked us to a simple question: is it possible to trap this gold carbene by external nucleophiles? In this regard, actually, I would like to show you two transformations. One, anyway, I am speaking for last 10 minutes. What are the nitro-alkyne cycloisomerization leading to this oxo gold carbene. And in parallel, actually, in 2010, actually, a French group has come up with a similar cycloisomerization where actually in place of the nitrogen, you have a azide. And this leads to the formation of a alpha immuno gold carbene intermediate. This can be trapped with a different nucleophiles to get the indole substituted at the C3 positions. So we have asked a simple question because these, what are the two transformations that I have shown? Actually, these are the intramolecular, either oxygen or nitrogen transfer. But you have actually a variety of reagents which can be employed for the intermolecular oxygen or nitrogen transfer. Intermolecular oxygen or nitrogen transfers. Here you can see a list of reagents that are used for the nitrogen transfers. So what we have asked a simple question is, if you conduct the same intramolecular nitrogen or oxygen transfer reactions in presence of these intermolecular nitrogen transfer agents, what happens whether intermolecular nitrogen transfer is facile or the intramolecular nitrogen transfer is facile. And at the same time, actually, our interest is whether whatever the gold carbenes that we have postulated, whether these carbenes can be trapped by these nitrogen sources. For example, if you see this nitro-alkyne cycloisomerization, as I told you, this leads to a alpha-oxocarbene like this. And actually, if you have a nitrogen transfer agent like this, where actually in nitrogen you have a leaving, nitrogen is attached with a leaving group like azide, this carbene will be transferred to this one. And now you have a nitroso group, and this undergoes a intramolecular cyclizations leading to a indazole ring. Basically, this should lead to the formation of a NN bond formation. However, when we employed actually this azide, the reaction didn't proceed. It gave exclusively the product that leads from the intramolecular cyclization. Next, actually, we have asked actually what happens if I use the other nitrogen transfer agents such as anthranil. So in this case, the reaction proceeded smoothly, and here you can see actually the nitrogen transfer happens. Then actually, this is what initially we expected. It should lead to a indazole oxide. But what happens is in the same part, actually, this NO bond seems to be reduced, and actually, finally, we got up with a NRL indazoles with a net formation of a 1 CO, 1 CN, and 1 NN bond formation. Anyway, when you want to submit any publication for the journal, actually, it's not only the methodology to get a product, but at the same time, actually, you also need to show that actually these products are synthetically useful. In that context, since it has a aldehyde and a ketone group, we thought actually we can selectively functionalize the aldehyde. And when we tried to make actually a hydrazone from this aldehyde, what we found is it's not the formation of hydrogen, but actually it leads to a head-to-head coupling of these carbon-carbon bonds, leading to a fusion of a pyridine ring. So when you use hydrazone, at the same time, actually, you also have a azo group at substitute at this position. And when you use actually hydrazine, you simply get the coupling of this McMurray-like coupling of these carbonyls. So next, once we know that actually we can trap this carbene with the anthranil, then we proceeded to trap the same with the benzoxazole. So where actually you have initially you will get this carbene, and actually the carbene will be transferred to this nitrogen, then actually you'll be getting a phenomethod like this, and this undergoes a intramolecular michelation leading to a quinazoline N oxide, and this is very general. And once we have success with this thing, actually we are, as I told you, actually a French group has developed this reaction, okay. which involves actually the formation of this alpha immunocarbene. This can be trapped with a allylic alcohol, which undergoes actually a 3+2, leading to the pseudoendoxyl. So we asked actually whether we can trap these carbenes with both the nitrogen transfer agents. So in case of this anthranyl, what we can expect is the formation of formation of a indole having a C2 immunosubstitution. If the reaction proceeds with the initial intramolecular nitrogen transfer followed by intermolecular carbene transfer. But however, if it proceeds with a initial intermolecular nitrogen transfer, it leads to a immunocarbene, and then you have a chance for the carbene transfer, but at the same time, actually, it also leads to the same product. So here, actually, we cannot distinguish whether the nitrogen transfer is happening intra or intermolecularly, but when you take benzoxazole, here actually, when it happens intramolecularly, it leads to a C2 spiroindoline, but whereas actually the same reaction, if it proceeds via intermolecular nitrogen transfer, here you can see first initially it forms a quinomethyde like this, and this quinomethyde undergoes a nitrogen insertion, then aromatization, giving a C2 aryl quinazolone derivatives. So in most of the cases, this whatever the reaction seems to be initially intermolecular nitrogen transfer, followed by aromatization, but we have some substrates where actually we have seen that actually this a competitive intramolecular nitrogen transfer, especially when these benzoxazoles are substituted with electron withdrawing groups like fluorine, trifluoromethyl, or chloride. In these cases, it seems the initial NO bond breakage seems to be not as facile as the intramolecular nitrogen transfer. And following this, actually, we have also employed another substrate, which is a homologated alkynone, and in this case, actually, the intramolecular nitrogen transfer with anthranyl should lead to a alpha immunogold carbene like this, and actually this should undergo a intramolecular Friedel-Crafts alkylation leading to a indole derivative. But whereas actually the same thing actually when intermolecular nitrogen transfer happens, you have the initial formation of this carbene, and this carbene should undergo a trapping with this anthranyl, and this is what actually we expected. But what happens is this anthranyl actually undergoes a 6-pi electrocyclization, because you have from this side you have to see, leading to a formation of this tetracyclic system. And the same reaction when we did with the benzoxazole, in this case, here you can see actually the intramolecular nitrogen transfer followed by intermolecular leads to a this oxazole fused quinoline, but whereas actually the intermolecular nitrogen transfer followed by a intramolecular carbene transfer leads to a indole derivative, which we expected to undergo a 6-pi cyclization to lead to a tricyclic system. But anyway, in most of the cases, it was the intramolecular nitrogen transfer that was facile. With this, I would like to conclude my presentation. We started this, whatever the nitroalkyne cycloisomerization, in the context of developing a methodology that comprises of a formation of estrogen followed by addition of indoles to address the scaffolds present in the pseudoendoxyl class of natural products. Then actually, we have asked some simple questions like actually what happens to this carbene and how we can trap this carbene with other nucleophiles, such as whatever you can see here, three simple alkynes and 2 simple nitrogen transferase. We can synthesize actually a complex polyheterocyclic scaffold, which you cannot imagine actually how you can synthesize these compounds in one step. With this, I would like to once again thank the organizers, and also thank all the students who have worked in this project, and CSIR, DST, DBT for funding, and thank you all for your kind attention. Thank you. If you have any questions, I will be very happy to answer.
Professor Ramana, very interesting result. I was just thinking, what's special in these benzoxazoles or related derivatives? As you mentioned, that agide did not work. In that case,
yeah.
What's special here? And azide should be more nucleophilic. I mean, it should strongly bind with the gold, and then transfer should be easier from
So maybe the
common
NO
thinking.
bond cleavage is easier than the NN bond.
Okay.
Because if you see the dipole moment, obviously NO has.
Okay. Is that a possibility that NO bond cleaved already before binding?
No. No.
Okay, so you never isolated any benzylamine with...
At room temperature, azide is there.
Okay, so only with that particular gold it's happening.
So because we are doing the room reaction at room temperature.
Okay, fine. Thank you. Thank you so much.
So now I'm happy to introduce another person, Professor P. Anbarasan from IIT Madras, Chennai. I'm happy to introduce because he is a proud alumni of Madurai Kamaraj University, and he has completed his MSc in School of Chemistry, Madurai Kamaraj University. After his PhD, he moved to IISc Bangalore for his PhD, and then he received very prestigious Alexander von Humboldt Fellow Award, and he went to Germany for that. And then later, he also moved to University of Berkeley, USA. In the year 2011 only, he joined at IITM. So now I invite Professor Anbarasan to deliver a lecture on stereodivergent functionalization of C-H bonds with cyclopropenes. Thank you.
Okay. It does work for me. Very good afternoon. Let me start with thanking. Is it okay? You want me to hear? Okay, fine. Good. So thanks to Shiva, Suresh, and my alma mater for inviting me back here to give a presentation on some of our recent chemistry. So today's presentation, this major is going to be on CH bond functionalization with the cyclopropene. Thanks to Suresh for introducing a cyclopropene already in his presentation. In this, I'm going to show you a journey of how we started and to moving towards when stereoselective synthesis, where we started and where we are now. There are two important things which I thought I would probably highlight before getting into my presentation are the symmetry and the asymmetry. Right? Symmetry, when all of us look at a structure, we would like to see some kind of symmetry, even like flowers, petals. You try to see some symmetry which is beautiful, right? It attracts your attention. But asymmetry may not really gain in such attention. However, there could be very interesting phenomena behind that, or consequence which comes out of that could be very interesting. In chemistry, it has also a major impact. And particularly when you think about in catalysis, when you think about designing a ligands or a catalyst to perform a particular transformation, the symmetry can certainly play a major role. For example, there are two systems which I showed here, one which has a symmetry, the C2 symmetry, and one which doesn't have. So when the one which doesn't have an actual symmetry of this type, of course, one can have multiple type of symmetries, but I'm just using a C2 symmetry in this particular case. One could potentially see that here and all four sides are pretty much open, or some of them may be preferred, some of them may not be preferred, but then potentially you have an anisotropic approaches or phases open to you, then you tend to get a mixture of, or selectivity probably not really good. And in the other case, you have two of them basically equal, and one prefers, for example, right? So the number of possibilities in the process you are trying to reduce in the process, and can potentially give you an relatively high selectivity. In this particular case, what I'm going to talk to you are pretty much on an enhanced selective transformations, right? But as I told you, an asymmetry, it may not be as aesthetic or something which you like and to see, but the consequence, as you see, that this enantiomers, for example, and interacting with an pyrodarkets could be very different. It could be either really supportive, could extract in something what you want, or it could be really detrimental. So this kind of drives us to kind of design some interesting things. Of course, some of this ligand which potentially used in coupling this symmetry aspect in making an enhancer selective transformations I have listed here. With this brief introduction of what we think of using these two concepts, this is what which I'm going to say. I'll tell you and what generally we do at our department, my lab. There are various things which we focus on, mainly on diisochemistry, either in the form of generating pure diiso compounds, or from an diiso surrogates, what we call it, right, as triazoles or cyclopropene, which today I'm going to talk about. And also we do an functionalization of an alkenes of this type, as well as a very selected, of course, we don't jump into the version of CH, but we pick what we prefer and try to do in that particular transformation, and few other things also we do. So today pretty much I'm going to give you one example on this chemistry, how we put together and made an enhancer selective transformation, and then one more example in this. These are two cases which I'm going to discuss to you today, right? So when I say a carbene and metal bound carbene specifically, when I start with, I'm not going to a free carbene. So based on the substitution which is attached to a metal bound carbene, one could differentiate them in any of these ways, and their reactivity and selectivity is highly depends on, of course, the metal has a role, but also has an impact with respect to substitution which are attached to those. And these are generally, we make it from a corresponding diiso compound. So this is a very elegant precursor. One can prepare, you can convert that into in situ, generate the metal carbene, and then perform various transformations. And these are some of these traditional transformation one could think about of insertion reaction, cyclopropenation, and what Professor Jerome is here. So we make an ELIX and try to do many other functionalization with an ELIX as well. So that's something which we gain in more attention at over a period of time. So I'll show you. So when you say ELIX as well, traditionally you can do based on the substitution what is present on the heteroatom, the Lewis basic side, one can think of a very space cyclic reactions as well. But then instead of a typical diiso compounds, as I showed you here, one can also think of a diiso precursors. There are various ones. And what we are interested in is, as I said, and sulfonyl triazoles, which because it's easy to synthesize. And other ones, which is, there are many other things. There are non-diiso precursors who can easily generate the carbenes, metal carbenes still in the systems. And one such a case, which I'm going to show you today, is from these ones. So these are the things which I'm going to pick and give you some examples around that. Okay, so as I said, the N-sulfonyl 1,2,3 triazoles, it's interesting because first thing is it's easy to synthesize. You just do an acid alkyne cycloaddition reaction to get, is reasonably stable. And when you put them with a metal catalyst, what you can generate in situ is an metal carbonides. So here, what you need is a Lewis base and Lewis acidity of a metal catalyst is pretty much is essential to drive this reaction. This is stable, but then you need to have a Lewis basis, Lewis acid, the catalyst is right choice is important to drive it. So what fits at this point in this chemistry is an rhodium 2 species, the rhodium carboxylate complexes. It does this chemistry to generate. What is unique in this particular metal carbenes are compared to a traditional diiso compound derived from like diisoketones, for example, diisoesters, for example, there is oxygen versus nitrogen. One can think about doing a very different reaction. One can think about incorporating this nitrogen as well. So based on the coupling partner, the choice of your reagents, one can think of building a new structures. So one is like I'm sorry, okay. So this is, one can think of direct only the carbon-carbon reacts, or you can think of both the carbon of this particular system be a part of your ring or part of the systems, or one can think of all 3 atoms getting involved. So That means what you need is you need a skill to choose the right coupling partner. You can diversify your reactions, may not be in a single steps at times, but you can do it in one part to kind of get to this unique pattern, so you can do that. So with that, with this, we have made lots of new molecules we have synthesized, but of course our aim is not just making a molecule, our aim is making a strategy, a designing and strategy, controlling and selectivity. These are the main key for us, right? So many things which we have showed. One of them I wish to highlight is about these tryptamine derivatives, which we synthesized through an insertion of this triazole moiety onto this third position of an indole, which is nucleophilic, obviously, right? So carbene, metal carbene is an electrophilic. You add a nucleophile, it's an addition followed by deprotonation, what you see. It happens. So this, for subsequent hydrogenation, one can get this. So what we were thinking at that point is, what happens if we put on some substitution, which could be even a Michael acceptor, for example, and then if you can perform a reaction, one can get even a chiral center over there. And that's what we were looking at, right? So if we can have a Michael acceptor over there at the C2 position, will the same chemistry occurs? Yes, although it is not as electron rich as an indole when you say an alkylated indole, but still this chemistry occurs. One could get this. One could get this, and then followed by the beauty was that we need to use a base to cyclize. That was an advantage for us, right? Is otherwise it just gets cyclized, you will not be able to induce a chirality at this particular center, right? It doesn't happen. So we use this. Why this doesn't work? So we use the base instead of base. We did of course, I'm not showing a whole detailed stories. We use a squaramide derivative as a hydrogen bonding catalyst to induce a chirality. And that reaction seems to work extremely well. This is of course, I'm not going to details of how we optimized and all that. This is the best systems what we found with an almost like 95:5 enantiomeric ratio and 87% yield. So the next thing was, can I put this in together in one part? That was the next step that we did see that we can make an initial Rhodium chemistry, insert at this particular C3 position, and followed by add this same part, right? Same solvent. This is actually we optimized in the same solvent. So we could just add this catalyst further, so no interferences, and we still get and quite good. And of course, there is no loss in the inertial selectivity. However, the loss of the yield is expected because you are forming a more than one bond, right? So if you consider and each bond formation is close to an 80, still you see that you will get to close to 60% yield of your two step reactions. Right, we kind of conformed and we proposed, I'm not going into details, just based on our crystal structure and the configuration what we had. I'm sorry, what we had. So we kind of proposed then how possibly the squaramide helps in activating your carbonyl and which phase this nucleophile comes in and adds in Michael fashion to the product. Okay, this is one aspect which I want to show you. The next one is traditionally, of course, there are, all of us know this CH bond functionalization. Of course, there is no detailed, elaborate introduction is required, but this is how we have been doing it for quite some time. And the recent strategy has been that can you take a simply and readily available hydrocarbon and take one of the CH selectively, could be an alk and of the chemo regios, selectively, and can put this molecule directly. So you can you functionalize it, right? So there are lots of metal catalysts known today to this two transmission. But what we are interested in is in group 9 metals, which is a cobalt, a rhodium, and iridium. And they tend to have a very common structural feature with respect to catalyst, which has an cyclopentadiene anion as a ligand and bound to a metal, which is a group 9 metal. And most of the time, this is an metal at the 3 oxidation state. So there are a lot of chemistry people have done with those. One can do many of these reactions, what I listed. I'm not going to detail that. But if you want to introduce a chirality into this is a catalyst available. But of course, many of these reactions would give you a product, structures. It could be within any kind of type of chirality. But if you want to introduce a chirality, there are a couple of options available. The first option is, and our ready option is, you can replace this X within some chiral ligand. Of course, you cannot replace both of them. That's going to be deadly because you don't have any site to further reaction. So that means you have to have an monodentate chiral ligand to drive this reaction. That's one particular option. So there you can have either a phosphorus base, nitrogen base, and mostly what is studied today is a carboxylic acid based thing. I'll also tell you in the next slide what is the limitation also. The second type is about instead of touching those an X type ligands, what is already there in the metal, can you functionalize a CP, right? Introduce a chirality in a CP, planar chiral molecule, and then use that chirality, keeping this all the and remaining vacant sites available, and try to do a functionalization. These are two options. As I said, the challenge with respect to the first type is the moment you have a ligand which is chiral, right? It's almost like blocks your coordination site. So if you go to group 9 with the CP star, you have only 3 vacant sites available for your further reaction, and you have a 1 which is a kind of chiral ligand which is blocked. That means only you have 2 sites. And most of our CH bond functionalization, you need to put a substrate to the catalyst, you have a directing group. That means that takes in 1 more site. That means 2 sites are already blocked. You have only 1 more to have a further reaction happening. That means the limitation for this kind of reactions are that you have to have a substrate or a chiral induction supposed to occur at the stage of a CH bond functionalization. It cannot happen afterwards. So that's one limitation when you do this transformation. That means, what does this mean? It means you can only perform a desymmetrization reactions. Nothing more than nothing less. Okay, you cannot just like take on any prokaryote systems and you cannot introduce any chirality. But if you choose another one, the second type, with respect to an chiral CP, you have all 3 vacant sites. You can do an all kind of type of reactions, including in desymmetrization. One can think of reactions, you can try to perform those. Of course, we are not the first players here. So there are many people who have worked. Professor Nicola Kramer, they are the one who kind of ventured on this, making, of course, there's a challenge with respect to synthesis. I'll come back to that. But if you look at the literature, the history is not now. This is even that what Kramer has used was synthesized by Helterman in 1989, where the binary backbone having a CP was synthesized, basically, right? So there are a lot of CP derivatives or chiral CP derivatives were known before. Okay, so as I said, like in 2013, Kramer has built this, and 2016, IU has used this instead of binary, a spinal derivatives was built. Okay. So what is the advantage of this? In addition to what I mean, right? Basically, you have an CP, which is a chiral planar molecule. You have a one-side backbone. We can have different substitutions. And based on this chiral backbone, of course, that's the one which is induce a chirality for you. And then this R group, which is going to project in your system, this is kind of this is an C2 type, right? So you will have an extended chirality one can think about, right? So you induce an extended chirality towards a metal complex as is possible. And introducing substitution on the CP is important because it gives you a better stability for your complexes. I'll give you an examples as well in my presentation. Of course, you can also have an addition chelation site. So there are a lot more possibilities in this particular scenario. And then you see that this is the model what was proposed by Professor Kramer, and then one can think of Fisian and Cuban type structure, and then see that only 2 phases are open for you, and that one blocks by a substrate, and the other incoming substrate is kind of driven only in one particular direction to give you a very high selectivity. These are stories. There are a lot of reactions people have done. What we looked at was initially an cyclopropene. I hope I have some 10 minutes or 5 minutes. Okay. So this reaction which we did some time back, and then when you look at it, most of the time an allylation reaction, these are the reagents what you have used: allylic acetate, allylic carbonate, allylic alcohols, and then all activated systems people have used. But then what you see here is that if you want to introduce a substitution at this benzylic position, for example, or when you want to have a multiple substitution on the olefin, generally this chemistry do not work. The reason, you generate a carbon metal bond. The first step of this reaction, allylation reaction, is that the alkene gets inserted to this carbon metal bond. Right. So when you have a more substitution, this hinders. So that's why most of the allylation, quote unquote, if you look at it, it will be a very simple allyl substitution, not a substitutor one. So we wanted to address that. Can we do this? So we thought, like, why can't we use the carbines? Right, the metal carbines. Can you generate on something which can, because insertion reactions are rather known. So can you generate some carbene which will introduce an allyl moiety in this particular manner? So that we thought is to use an cyclopropene. in addition to simple addition reaction, what Professor Suresh has mentioned, we can also use the metals to ring open these to make a vinyl carbon. This is also known. People have made a mercury carbon complex out of that and then even characterized that. Okay, so this is very strange system, very beautiful. One can do a lot of reactions. People have used this, but not for an allylation reaction. I'm not going in detail here because lack of time. I'll just quickly browse it. So we have done this allylation with the cobalt catalyst initially, and you see that we can even we can even introduce a substitution over there, which is not in general is practically possible. So based on a cyclopropene substitution on the cyclopropene, you can selectively introduce a substitution at the allylic position of your choice. Of course, the challenge is a synthesis of cyclopropene. So we have showed some application. We did even a study and mechanism to understand how this chemistry occurs, whether really a cobalt involves in a CH bond functionalization followed by a reaction. Yes, it does do. You see that CP is getting trapped in this particular case, and we did a milder reaction to identify this possible species, and then of course, and we went on further to test the reactions. Okay, this is a mechanism. I'm not going in detail. I'll just bring your attention to this two particular species, which is an E and E dash, where it's an eta 1 and eta 3 species. Right? So this pyridine is not something which will undergo a reductive elimination, will not undergo a cyclation onto an allylic species. But if one can have a directing group which undergoes such a cyclization, one can induce a chirality as well as a new ring systems could be built. Right? So that is an interest, so which is possibly can bring a new structures. What we were interested in that particular case was the phthalate derivatives. There are a lot of phthalates which are quite interesting and important as well. Right? So we want to do it for benzoic acid. Yes, we did an initially reaction with the CP star rhodium chemistry. The reaction does work at 45 degrees Celsius pretty much. Right? Very for Chennai is pretty close to a room temperature. So it does work and gives you a good yield. What is beauty is that you have a chiral generator created here. Can we make an NHA pure system of this? So initially our aim was to not to jump onto what Kramer has done. We want to parallelly build an kind of pillar. And can we have a little more an elaboration of this particular field? So for that we started with an phenol as a backbone, and we started synthesizing these CP derivatives. So of course we have to make an phenol. It's not really commercially available. One has to make it, resolve it, and then do a sequence of reactions to get this particular spiro compound. I long pressed, I can't. Okay, so spiro compound, right? So then you can do an 1,5 sigma-tropic carbon shift under a very high temperature. You get an CP derivative with an, of course, this double bond means that you have a mixture of CPs basically, and you do an react that with an rhodium, you get a metal complex. The shock comes here. We use this catalyst to perform a reaction. The reaction itself doesn't work. Probably it's too bulky that the substitution which is over here, then RL might is probably not really helping out. So the reaction was not itself even happening. So by that time it was 3 years for the students. So we have to go back to an Kramer's catalyst, and then we made a series of them to start with. 5 of them we have made to test those chemistry, and we did that. Yes. The first rhodium one with the methoxy and the chloro, we were able to see, and at least I could isolate it and then characterize the compound and see an enantiomeric ratio, which is 60-40. And then we moved on to an optimization. So here I'd like to show you a few, is that when you come to a rhodium 5, which is because our aim is to, our aim is to make both the selectivity, which is the inertial selectivity, as well as the reactivity. You want to have a higher yield of your product. So you have to have this balance. So you need to control both of them, right? Quickly. So what we saw was that with a tertiary butyl catalyst, you had a 85-15. With this, beyond that, we were not able to move. And there's a second problem is this catalyst I have to use close to 8 mole%. The stability of the catalyst and reaction conditions were not good. Okay. So then we decided to put a substitution on the CP. And we have made a few more of them. And what we realized was the moment we put an isopropyl, it was a shock. It gave a 50-50. Luckily, we had another catalyst also to screen, and then we got to and now it is not a mistake. It is written at 12:88. It's because we are getting an other enantiomer with the same chiral backbone. no change in the chiral backbone, but we get an other enantiomer. So we further structurally modified this tertiary butyl by putting 2 of the methyl groups to one as a cyclohexyl, so that you have a little more conformationally frozen structure. So there you get an almost like a 5:95 ratio, and then you can eventually get, this is of course when you put on further bulky substitution is not going good, and this is best. Okay, so just to summarize, what we see is just having the same chiral backbone and change the substitutions on the CP, I can switch from one enantiomer to another enantiomer. That's the beauty which it gets through. Okay, I'm just quickly finishing it off. This is to prove that first is a racemic, one is in one enantiomer, other is another enantiomer. I'm not going here. I'll quickly go here, as this is a place what we believe is an chiral induction occurs. So we propose a model based on which, because this is a catalyst structure, this is based on which, like where you can have either the approach of a carbene, which thanks to again Professor Jerome, we found that in a DFT they show that this is pretty much in perpendicular to your CP. If so, then whether the carbon is close to your up or down, which is possibly, we think that, we strongly believe that that has an impact. And when you have a longer or large steric, it doesn't favor, and the other one is favored. When you go to another one, when you have substitutions, where you have now this probably, it's a relative, right? It's a balance which you make, which is where you are looking at. So on the other case, the one which is here, the bottom one seems to occur and give us a product. So I'm not going to take you to this, because this is even more interesting. Not only just an enantiomer diversity, we also get a chemodiversity. In addition to getting in one product in 2 enantiomers, we also get 2 different products, just by a different catalyst. Okay, so probably with more details next time, when time permits, I'll give you more information. And all this work of the second part with the CP was completely done by Mr. Bakiraj, one person for last 4.5 years. And remaining, of course, there are carbon chemistry were supported by other people. And of course, a lot of funding who has been helping us for performing such a challenging ones. And thanks to all of them, and thanks to all of my students, and thank you all for your kind attention. I'll be very happy to answer any questions.
Thank you so much for the wonderful
Sorry
lecture.
if I have taken a little more time.
This lecture is open for questions.
Yes, man.
Part bulky, just using an additional Lewis acid, if it's possible.
Wait, your part.
If you go to the last slide, I mean this, the explanation before that, I think. Previous one.
Yeah.
You said that this one, right side one, I completely understand. You can play there, I can make the catalyst bulky. Left hand side is basically the R and the oxygen, right?
Yes.
If you put in Lewis acid, BF3, etherate, I don't know, whatever, to make that part more bulky, can you get more, boost the enhancer selectivity?
But these cases, of course, it's not going to really that way, right? See, when you add a Lewis acid, what happens? Then your reaction will not itself happen. Because you have rhodium 3, which is itself a Lewis acid, to get this reaction happen. You add a strong Lewis acid like a BF3, you are done. You are killing your system, period.
Or something else, I don't know. I mean, they have to be balanced. I mean, co-catalyst.
We need.
Co-catalyst.
Absolutely, we need, but not at the, I mean, what could try, but we have not done it. But what I strongly believe is that this is a reasonably softer acid than a Lewis acid than an rest, which you think. So if that's the case, I would not prefer to add them. Rather, I try to modify a structures reasonably to get a better thing.
No, but this switching is amazing. I mean,
Yes.
Thanks.
Any other questions? Okay, now I invite Dr. S. Sureshkumar to honor our guest speaker with a small memento as a token of appreciation. Yeah.
Thank you, Master. Thank you.
Thank you.
Thank you. So the next talk is going to be delivered by Professor Yelumalai from Pondicherry University. And I personally feel so happy to share small information that myself and Professor Yelumalai and Dr. Sureshkumar, we all started our professional career at this university in the same day as an assistant professor. Interim, he just moved to Pondicherry University as an associate, and now he has become a professor. And he is really doing excellent over there. And he is a PhD scholar from Indian Institute of Science, Bangalore. After his PhD, he received JSPS fellowship and he did his postdoctoral research for almost 6 years in Japan. And meantime, he received very prestigious award, which is nothing but Young Ceramist Award from the Japanese Society of Ceramics. Okay, yeah, and he's really doing good at Pondicherry, and he's specifically working in green energy technology. So now I invite Professor Yelmalai to deliver a lecture.
Thank you, Professor Ashok, for your elaborate note, and it is very great to meet you after a long time. And also at the outset, I would like to thank the organizers, in particular Dr. Sureshkumar, Dr. Suresh. And it is also a great occasion to meet the eminent professors, my teachers, faculties, Professor S.N. sir, and from the own department, Professor Natarajan sir, and our another eminent professor, Professor Ramaraj sir. And this is also a good occasion to meet many of our friends, academic friends. And I think we are meeting several of us after a long time. Without dwelling on any other thing, let me take you to the topic that you are seeing on the screen. So I will be sharing with you on recent developments on electrode materials for post-lithium-ion battery. It is a little mistyped in the schedule. It's not potassium-ion battery. It is post-lithium-ion battery. What I mean is beyond lithium-ion batteries. We need to improve the capacity and the energy density of the batteries. I'm sure all of us carry at least one battery. Many of you may be carrying more than one battery. One may be in a smartphone, another may be in your smartwatches. Maybe some students, enthusiastic students, they may be carrying more than 2 batteries also. This talks about the maturity of the battery technology that has gone into, in particular, lithium-ion batteries. So for simplicity, I will restrict the development that has been made in Pondicherry University in our laboratory. And wherever required, I will be comparing it with the literature one. So our group in Pondicherry concentrates on 4 aspects of electrochemical technologies. And we dwell in electrode materials, both into cathodes and anodes of various battery chemistries, lithium battery, beyond lithium batteries like lithium-ion, lithium sulfur, sodium system. And we also engaged in material development, the sister device called supercapacitors and supercapacities. And we also make progress in these aspects. So today's lecture mostly will concentrate on batteries beyond the lithium-ion batteries. So this image you would have seen, many of you would have seen, it's available in the open literature. And this shows the evolution of mobile phone technologies. I was a student maybe 20 years before in Bangalore, and we hardly had pages. I remember Professor S.N. sir used to have pages, and now we have smartphone of unlimited talk time. We have smartphone of unlimited or the required display size. This has made possible because of the improved battery technology. In particular, the capacity and the energy density of the battery has been so much improved that we could comfortably use such electronic gadgets. And believe it or not, so now it is penetrating into beyond mobile phones, beyond electronic gadgets. We are into grid storage, and we are also into electric vehicles. What are batteries? This is the simple textbook definition. It's an electrochemical device which converts the chemical energies available in the electrode materials into electrical energy. And with respect to batteries, as long as if it is a primary battery, it can store even 20 years, even beyond 30 years. So places like missiles, they use the primary batteries. Once you fabricate, it will hold the charge for 20 years to 30 years. Whereas secondary batteries such as alkaline secondary battery or lithium-ion battery, which we use in your smartphone, so they hardly hold charges for about a month or so. If you charge your smartphone and keep it as it is, and after 1 month, it is not possible to on. These are the 2 distinct characteristics of primary batteries and secondary batteries. And the simplest battery would be the Daniel cell, which uses a zinc rod immersed in a zinc solution and a copper rod immersed in a copper solution, and you sense a potential of about 1.1. Combination of any redox couple, if it develops a positive cell voltage, we call such cells as a galvanic cell. All galvanic cells, in principle, they can be a battery, whether they are primary or secondary. It depends on the kind of electrode reaction that is happening. So International Energy Agency, the global nation, they came up that so we are currently into this. So we are transitioning into from conventional vehicle to electric vehicle. As you see here, by 2040 or so, most of the vehicles transportation will be of electric in nature. It can be a battery operated electric vehicles or fuel cell operated electric vehicles. This requires upgradation of current lithium-ion battery. As we all know that current lithium-ion battery uses the theoretical capacity limited graphite as an anode, having a theoretical limited capacity of only 372 mAh, and lithium cobalt oxide and their combinations, we call them as NMC, NMCA, NCA, etc. So the current lithium-ion battery could be able to power maybe your smartphone, your smartwatches, or electronic devices, maybe a device like something like this. But so as EV is coming up and grid storage is being stressed, very good introduction is given by our Honorable Vice Chancellor of this university and Professor S.N. Sir, where the sustainability is being practiced or to be practiced. So to use renewable energy technologies and to integrate the current battery technology into electric vehicles, we need to upgrade the capacity of the batteries. So this is what the government of India has predicted. India has predicted that by 2030 or so, there is going to be a huge requirement for the battery technologies. So the young minds, youngsters, you have a lot of role to play in terms of battery chemistry, developing electrodes, electrolyte fabrication, and performance analysis. And you can see that as much as more than one order difference we are lacking. So this talks about the importance of battery technologies. So in near future, mostly for EV sector and as well as the grid renewable energy technology storages. Okay, so we have conventional lithium-ion battery uses intercalation chemistry where we have a shuttling of lithium-ion between the anode and the cathode, and it delivers a possible capacity as well as energy that you can able to use with your smartphone or laptop or camcorder. But when it is for electric vehicle or grid storage application, the capacity is limited, it has to be upgraded. And we have two prominent technology coming up, the alloying technology and the conversion technology. There are metals or materials such as tin, cobalt or such materials. When it is made to react with lithium, they can reversibly make alloys with lithium. And you can see that in very particularly, you can see that lithium silicon, it can give as high as 10,000 watt per gravimetric capacity. And in terms of theoretical gravimetric capacity, it can be close to 4,000. Believe me, this capacity is 10 times higher than the conventional graphite capacity. So it means that if such technology is fully developed, for a given mass of silicon, you will be able to store 10 times larger energy that we are currently storing with the conventional lithium-ion battery. So it means that, so if such battery is integrated into the electric vehicle, the electric vehicle would be able to charge in one charge. So if conventional lithium-ion is going to travel for 100 kilometers on one charge, and the silicon integrated lithium-ion battery will be able to travel on single charge on 1,000 kilometers. That's the greatness. So a lot of progress is being made. That's why the beyond lithium-ion battery or future lithium-ion battery will use not limited theoretical capacity based graphite as an anode, rather it is metal and metal oxide based anodes as a electrode material, and whose theoretical capacity is at least double or close to 10 times. That is why the research and development in alternative electrodes as well as the post lithium-ion battery or beyond lithium-ion battery is being stressed. So in our laboratory in Pondicherry University, in Department of Green Energy Technology, we explore simple metal complexation chemistry to make metal complexes and use these precursors as a starting material to generate various non-structured materials. So for example, various metal ions are made to react with organic ligands. I specifically take the more carbon-containing organic ligands so that after complexation and pyrolysis, I get a huge amount of carbon that will support for buffering as well as to facilitate the conduction. So a simple metal complexation chemistry is used, and one can also tune the morphology, composition, and surface nature so that we will be able to tune the electrochemical aspect of electrode materials. So keeping the mind that I need to get the high capacity or high energy density for the post lithium-ion batteries. So this is the graphical view of recent work that was done in Pondicherry University. We have extensively made use of silane ligand as a precursor to make a complex, And we have made cobalt and tin sulfide, cobalt phosphate, nickel. I'm not going to bore you with all the content. Maybe I will take you to one or two systems. So for simplicity, I will restrict how the material is prepared and what is its performances. The detailed analysis and all is already published, and one can look up if they are interested in that. So this work we have recently published, maybe 2017. So we made use of silane as a ligand, having a large number of carbon atoms, and made a complex with the cobalt salt, and it just precipitates. So those who are working on metal complex, you will appreciate me that it is already well established complexation technique. And this complex precursor was utilized, and it was pyrolyzed in a argon atmosphere at elevated temperature, and then you get a very homogeneous composite. So where Professor Natarajan also introduced metal organic frameworks, it's a kind of metal nanoparticles embedded in the matrix of carbon. So metals or metal oxides will be active react centers, and this carbon will act as a buffer and also to facilitate the conductivity. So all these characterization reveal that so the material prepared consists of cobalt and cobalt oxide on the matrix of carbon. Enormous amount of carbon, more of a graphenic nature or reduced graphenic nature is present. So in our laboratory, we have established a standard protocols to make the batteries. So we take any material to the level of prototype, at least TRL level 4, so that not only the proving the concept, we also make a prototype. So all my students are made to develop expertise to develop prototypes, and they also have to demonstrate by powering consumer electronics or running some small toys or something like that. Any material, any electrode material that they make. And this is the standard procedure that we employ for making the electrode as well as the battery. And complete setup, we have at least 50 channels at a time, 50 batteries at a time I can charge and discharge thanks to generous funding from SCRB, DST, and CSIR and other bodies. So what is the performance? This is the performance. Before we test the capacity of the electrode material that we intend to make, first and foremost is to look up whether it is electrochemically active, whether it can really make a halide with lithium reversibly or not. You can see that the appearance of these redox peaks confirms that cobalt and cobalt oxide can really make a reaction with lithium reversibly and deliver a capacity of 1000 mAh. And this is the typical charge-discharge profile. A first cycle capacity is 2000. As I told, theoretical capacity of graphite is only 372 mAh. Whereas now you get the capacity, practical capacity of non-carbon electrode as high as 1000, as high as 2000. So the stabilized capacity at a C/5 rate is 1000 mAh. So we have Kodandaraman, he will be able to appreciate this. So 1000 mAh as the theoretical practical capacity at a C/5 rate for a quite number of cycles. So it means that cobalt and cobalt oxide could be able to work as an alternative anode so that it could deliver the practical capacity of over 1000, which is 3 times higher than that of the conventional graphite. So when cobalt can make a complex with silane, so we have developed a range of metal ions. For example, in this case, tin and tin sulfide, we have used the similar ligand. And here, so after pyrolysis, we have also made hydrothermal treatment, post-hydrothermal treatment. Very fascinating nanomorphology we could be able to receive. And you can see that leaf-like morphology, these are all almost nano-sized thicknesses, and as introduced by Professor Natarajan sir in the beginning, so they have a very high surface area, and I expect that they should perform much better compared to the bulk materials. And for our information, this was recently selected by Drexel University, and they have every year competition, and we were one among the nanomorphology contributed to the nanohartography. And what is important is the capacity of the battery. And believe me, this is a full cell capacity. What do I mean by full cell capacity? We have a tin sulfide as an anode, not the conventional graphite or lithium as an anode. The tin and tin sulfide developed by this pyrolysis through the complexation, and the commercial lithium cobalt oxide as a cathode. And you see that over 200 hours, the cell voltage is non-zero. It means that tin and tin sulfide could really work as an alternative anode, making reversible halides and dealloying. And what is important is that practical capacity. So at a C rate of 0.2, so you get a close to 600 mAh as a practical capacity or discharge capacity. And believe me, this capacity is the highest single cell capacity for the lithium-ion battery. And a commercial lithium-ion single cell battery could be able to deliver only 260 mAh. And this is at least double with respect to so full cell capacity. One can get a very high capacity for a half cell, so which is of no practical use. But what is important is the full cell capacity, where you can really use tin and tin sulfide as a alternative anode in replacement of graphite, where you can reach double the full cell capacity for conventional beyond lithium-ion batteries. And it was demonstrated to power consumer electronic. A 2.7 voltage green LED was powered for more than 6 hours on single charging. So that is the prototype we have made. And so we have also made nickel in this regard, and nickel oxide embedded on the carbon matrix could also deliver a possible capacity of over 120 mAh for a reasonable cycle life. And so such work was recently highlighted by New Journal of Chemistry with their cover features. And cobalt phosphide is another interesting material. So we have used this for beyond post-lithium-ion batteries. So as we all know that Government of India is now focusing more on sodium system, because around India we have a lot of sodium deposits. We have a huge amount of sodium seashore and sodium deposits, unlike the scarcity lithium system. So more attention is these days given by Government of India to develop sodium-ion battery, mostly for not vehicular application, for grid storage or renewable green energy technology storage applications. So the only difference is, so we have at least 24% larger sodium ion. This gives you a good room or enough room to have a high power density compared to the conventional lithium-ion battery. So since lithium being tiny, having a large ionic solvation radius, it is difficult to move. So when it is applied for a battery application, we will be having a limited power density, whereas sodium having a larger and solvation radius in comparison with lithium is less, and so we have a better mobility. Maybe I can continue. So we will be having a better mobility for sodium compared to the lithium. That's why much attention is also given very recently for this sodium-ion battery. And we have explored this cobalt phosphide as an electrode for sodium-ion battery. At a 0.1 C rate, you get a full cell capacity of close to 300 mAh. And this is quite good compared to the conventional disordered carbon-based sodium-ion system. And zinc is thought to be a poor electrochemical material for a long time. And so to our surprise, we have employed this material as an electrode material for sodium-ion battery. And you can see that so a slab of nanostructured slab of zinc oxide embedded in the carbon matrix has been developed by a simple complexation followed by pyrolysis method. And after material verification, you can see that a capacity of 600 mAh. So zinc is known to be a poor material, but now we can see that at least some deliverable capacity one can get even for the zinc oxide. And in the same way, so I mean, we have verified by thorough analysis, post-mortem analysis, and it makes alloys with the zinc and conversion and reconversion, all those things have been verified. And in this line, we have also very recently employed this technique, a versatile technique to ready-to-use electrodes called electrode spinning method. You can readily print or readily make a nanofibers of any material, mostly metals and metal oxides and metal chalcogenides, and you don't need to have a much post-treatment. You can readily use as an electrode material. To our surprise, when we used manganese selenide as an electrode material for the sodium-ion battery, you get a capacity of over 600 mAh. You see that, so far we have been talking about the conventional lithium-ion battery with a full cell capacity of 260. Now with the beyond lithium-ion battery chemistry with respect to sodium-ion, you have a full capacity of 600 mAh, and it is highly stable with a different C rate. And so those who are working on battery, you will appreciate that it is a robust battery power density one can get, and the stability of the electrode also quite good, and Coulombic efficiency is almost invariable for the 100 cycles established. for the very, so only very few groups have identified what is the mechanism for such a high capacity storage. And so we have employed a technique using cyclic voltammetry to quantify whether the sodium ion storage is only by conversion or alloying mechanism or also by electric double layer formation. And you can see that significant portion of the charge storage with respect to sodium storage is facilitated by the double layer capacitance. So having a double layer capacitance in addition to the redox capacity is very important because the resultant battery is going to deliver high power density, which is demanding aspect for the electric traction. So in this line, so we have also recently making progress on metal hair battery. So whether it is a lithium ion battery or a sodium ion battery or any other battery system, so they all use mass bearing electrodes. For example, in case of conventional lithium ion battery, we have a element lithium 6.9 gram or carbon 12 gram per atomic AMU, and lithium cobalt oxide at least 97 gram. Put together, you have 100 milligrams in a cell. So whether it is possible to use oxygen or air, atmospheric air as an active material, and to this surprise, thanks to John K.M. Habraham and John, in 1967, they have came up with a metal tarnishing chemistry. So to develop a new battery chemistry, and they are metal air batteries. The atmospheric oxygen or air can be used as an active material. In particular, so reactive metals such as lithium, sodium, aluminum, iron or zinc, when it is made to combine with oxygen, these reactive metals undergo tarnishing, producing their cations and releasing electrons. If we can effectively separate, like in PN junction, how we effectively separate using a suitable separator and other things, we will be able to rip very high energy density. With respect to lithium oxygen, you can see that excluding oxygen, you will be able to get the theoretical energy density of 11,000 or close to 11,200. And this is almost equal to the capacity or the energy that you get from 1 liter of gasoline. So it means that a lot of potential or avenues are there to develop a range of metal oxygen batteries. And plenty of oxygen is available, 21 volume percentage of oxygen available in the atmosphere. You don't need to carry in the barrel, and you can let open in one of the sides. So the cathode side of the oxygen should be let open. But the problem with lithium air battery is the sluggish kinetics of oxygen reduction reaction and oxygen evolution reaction, which are taking place during discharging and charging of the lithium ion battery. So we need to upgrade or update the rate or velocity of these two reactions. So in this regard, we have developed several potential ORR and OER catalysts, and you can see that. So we have gradually improved their performances from moving from porous carbon to and carbon matrix embedded with the selective catalyst towards catalyzing ORR and OER. And this is one such material. So where we have made like a cauliflower-like morphology by a simple combustion method developed by Professor Patil sir in IPC in Bangalore. And you can see that this material delivered very high catalytic activity towards oxygen reduction reaction in oxygen atmosphere. And how do we confirm? So you confirm it with the inert atmosphere. In organic atmosphere, there are insignificant peak, and in the case of oxygen, we have a significant current density. And elaborate study on the RRD data confirms that the oxygen reduction on these catalysts undergoes 4 electron transfer reaction, which is preferred reaction for the metal oxygen battery to perform well. And so if it is going through the 2 electron transfer, so peroxide intermediate will be forming. This will reduce the cell voltage, and also the catalytic rate of the reaction will be slowed. And so we have quantified whether some amount of peroxide is forming or not on any of these catalysts developed. To our surprise, almost insignificant amount of peroxide is being developed. So meaning that it's selected towards the 4 electron transfer. So this is half cell data. What is important is the full cell data. This is the components of air battery, air coin cell, and a prototype TRL level with TRL level 4 we are making. And and this is the capacity of lithium air battery. So lithium as an anode and oxygen as a cathode and embedded with the catalyst. And what is the discharge capacity? At a current density of 50 milliampere or per gram current density, you get 3700 mAh. Much better than the graphite based lithium ion battery. 10 times higher, as I told in the beginning. So 10 times higher capacity. If this such battery is developed, in fact, Elon Musk's Tesla program is concentrating on developing electric vehicle along with IBM, they are not going, they intend to use not the conventional lithium-ion battery, they are going to use this lithium-ion battery, lithium-air battery, because lithium-air battery theoretically has a 10 times larger capacity. Only problem here is the sluggish nature of oxygen reduction reaction, oxygen evolution reaction. If that rate is taken care, elevated, we will be able to get for a given mass 10 times higher capacity. So instead of 100 kilometers, using the lithium-air battery, you will be able to travel 1,000 kilometers on single charge. And so we have also made a cobalt analog in this regard. And so we have 2 LEDs, 5 LEDs were glown using 2 prototype lithium-air battery systems. And I think we went for patent. And here the capacity is little elevated, 4,000 mAh. You can see that we need to have a catalyst. And these cobalt and cobalt ferrite acts as a reaction center on the carbon matrix to absorb more oxygen and dissolution. And after dissolution, it has to facilitate for the charge transfer reaction, which I told ORR and OER. And such a fine work also was covered in a cover article of Chem Electrochem recently. We thank the editor for generously accepting, so freely covering the articles. And so we have also made recent progress on different materials. And I think the next slide is very important. So we have a porous carbon matrix as a OR cathode or catalyst. And then we do possible capacity of 1,600 from 1,000 mAh to 1,600 mAh. Now when we integrate with the metal oxides and perovskite oxides, we could increase the capacity from less than 1,000 mAh to 6,000 mAh with the lanthanum manganese oxide embedded in the carbon matrix. 6 times increase in the capacity. It's as good as you could be able to travel 6 times larger longevity if it is integrated to such a electric vehicle, or if it is integrated to your smartphone. You charge today, maybe so if a conventional lithium-ion battery works for about 10 hours, you will be able to, this lithium-air battery will be able to provide energy for 60 days. That's what it means. So this is the prototype we have made, and all these devices are at least TRL level, at least 4. It means that it is ready to take up the next evolution, commercial level. So these are all almost a commercial type of lithium pouch cell that we use in our smartphone. Okay, so this was also recently highlighted. So, okay, when oxygen can work as an electrode, why not oxygen being on the same family? Okay, so being a sulfur in the solid state. So we are also making a progress on metal sulfur battery. So in this case, we will have an elemental lithium as an anode, similar to the case with the lithium oxygen battery, and elemental sulfur as a cathode material with a suitable electrolyte. And what are the merits you will have? You are going to lose only few little less voltage compared to the conventional lithium-ion battery. Sulfur being abundance compared to oxygen, oxygen is so difficult to catalyze. OR and OER difficult to catalyze. You need to have a selective catalyst. Whereas in the case of sulfur, you have abundance, non-toxic, and plenty of sulfur is available globally. And so we can use elemental sulfur as a cathode material and lithium as an anode material. The problem here in sulfur is the polysulfide dissolution. So when the sulfur reacts with the lithium, or vice versa, lithium reacts with the sulfur. So elemental sulfur is present in S8 and it is in the ring structure, and ring is open and it forms Li2S and Li2A8. And these polysulfides by nature, they are in liquid state. And these liquid state polysulfides, they go into the electrolyte. They are not available for cathode for further charging and recharging. So we need to trap these polysulfide or arrest the polysulfide so that significant amount of sulfur is available at the cathode side so that the battery could be able to perform much better. So in this way, we have made a carbon material embedded with the nitrogen and sulfur heteroatoms, and to that we have intentionally added some sulfur, and to our surprise, you can see that now the capacity is increased to 1000 mAh. So you have a theoretical capacity of sulfur battery for 1600 mAh, and we have already crossed more than halfway. And it is stable for 500 cycles. We have made a lot of progress. I think I have another slide where Professor Ranisar spoke about MOF. Very recently, we have derived this metal nanoparticle embedded on the carbon matrix, facilitated by the MOF or ZIP material. And you can see that these, we expect that these transition metal oxides are metals in the sulfur battery also. Such concept has been very well understood in case of supercapacitors. Now, first time we have introduced this quantification of diffusive and capacitive charge storage in case of lithium sulfur battery as well. And it was recently appeared in Langmuir. So how much time? Yeah, so I think I'm mostly done. So this is the sister device. We have made a lot of progress. So I think I can just go through the slides. Just few seconds. Yeah, so these are the prototypes we have made for the supercapacitor, and large device has been exhibited, and so this is the summary of work. So we have improved the capacity from commercial lithium-ion battery to 600 to more than 600 mAh for the battery, and also for the supercapacitors. And we have a joint project with IIT, IISc, and IIT Hyderabad, SICRI. And so in all, what we do is we make alternative electrodes, mostly metals and metal oxides, and sometimes from sustainable sources by modifying the morphology, conductivity, redox process, and increase the electrolyte interaction in such a way that redox activity is facilitated. It results in high capacity, high power density, better cycle life. And one of such product was this is one. And we have also demonstrated in a DST meeting very recently, 2 months back. Professor Ramana is here. And so thank you very much for your kind attention.
It's really quite impressive to see the progress that has been made in the field of batteries. It's really well appreciated. You know, any questions from audience? Yeah.
Yeah.
Good evening, sir. Sir, how do factors like temperature and humidity and the air quality in the fabrication environment affect battery performance and quality, sir?
I guess you are referring to lithium air battery, correct? Of course, temperature dependence one has to also consider for other batteries. With respect to environmental aspect, very much important for the lithium air battery, because the environmental oxygen is not 100% oxygen, it is also already contaminated with carbon monoxide, carbon dioxide. And so these carbon monoxide and carbon dioxide, when it reacts with the alkali as an electrolyte, for example, so they can make a carbonate and they will be embedded on the pores of the catalyst. So initially you will get high capacity. After a few cycles, 5 cycle, 10 cycle, the cycle life will be retarded. So carbonate formation will be there. So that's why. So you need to either filter these toxic gases or problematic gases, or you have to have a pure oxygen. But there is a new battery chemistry is coming up, similar to lithium oxygen battery, lithium CO2 battery is coming up, where one can use the raw carbon dioxide itself as an active material. So the catalyst must be robust enough in such a way that it catalyzes OR or OAR as well as CO2 reaction. And with respect to temperature, generally, so low temperature will result in poor performance of the battery, because the lithium ion or ion mobility will be retarded. At elevated temperature, adverse effect will be led to the battery. It will decompose electrolyte, unnecessary gassing and all will take place. The battery need to be optimized in a insulated environment depending on the battery chemistry. I hope I answered.
Thank you, sir.
Any other questions?
Yeah. Correct. Okay, so dendrite formation, wherever we use in particular lithium as an elemental lithium as an electrode, we have a dendrite formation. So in that particular work is to, our specific work is to focus on the identification of cobalt and tin as an electrode material. Of course, dendrite formation is inevitable in lithium systems. So, so people had some additives or suppress the dendrite formation, all those things. Dendrite formation is inevitable lithium battery, but different aspects need to be addressed for counter that. So we concentrate on the electrode materials. Thank you.
Thank you so much. And I will be happy to honor my dear friend.
Thank you, Professor Ashok, after a long time. Thank you. Thank you.
Yeah. So next I will be happy to invite Professor R. Godandaraman, who is an electrochemist from Indian Institute of Madras, Chennai. Actually, he is also from Indian Institute of Science, Bangalore, where he has done his PhD. And he went through 2 postdoctoral research training, one in Michigan State University, USA, and other one, National Research Council of Canada. So in both places, he has done his postdoc research. And with this small introduction, I invite Professor Godandaraman, and he will be delivering his lecture on battery chemistry. Yeah. Thank you.
Okay, thank you, Chairman, for the kind introduction, and very good afternoon. Is my slide going here? Okay, thank you. Okay, this is the title that I have proposed. Before that, thanks for the organizer for this kind invitations. So this is the title I proposed because Shiva was asking me to submit abstract when I was doing something in Trichy, so I gave this very long title. Later on I thought about it, then I simplified. Okay, this is the title under which, but the content is same, but the title is different. So the objective is to use the quinone for energy storage here, particularly redox flow battery. And this quinone has some issues in terms of capacity degradation. So to mitigate the capacity degradation, also to increase the energy density. Energy density, I mean volumetric energy density. That means 1 unit volume of the electrolyte, how much energy it can store or it can deliver, right? To increase that, we need to increase the solubility. So in order to increase the solubility, we went on functionalizing similar quinones with the phosphonate or with the carboxylate type of groups. But by doing so, we are able to increase the solubility, but there are other issues that were cropping up. So all were related to capacity fading with the cycling. So my interest here is to see what is the reason for this capacity fade and how to arrest this capacity fade. So one molecule does 3 different roles here, that's why I put 3 hats. And why we need redox flow battery? Because in the future, the grid going to be a 2-way grid. That means you can draw energy from the grid just like we do now from the electrical lines. Also, you can supply energy back to the grid. So for the 2-way grid to be stable, there are a lot of other electronic items required, otherwise it won't be resilient. And also we need to match the supply and demand. For that, an energy storage mediator is important. So that is where a low cost energy storage option is important. That's where this organic redox flow battery come into picture. So for the benefit of students, I made a small animation that shows how this quinone can be used for energy storage application. I have compared it with pumping a water from the lower tank to the upper tank. So here you see this is the Nernst equation. Sorry, I do the same mistake as what previous speaker did. So you can, so it's not going. Let me see. Okay, now, yes, okay. So you can see this is the Nernst equation for the 2-half reaction, quinone to hydroquinone and ferrocyanide to ferricyanide, right? So as you charge, that means as you draw electron from the ferro and put it in the quinone, so it becomes hydroquinone. So you see water going up here, right? So this is process called charging, because as you do this, the voltage of this quinone side will become more negative, that means increase in energy. The voltage of the ferrocyanide side will become more positive, that means decrease in energy. Therefore, the energy difference between these 2 redox couple or catholyte and anolyte will go up, and that is very similar to pumping all the water up, and you see if you let the water come down, automatically it will flow, right? Because it is now energy stored, potential energy stored here. Very similar thing we do with this organic molecule to store the energy. And we do the reverse, okay? When you do the reverse, the energy will come out of the battery and the redox couples will come back to the energy level where they were before, right? And now if you look at it, this is how the actual redox flow battery will look like. The anolyte and catholyte, that means the quinone and the ferrocyanide, ferricyanide that I talked about, is stored in these 2 tanks, and then they are pumped into the cell. It has a dummy electrode like a carbon electrode. It is used only for the charge transfer process, okay? So this tank, depending upon the size of this tank, you can increase or decrease the total amount of energy that is stored. Therefore, it is very modular in nature. Suppose you have a grid, in that locality you have certain X amount of energy in excess. So you can design your tank such that that X amount of energy is accommodated. So you don't need to over design. If you buy the existing lithium-ion battery, the power and energy are coupled, whereas in redox flow battery, you can independently design and design the power and energy rating. So that's the advantage here. Okay. So now, if you look at it, this shows the cyclic voltammogram of quinone hydroquinone, in this case specifically 2,6-dihydroxy anthraquinone, and then the ferrocyanide CV also I have shown here. This is before cycling the battery. The moment you cycle, after a few cycles, we start seeing a species here. You see an oxidation signature here, and there is a small shoulder here. These two are the species which actually degrade my capacity, degrade the cell's capacity. So our interest is to investigate what are those species, right? So now if you look at it, this is our hypothesis. So as you charge the battery, quinone becomes anion radical, then it's supposed to go further dianion, but this anion radical can undergo dimerization, form a peroxo species. You see OO bond here, there is a peroxo species. The beauty is the peroxo species can be oxidized or reduced, like just like hydrogen peroxide, which can be oxidized or reduced, right? So on the other side, you will have the ferrocyanide, ferricyanide that is happening. So if you form this, if this peroxo species forms, this is not electroactive. You might have seen in the previous slide, this peroxo species appears somewhere here. So the voltage of this is very similar to the ferrocyanide, ferricyanide voltage. That means the voltage difference between them is 0. So therefore cell will not function. So it is important that we don't have this peroxo species. So how to arrest that? One way is to apply the higher potential so that the peroxide species can be reduced. You can make a dianion finally, okay? So that's what this slide shows, how we can apply the higher potential and make this, we can reduce this and take it to dianion. The presence of OO bond linkage can be proven from the FTIR and mass that shows dimer present and so on, and presence of radical is proved by EPR. I am not showing those details for the want of time, okay? So now one more species that is possible to form, that is when you charge this battery, so you form the anion radical. This also this molecule which you have put in the alkaline aqueous medium, that is alkaline potassium hydroxide medium, ionizes, forms this kind of species. It's you know this get deprotonated, okay, but there is an equilibrium. So this anion radical that is formed can form a charge transfer complex with this neutral species, and I call it as a CTC. So this charge transfer complex is EPR active because it has a single electron floating around, okay, and this charge transfer complex is what you have seen in the CV as a small shoulder very near the hydroquinone-quinone signature, right? And now, knowing this, so we wanted to know, so okay, we know there is a peroxo species formation. So how do we use it in our favor? What we have done, this is the first, okay, right here. So this you can see here, these black lines. So when we charge, discharge within the limit of 0 to 2 volt, okay, you get about 2 ampere hour per liter capacity. So ampere hour is equivalent to moles, okay. When you talk about moles per liter, it's similar to ampere hour per liter that I talk about. That means you have dissolved the hydroquinone in the electrolyte and you have used it here. A fraction of it has come out for the electrochemical energy storage. That is what you see as a 2 ampere hour per liter. But as I increase this cutoff voltage, you can see it, I am going all the way to 2.4 volt. When I increase the cutoff voltage, what happens is this peroxo linkage breaks. That means it gets reduced to a dianion. Therefore, I am able to expand the capacity from 2 to 12. This is possible because we knew the species is forming, and we also know the remedy that just increasing the potential, we can do that. One way to increase the capacity of the cell is go back to this here. So you can see here, this charge transfer complex is formed because of presence of this neutral species. So we can simply increase the concentration of hydroxide in the solution. Therefore, you can tilt this equilibrium towards this, and therefore you can avoid formation of this charge transfer complex because both are negative ions. It's very difficult to aggregate. Okay, that is another way by which we can stabilize the capacity. There are two ways. One is apply more voltage, other is increase the alkali concentration. These are the two ways by which we can do that. And now coming back, you can see this is a CV before cycling the battery. This is a CV after cycling the battery. We identified this species, it's a peroxo species. We identified this species, that is a charge transfer complex. After identifying these two, we are able to expand the capacity. Right? Now let us go to the case 2, wherein it is 1,5-dihydroxyanthraquinone is converted into, for example here, it is converted here into a diphosphonate type of a species. Okay, why did we do that? As I said before, we wanted to increase the solubility of this compound. It is otherwise soluble only very poorly, about 70 millimolar. So we wanted to go to molar scale, so we functionalized this. When you go to molar scale, in 1 unit volume of the electrolyte, you can dissolve more species. That means more energy can be stored. That means higher energy density can be achieved. So now if you look at it, we have made this thanks to Richa. So sometimes if the student get transferred from another group to you, you should not be unhappy, you should be happy. She came from inorganic group after 2 years. She had a very good synthesis hand. So without me telling anything, she starts synthesizing. Then it was easy for me to guide because she keep on making molecules. I tell her, put it in this cell, put it in that cell. Then life is simple, right? So this is what happened with her. She is having very good synthesis hand, although it is not as good as a synthesis what Anbarasan do or other organic colleagues here do. It's only 1 or 2 steps, but I don't know how to do it. The students did it. So after this, whatever comes, I take credit, not here, right? So now you take this compound. What was our idea? Let us functionalize, especially with a long chain. So this chain will go around. So the peroxodimer species formation will be avoided, number 1. And because of these functional groups, the solubility will go up so that I can increase the energy density. These are the 2 objectives I had in mind and designed this material. But to our disappointment, the first charging went very well. But the first discharge is here. So this difference, this arrow that you see is the difference. That means there is a loss in capacity. That means what went as hydroquinone did not return. A fraction of it only returned as quinone. Okay. So the fraction of the length of this, length of the charge curve, length of the discharge curve divided by the length of the charge curve tells you the fraction of the molecule which returned back. In other words, Coulombic efficiency of this process, right? So now if you look at it, there is a huge loss in the first cycle, and when you are continuing cycling, after around 70 cycles, we saw there is a hump, another plateau started developing here, and that plateau got intensifies as you cycle more and more. That means what? The quinone was reducing at this voltage earlier, now it requires higher voltage, okay? But if something requires, that means if it requires higher voltage, if it is a quinone, then it should have reduced at lower voltage, but why is reducing at higher voltage? That means there must be another species in the solution. That may be quinone or some kind of quinone derivative that is in the solution. So that was our initial guess. We repeated this measurement several times, we got the same observation. Then my student went on doing this charge discharge at different currents, starting from 5 milliampere per centimeter squared all the way to 40 milliampere per centimeter square. And this is the Coulombic efficiency. What is Coulombic efficiency? The fraction that come back as quinone during discharge. That tells you the Coulombic efficiency. If you see, the Coulombic efficiency is low at lower current, whereas it increases at higher current. What does it mean? Higher current means the battery charges and discharges quickly. That means very less time is given for each cycle. Lower current means more time is given for each cycle. So in that time period, there is some chemical reaction happens automatically in the solution. That is what's stealing my capacity, right? So that was our conclusion. So we have to figure out what is that species that is forming, then only I can mitigate the formation of that species. So now we have went for NMR to find out what is the species. NMR said before and after cycling, everything looks same, there is no difference. That means it says there is no other species present in the solution. Then we were thinking, okay, proton NMR is not useful. Then we went and did some cyclicotometry, taking the solution after cycling. Cyclicotometry did not show any new species in both the side, in anode side as well as cathode side. That means there is no crossover or there is no formation of new species. That's what it says. Then we went for EPR. It was EPR active. Obviously, because we have formed some anion radical, the radical still may be there in the solution, therefore it is EPR active. The G value is about 2.002, so it's very similar to free electron. Okay. So then with this, what we did was, okay, we suspected there could be a formation of a dimer in this case also, but there is no peroxodimer. Why? If there is a peroxodimer, if I have, after the second plateau, when I go for a discharge, I should get the entire capacity, but I am getting only part of the capacity. Therefore, there is a very less chance for the peroxodimer to be present. And also FTIR said the same thing, there is no OO linkage in this molecule. So here, what we did, we have increased the concentration of the potassium hydroxide from 1 molar to 3 molar. What has happened? Once I increase, in each cycle, you can see here, 1 to 9 cycle is this black one, then 10th, 30th and 50th cycle, you can see when I increase this, that capacity loss, that means the gap between the end point of the charging and the end point of the discharging started increasing. Earlier it was almost close, now it started increasing. What it means, also one more thing to notice, this capacity here, it is about 600 milliampere hour per liter. Previously it was about 350 milliampere per liter. By increasing potassium hydroxide concentration, I increased the capacity. That means the reaction is facile. Why it is facile? Because 3 molar potassium hydroxide is more conducting than 1 molar potassium hydroxide. Therefore, you get better capacity. Fine. But I also have a huge capacity loss. Why is it? Because the radical also forms more in this process. So that radical must be doing something, leading to capacity loss. Then we looked at, we charged the battery. You can see here 101st charge, that is a green curve which is not visible, which is under the blue one. This is a charge. And we waited for 10 minutes, then we discharge. That is this purple one. So when you wait, the loss is even more. Why? Because when you wait, this radical that is formed is undergoing some sort of dimerization, and then that is inactive, electro-inactive, therefore you have a capacity loss. So that was happening. Then we suspected when I increase the potassium hydroxide concentration, the loss is even more. That means the charge transfer complex that is formed must be stabilized by this potassium ion. So that is playing a role dynamically, it is uniting two different species and forming a charge transfer complex. And we resorted to cyclic voltammetry now, and we found another redox peak at a potential more negative to the quinone redox potential. That is why you have the second plateau. More negative potential will give you higher voltage plateau in the charge discharge. So that is matching all this observation. So what was the issue here? So I had a quinone, I reduce it, become anion radical. Also this quinone species can exist as anion because it has a phosphonate group, so those protons can go away. And then you are going to add, there is some, then this anion radical can pick up quinone in the solution and potassium from the solution can form a dimer like this. And if you further reduce, that is during the second plateau, it can become a dianion, liberating this other quinone species. This quinone species will be fed back into the system. That means it will affect this equilibrium, it will promote formation of anion radical, and that will promote the formation of, again, dimer. So this is leading to a catastrophic effect. Therefore, even though we are able to reduce the dimer, it is again leading to another dimer. So it's a cycle. How much time left? 2 minutes. I started 4:10, I think. 4? 20 minutes. Yeah, I started 4:10. Yeah? Oh, yes, fine. So now, if you look at here, this is our charge discharge curve. What we have done, because we know there is a dimer, we wanted to see how to avoid this dimer formation. There is one way. That is, you go back here, you see, if I somehow manage to avoid this dimer formation, how do I avoid? Either I make sure the concentration of Q is low or Q minus dot is low. Any one you can do. Or I can maximize this more compared to this. So that's what we have done. We simply added some D-fructose into the system that will ensure that this quinone is always in the reduced form. Therefore, we have avoided the second plateau. We also got the capacity, discharge capacity very similar to the charge capacity. Therefore, there is no loss in the performance. But this cannot be used in the battery because we cannot keep on adding fructose and make a battery. This is only to identify what is going on in the battery. Nothing else we can understand from this. And you can see here, this is a cyclic voltammetry. Once you add fructose, you don't see that second redox peak at very negative potential. That clearly tells there is no dimer. The presence of fructose ensures always there is a radical present. There is no dimer that is present. Therefore, the battery is seamlessly able to run. For want of time, I skip this. And again, with the fructose also, we found this EPR active signature. That means fructose is transferring electron to the dimer, quinone. So, and what happens? So, we had a battery which is giving about 0.7 to 8 volt. The moment you add fructose in the quinone side, the voltage has increased. How do we understand this? You can see this animation. So, I had this quinone and there is a ferrocyanide which is having a potential separation of 0.72 volt. The moment you apply, D-fructose to it, and it is equivalent to having the bottom tank fill, the top tank open. So, if there is a rain, the top tank also will fill, therefore, there will be a difference in the potential energy. But this battery cannot be operated. Why? Because the ferrocyanide remains as ferrocyanide. So, if you wanted to oxidize the hydroquinone, then electron has to go to the ferrocyanide, it is not possible. Okay, but this only tells, okay, we understood the problem, right? So, this particular molecule was no way useful for us, although we understood what is the mechanism by which capacity is lost. So, then we went on making two more minutes. Yeah, sir? Yeah. So, we went on making this molecule. Here you can see this is a carboxylate type of thing because it's a carboxylic acid group, alkyl, an ether alkyl carboxyl group here, and you put them in alkaline solution, then it become a carboxylate. So now what happened here, when we cycle this battery, with the cycling slowly capacity was decaying, okay. Although the discharge capacity was very similar to the charge capacity more or less, but with the cycling it was keep going down, finally it will become 0. Then we were wondering what is happening. Then my student started cycling for some time and then she gave a rest, and next day morning she started, then capacity regained. Again she started for some time, then she gave a rest, it started regaining. That means there is something related to the absorption, desorption that is going on in this process. That's what we understood. Then we wanted to know what it is, open the cell, okay. Then we are using a membrane called a Nafion membrane, which is a perfluorosulfonic acid membrane. So these molecules have a tendency to go aggregate on that membrane. So we could see from the color of the membrane, otherwise it is a transparent, colorless membrane. So we could see that. Then we were wondering what is happening, why this molecule is absorbing, whereas other two molecules were not aggregating on this Nafion. So hypothesis is the following. So you have the 2 carboxylic acid arm. When you put in the KOH, it becomes carboxylate. And when the cell is in operation, probably both the arms comes in one side, and this aromatic backbone, okay, by a lipophilic attraction may get absorbed on this backbone of the Nafion. That may be the reason why it is happening. This is our surmise. So with this in mind, we went and did some NMR because we had to prove that. So we did NMR. What is interesting is, for this molecule, when you take it in the CDCl3, this is a pattern, okay. So the E proton here is appearing here as a doublet at the highly deshielded. But once you withdraw the solution from the cell, okay, that means you have both D2O, because D2O is used for diluting the solution, and KOH is present in the solution. So because of KOH, it will exist as a carboxylate. So this carboxylate will do an intramolecular interaction with the carbonyl carbon. Therefore, the shielding effect is gone, right? So you see there is a swapping. The F proton has come first now. I don't see the color myself. Okay. F proton you see in the top, that the E1 comes in the middle. So triplet went first and doublet went behind that, right? So this is a clear proof that there is an intramolecular interaction. Because of that, the arms are driven towards this carbonyl group, exposing the backbone. Therefore, this backbone is able to interact with the Nafion and aggregate on the surface. Whereas other molecules did not have that avenue, so they were not doing that. So this is a new problem. Because of this, capacity is lost, okay. So what we did, this problem we turned into an opportunity. What we have done, we have taken, this is another proof. You can see this is the molecule IR and Nafion, fresh Nafion, and you see Nafion which is used in the cell. You see the signature of this molecule on the Nafion. That's a proof that it is sticking to the membrane. So what we did, we have taken the electrode which is here, okay. That electrode itself we have dipped in the Nafion ionomer solution. So when the electrode is coated with the Nafion ionomer solution, this molecule will first stick to the electrode instead of going to the membrane. Once it is very close to the electrode, electron transfer will be easier. So that capacity should not drop at all. That's our idea. So this learning we had from the problems that was presented by the Nafion membrane. So we did that, and you see in the previous case capacity was keep on decreasing with cycling. In this case capacities keep on increasing. That means utilization of the material is becoming better and better, because this molecule is retained on the electrode itself, not allowing to go to the membrane. That's the idea here. And you can see from the IR spectra, the Nafion which is, excuse me. So you can see here the signature of this molecule is not seen on the Nafion which is used here, because it's all trapped by the electrode itself, it is not gone to the membrane. So with that we have shown even with a higher concentration we can run the battery. We have gone up to 4 ampere hour per liter kind of a capacity. That's what the demonstration we have done with this. So, and the conclusion, we had this quinone molecule, simple quinone, anthraquinone molecule, 2,6-dihydroxyanthraquinone, but therein we had the problem of peroxose bridge formation, but we found a way to break it and unravel the capacity, which was locked. And in the second one, we had this complex, this charge transfer complex formation. We didn't have a solution, but we identified the problem. The third one, we found this intramolecular interaction allowed this molecule to self-assemble on the Nafion, which was used in our favor to make the electrode and Nafion composite. and hence capacity is retained. These are the three different action by the same redox site, which was interesting for me. Therefore, I decided to present to you. Okay, with that, I thank all these guys who are involved in this work and the funding agencies who supported our research. Thank you for your attention.
Any questions? You have a question?
Beautiful chemistry, you're going to hate me for the question. In your last part, with the intramolecular interaction, if you have the carboxylate attacking the carbonyl group to create the stereogenic center, your arm should show diisotopic proton. You will have different chiral isomers. You will have a racemate. You will have meso. Your NMR must be more complex than you have.
Okay.
How do you explain this?
I want to answer from you. I'm not an organic chemist. I will talk on this with you. But so far, this is what I understood from this study. So I will think about it. Thank you. Thank you. Yeah. Aliphatic. Yeah. Okay. That's where I like your company. So you correct me.
Thank you. Thank you so much.
Thank you.
Nice presentation. The last lecture of this session is going to be delivered by Dr. Sureshkumar from National Institute of Interdisciplinary Research, Science and Technology, Kerala. Actually, he has obtained his PhD from Dublin City University, Ireland. And later, he just did his doctoral research in Michigan State University. While doing his PhD, he was really associated with several industries. And he has very nice collaborative research exposures with the industries. And right now, he is serving as a scientist at NIST. Yeah, right. And he is working on developing indigenous material for making photovoltaic solar cells to trap sunlight and to make into electricity, right? So without further delay, I invite Dr. Suraj to deliver his lecture.
Is it on? Okay.
One important point I need to mention. Now, I was really quite impressed to see his CV. And as a young scientist, he has received the Young Scientist Award from more than 7 bodies. Okay, so including CSIR Young Scientist Award, one of the very prestigious awards. So he has received more than 7 awards as an young scientist.
So, am I audible? Yeah. So, warm good evening to one and all. And first and foremost, sincere thanks to the organizers and Shiva for inviting me over here. And excellent introduction, and thanks a lot for to the chairman. I'm pretty sure like an afternoon session after taking so much of sweets and all, such a nice lunch today, and everyone is waiting for a cup of tea. So I will without wasting much of the time, I will just move on to my presentation. So the presentation is titled as Enabling Clean Energy Transition Through Indoor Ambient Light Recycling. So I'm so happy, like 2 of my previous speakers who are also my friends. So they speak to you about the storage part, the battery part, isn't it? And why we are speaking about this battery and all? Because we all know the issues with the climate change, the carbon emissions. We need to move out from the fossil fuels to the renewable energy sources where the EVs and all those things are coming up. We need to store the energy. We need to put the solar cells. We need to produce kilowatt and megawatt kind of power. But today, I'm going to discuss with you something which is a little bit different from before. So all of you recognize what is this, isn't it? So today morning also, our respected Vice Chancellor mentioned like there should be alternatives or sustainable solutions for the batteries. So we all need batteries, isn't it? Like that's something like we can't keep it out. But there are millions of applications right now. Like you might have heard about IoTs, Internet of Things, sensors, actuators, those kind of communication devices out there, which actually are powered by those button cell batteries or AA, AAA batteries. And do you know, like in our home itself, every year, how many batteries we are throwing out, isn't it? From the clock, from the remote controls, from the kids' toys. And can we actually have an alternative, a sustainable alternative, an indigenous solution for these kind of one-time use batteries? So that is actually the point that we are trying to work on. You know, like every year 15 billion batteries are thrown out into the Earth's crust and which are not being recycled, which is almost the size of our state, Tamil Nadu. Imagine, so every year it is getting added up. So that is actually the point that we are trying to speak on. And there are various forms by which we can harness the energy around us and use it for these kind of applications which are mostly situated in the closed spaces. So it can be either through radio frequency harvesting, the piezoelectric generators, the thermoelectric generators, or from the light which actually surrounds us. So out of all these various options available, the ambient light harvesting actually provides certain unique advantages which are like it's easily available. You don't need to find a vibration. You don't need to find a temperature difference. It's actually having the highest power density per unit area, the ease of integration, and the kind of pleasant aesthetics it is having because you are actually trying to keep it on the indoor spaces. And most importantly, the point here, the energy harvesting in any ways that we are doing, it actually not only reduces the number of batteries ending up as landfills, but also lowers the volume of mined raw materials. You know, we need lithium for high-end application. Why to use that lithium for powering a small remote control or powering a toy or powering a clock? So if there are some other sustainable solutions, that is what we need to look into. So as we see, like ambient light harvesting gives the maximum power density. And out of the entire photovoltaic technology, the one like today morning, Dr. Nithyananthan has really set the stage for me, like where he had clearly explained you about one very beautiful technology which works with the principle of artificial photosynthesis, which is none other than the dye-sensitized solar cells, which actually delivers the maximum power density among all the photovoltaic technologies. It's very simple, like as he mentioned, like 2 electrodes and 3 components in between, a dye, a semiconductor, and an electrolyte. And it works with the principle of like the light is incident, and if the band gap is matching, electron gets excited. I'm not going to all those things, like because already you have heard about it. So what I'm going to tell you is that whatever in 1991 Michael Gretzel in EPFL and Brian O'Regan discovered this technology, after almost 25 years of time, the entire scientific community realized that this is not a competitor for silicon, but it has a totally different regime of applications which are out there, which were not there before. Because, you know, like the indoor light that we see here, the CFL and LED, when it came up only like 10 years back. Then the kind of applications we are speaking, Internet of Things, sensors, actuators, smart devices, smart classrooms, when these things started to come up, only in the last few years' time. And that's where the entire thing started to change in 2017, where the Michael Gretzel actually put up the paper in Nature Photonics, where they introduced a co-sensitized organic dye along with a copper electrolyte, along with a p-dot counter electrode, replacing the conventional ruthenium dye, iodine electrolyte, and platinum counter electrode, realizing an efficiency of around 28.9%. And over the past couple of years' time, the efficiency has gone from 28 to 34.5. And we were also trying to work on it from last almost 8 years. And very recently, last month, we were able to break the record for the first time, breaking the EPFL number, reaching an efficiency of 35.6%. And this was all achieved not through the conventional dye cells, what you normally see. It uses like this organic co-sensitized dyes, copper electrolytes, and innovative device architectures like what you see here. These are the kind of organic dyes that are being used in this high efficient kind of indoor light harvesters and these kind of copper-based metal complex redox electrolytes. So what we do in NIISc, whatever I am going to show you, is actually a nutshell of the work that we have done since 2014, almost 10 years of the work. And we work at the interface of physics, chemistry, material science, and engineering. And we keep an eye on the end user application where you are going to use these devices. And accordingly, we fine-tune the devices in a way to actually control the power output and thereby change the chemistry or the material part out of the whole thing. So today I will just handpick 2-3 different works which is mainly associated with the electrolyte, the chemistry of the electrolyte which is involved, which really helped us in a way to further push the efficiencies to those kind of like benchmarked numbers. So, like conventionally iodide triiodide is used, but it has a lot of big issues like associated with the commercialization and also with the energetics, which actually limits the voltage. And voltage is a very key factor based on the application, the indoor light harvesting energy circuits that we speak about, where it needs a minimum of 1.5 to 2 volt threshold voltage in a way to kickstart the circuits. So voltage is actually, just keep in mind, voltage is actually a main parameter that presently we are looking on. So there we actually introduced this copper-based electrolyte system, and in 2017 Gretzer actually came up with this metal complexes, and what they have done is a tetramethyl bipyridine system, and we actually took this normal phenanthrolene based system because it's more cheaper and more easily available, and we tried to work out, this is actually one of the first paper where we compared the iodine, cobalt and the copper electrolyte in a very detailed way, and what we have understood is that even though these performances are fine, the main key research behind this particular initiative is to understand what still is left behind, how we can further improve it. And there we find out 2 critical parameters. One is the mass transport, because these are metal complexes, isn't it? So 2 electrodes, this ions has to migrate in between. So these are diffusion limited. And how we can improve the diffusion? If you improve the diffusion, like the charge transfer will be faster and you will get a better power conversion efficiency. The second part is the recombination. And that recombination is not just the normal recombination from the conduction band, but basically from the sub-band gap state, trap states and the surface states. And then we went into like how we can address these particular things. So when it comes to mass transport, what we have done here is to control the thickness of the electrode. And there, like when any photovoltaic device, there is a rule of thumb. Like you take a device, you measure a JV, you will get a current density. You do an IPC, you integrate it, you will get a current density. This both should match. It should match for the PN junction normal semiconductor devices. But if you are actually speaking about a device which is mass transport limited, it's not necessary. Why? Because your JV is done at 100 milliwatt per centimeter squared. Your IPC is a monochromatic light which is done at less than 1 milliwatt per centimeter squared. So that is actually clearly proved with this particular, this is actually the first time where this particular concept actually was put up, where like the students Saurav and Jay, what they have done is that they made devices with a different thickness. So here you can see, like this graph will clearly show you, when the light intensity is less, the device with the lower, higher thickness actually performs better, like leading to like, like around 12% efficiency. But when it comes to the the higher intensity condition, there the thinner electrodes actually leads to more than 10% efficiency. So this is a very critical factor. The take home message is nothing other than that. Like it's not you make a device for measurement and you take the same device and do an indoor measurement, you will not get the kind of performance. There are very critical parameters that you need to address, thereby you can improve the photovoltaic performance, particularly under the ambient light conditions. And this is actually a follow-up work that we have done where we systematically investigated the porosity of the electrodes by which like you can actually improve the mass transport limitations. And this was actually followed by addressing the second issue, which is the recombination. And there, we actually came up with a new innovative kind of a concept, which is called the asymmetric dual species copper electrolyte. So normally what happens? What results in the recombination? You have the TiO2, the electron is injected, and those electrons will actually recombine with the holes which are present in the electrolyte. So what we have done is that how we can reduce this recombination. One concept is to reduce the driving force. If you can actually reduce the driving force, that will reduce the recombination. So what we have done is that what results in the recombination? The oxidized species. In normal cases, you have the oxidized and the reduced species having same structural kind of properties. But what we have done is that we custom made a oxidized species, which is a 5-coordinated species with a halide attached to your copper metal center, which actually pushes your redox potential like to more positive region. So now your recombination driving force is completely reduced over there. And what we have done is that we actually, with the passage of the time, what happens? The copper 2 metal complex is unstable. And the moment you add the additives in the electrolyte, which is there in the actual device, this tertiary butyl pyridine, the pyridinic bases that you added, it replaces the whole ligand. It forms a copper TBP4 kind of a complex. And this TBP actually poisons your counter electrode, and that leads to lot of issues. But what we have done is that with this structural modification that was done, we were able to actually obtain a totally different mechanism, which is like a dual species kind of a mechanism, and we were able to obtain the crystals with the passage. This actually is a work which was done over a period of like close to 4 to 5 years time. And then we separated the crystal, we analyzed it, and finally we came across like a very interesting observation where you can see that with the conventional electrolyte, there is very critical counter-electrode poisoning that happens where the charge transfer resistance is much higher, but when it comes to this new dual species electrolyte, it almost like gets to a constant over there. And end of the day, how it reflects in the performance. So here you can see, we took the same dye like what Michael Gretzel from EPFL has used, the XY1 dye and the D35. This is actually the Nature Photonics paper, the same dye, only difference is that we changed the electrolyte from their electrolyte to our dual species electrolyte. And what you see here is orders of magnitude improvement in the lifetime. So this order of improvement in the lifetime was a result of the lower driving force, which reduced the recombination and improved the lifetime, which reflected in your voltage very clearly. From 797 millivolt to 905 millivolt it improved. The current is slightly less because this particular electrolyte is a little bit more colored. The DD transition is over there in 600 to 700 nanometer region. So that extra light absorption kills a little bit of the current there. But with the better counter electrode charge transfer resistance, faster regeneration at the counter electrode, you get a better fill factor, finally leading to 35.6% efficiency. And this was again proved by taking the other ligand, which is a dimethyl bipyridine ligand, and we were able to make the same complex, and we see the same kind of an improvement, but the net efficiency was not high as that you see in a phenanthrolene ligand. But you can see from the standard, like going to the dual species, there is a systematic improvement in the performance. And then we have actually taken these devices here. You can see this is a temperature sensor, which is actually being powered by two of these devices being serially interconnected. This is where, like I told you, voltage is the critical. Why it is being serially interconnected is that the sensor needs a minimum threshold voltage of around like 1.5 volt. And this is actually like very recently, like last month it was published. And then like parallelly, we were also doing another work where this particular dual species electrolyte was introduced along with a new co-sensitizer, which was actually developed by one of my students. And now by integrating with this co-sensitizer, the XY1B dye and the dual species electrolyte, we were able to reach an efficiency close to around like 37%. So now I will move to another important work that we have done last year from the material part, where, as I told you, the end-using application needs higher voltage. How you can get more voltage from these single junction devices. So there, we have introduced another new strategy of bilayers. So what we have done, this is actually a paper that last year we got published in Journal of Material Chemistry again, and this was selected as one of the most popular articles from the last year. And what we have done here is that one of my students, Anuja, she made some microstructures, zinc oxide microstructures. And initially, like if you check the literature, some of our papers, we were using this as kind of a platform. We remove the zinc oxide, we create some architectures that improves the scattering. But one time while she does the experiment, she completely forget to remove the zinc oxide. And what we have seen is a very lower performance, but the voltage was very high. Then we investigated further into it, and what we have seen is that when you actually forms a bilayer, there is a shift in the conduction band. With the normal device, if the conduction band is like that, when you go to a bilayer device, there is a negative shift in conduction band, and that is clearly reflected in the voltage, because the voltage is the difference between your Fermi level and the redox potential. So if your conduction band moves more negative, your voltage automatically increases over there. But you know, like you can see the performance is like not high, like it's around like 7 to 8 kind of efficiencies over there. And previously, like whatever I have shown here, this is initial results were done with the standard dye, which is Y123. And later we switched that dye with another dye called MS5, which is having longer alkyl chain. So in the morning, Dr. Nithyananthan was telling you like how the long alkyl chain, that is actually one strategy by which you can spatially separate your holes from getting close to your TiO2, thereby reducing the recombination. So by changing from Y123 to MS5, automatically you can see how much improvement in the lifetime has been achieved. And that actually lead to this record voltage of 1.27 volt from a single junction device under the full sun condition and just above 1 volt under the indoor condition. And I just want to tell you, just look at the efficiency. The efficiency under the indoor light here is only less than 10%. And you can see here the real application. So here you see two devices like these sensors, like previously you have seen in the previous video where the two devices are serially interconnected because the threshold is around like close to 1 volt. So you need to generate above 1 volt and two devices need to be serially interconnected. But here you can see just with the one device, which is like a button in your cloth. So with that one device, you are able to power a small gadget like a temperature sensor, which actually opens up kind of applications where like this can be taken up further. Then from the engineering side, we have done a very innovative step where, conventionally from the last 33 years, whoever works with the dye cell, one thing that comes to their mind is the holes, because you need to fill the electrolyte. The holes need to be there, and that actually is the triggering point for the leak and the other issues that comes up. So when it comes to scalability, you need to actually work on totally different strategies that are different from the normal basic science research. So there we have done a very innovative kind of an approach where we made a hole-free spacer free device. So this is actually a small module like where you don't see any holes. So basically like now we even make it on thin films where you can see that it's just like a normal CIGS solar cell or a gallium arsenide kind of a solar cell without any holes or without any kind of spaces. So presently like this is the update from our lab, like the best efficiency, indoor efficiency right now what we are having is above like even 40% in the hand. So now moving to the translation, lab to the land, whatever the science that you do in the lab, how that translation happened. So it all started in 2017 with a DST SERI project where for the first time like we indigenously designed and fabricated a set of equipments by which like we can move into the kind of modules and prototypes and get a kind of an expertise where the translation can be taken up further. But then we realized, 80% of the cost of production into these devices goes into the TCOs, the transparent conductive oxide, and what we normally use are the FTOs. So just by buying the FTO, you can't be able to scale it up to that kind of an extent. And then we went into indigenization of the conductive oxide coating where we have done it. We made some very unique equipment, spray pyrolysis systems and optimized, and we make our own FTO. So on a 5 centimeter by 5 centimeter substrate, now we get around like 4 to 5 ohm per square centimeter, 15 by 15 around 7 to 8, and a 30 centimeter by 30 centimeter will get around like 20 to 30 ohm per square centimeter things. So now like you have the equipments, you have the process, you have the science with you, like no one will accept saying that like you have a device, it gives so and so kind of efficiency. Numbers doesn't matter. Real application world is totally different. There you really want to show what you can do with the things that you have in the hand. So there like we actually try to innovate and find out new applications, and we were actually scouting through like what really can change the life of people around. So there can be applications like remote controls, there can be just like a sensor and things like that. And then it struck our mind like, why can't the air quality and health, because our system is able to harness the indoor light. And post-COVID, one of the most critical parameters in the closed spaces which are not being monitored are the indoor air quality. And you need to have like lots of these kind of sensors that need to be installed. And if we can self-power those systems, that actually is going to be a big impact that can make to the community. And that's where last year, like we made one of the first prototypes which actually detects the temperature and humidity. And then later it was actually changed to a more pleasable kind of a product. And this was actually supported by DST through the DST Solar Challenge Award. And this particular prototype, like it doesn't have any batteries. So over the passage of like 10 years, you can save around like 40 AAA batteries, which leads to like almost like 2,500 grams of CO2 emission reduction by the whole system. Then the point is that you are speaking about installations in the indoor space, and why someone should accept that, like why the community should accept something, a science and a technology to be installed in their homes. So there, like we started to think like, what people will accept more, like art. Art is some form like that people appreciate to have in their homes or in their office spaces. So can we actually think about integrating the science, technology, and you can see these are all solar cells which are made in different dimensions, which are made in different shapes. And this is actually a very recent prototype that we have done. This is a home decor, like you can keep it as a decor item there on your wall, and it gives you like various temperature, humidity, those kind of parameters. And presently, myself and Dr. Nithyananthan, we recently like got a project which we are going to start in this April, where our target is actually air quality, self-powered air quality installations in airports. So, airport is actually a place where in none of the airports in our country, there are no proper detection of the proper air quality system. And then we are actually partnering with the Trivandrum Airport from Adani, and the initial prototype will be done over there. And that prototype, it's not a solar cell. What you will be seeing is an artistic installation, but that artistic installation will communicate with you. For example, like one of the dream concept that we are having here, you can see this is a dragonfly. So we want the dragonfly to be the messenger of sustainability, which speaks to the world about a sustainable indigenous solution, which is a self-powered solar cells, which are locally manufactured, at the same time communicating a message like an air quality, which can improve the quality of living standard of the people. So this is actually where we are going, a battery-free world through ambient light recycling. But don't take it in another way, like this is not completely replacing batteries. Wherever possible, wherever we can replace it completely, that can be done. Otherwise, like you can have a super cap or you can have a storage cap, and the primary battery replacement, the quantity can be reduced to a greater extent. So to conclude, like we actually work on the advanced guarantee turnkey solution, innovative application, leading to the indigenization of the ambient air light harvesting technologies for the future. And whatever I have done, like this is actually my team, and they are behind the entire work, and the collaborators and the funding agencies. I just want to show you a 1-minute video, and with that I will finish it up. So this will actually brief, there is a voice over there, can you?
The global energy crisis, intensified by the pressing challenges of climate change and an ever-growing population, has necessitated a paradigm shift in our approach in how we generate and harness energy. The evolution of Industry 4.0, connecting people, machines, and systems through Internet of Things, is enabling a transformative era in the present century where battery-powered connected devices play a pivotal role in expanding our technological landscape. With 15 billion primary batteries disposed annually, we are polluting more than 0.3 million square kilometers of land. Replacing batteries, realizing self-powered devices not only reduces the carbon footprint from used batteries but also lowers the volume of mined raw materials, thereby improving the entire value chain. Aligning with our nation's ambitious goal of attaining net zero emissions by 2070, CSIR National Institute for Interdisciplinary Science and Technology, with a decade-long experience in the area of molecular photovoltaic devices, envisions spearheading a transformation in indoor ambient light harvesting technologies. CSIR NIST has achieved indigenization, pioneering the development of equipments for indoor photovoltaics, alongside the establishment of standardized characterization facilities and supply chain. NIIST has successfully optimized the fabrication processes for indoor light harvesting small area devices, master plates and modules, realizing higher performance under indoor light compared to conventional solar technologies, achieving self-reliance and Atmanirbhritha. Indoor photovoltaics is predicted to achieve a market of $850 million by the end of 2024. This marks the commencement of an unparalleled breakthrough within the energy sector, as we strive to cultivate an off-grid, self-sustaining power ecosystem through innovative approaches in light recycling technologies.
We're actually conducting a skill development course. It starts next month. Those students who are interested, you can actually check the website. It's a 1-week course where you will get a hands-on training for these kind of photovoltaic devices. What we are trying to do is not just like, these are not rocket sciences. Like everyone should do it. Like every place should have these kind of indigenous technologies that that should come up. Then only like this can perpetuate in a bigger level. So thank you. Thanks a lot. So I also do have like a small prototype with me. So this is actually one of the products that we have developed. It's a self-powered temperature and humidity sensor. So you can see like if some light is there, someone can just shine a mobile and yeah, can you just like turn on this light for a second? So now it's not working. So since enough Yeah, you can see like the display is on there. So we didn't put any battery or supercap in it because it's a prototype to show that like it just works with the kind of light that is having. So this is actually in 100 lux. The minimal light intensity that you need is around 100 lux. But the moment you add CO, CO2 and those kind of sensors, then the power, it becomes a bit more power hungry. So we are actually making our own kind of circuits. Sensors are being purchased, but the energy harvesting circuits are being indigenously now made, particularly suiting to the applications. Thank you.
Thank you, energetic presentation. And I really appreciate that. Okay. Yeah. Any questions from audience? Yeah. Okay. Thank you so much. It was really wonderful presentation.
Thank you.
Yeah. For your patient listening and for nice interaction with the presenters. Thanks.
Before we continue the session 4, we will now have a short break for tea. Please use this opportunity to network and engage your fellow attendees. Kindly get back within 10 minutes.
I thank my friend Professor Ashok Kumar for the wonderful chair of this session. Thank you very much. Yeah, thank you. Thank you. Break.
Over to you, sir.
Yeah, good evening to all of you. Welcome to the last session of this today conference. We have almost 5 speakers in the last session, and the first speaker, the plenary lecture will be given by Professor Jerome Lahore. He is from Department of Organic Chemistry, Faculty of Science, University of Geneva, Switzerland. He is very renowned professor who do not need much introduction or highlights. He did PhD from University of Texas at Austin and postdoctoral studies at Harvard University with Professor Evans. Then he joined 1995 and now is serving as a Dean of the Faculty of Science at the University of Geneva. So with this small introduction, I request Professor Jerome to start his presentation. Thank you.
Microphone, okay. I have a feeling we were together 2 days ago. Thank you for the kind invitation. Thank you for the IISER. Okay, I think I said it right. Well, I think I made a mistake. Sorry for this. And it's a great pleasure to be here. Okay, so arrow down. Arrow down. No, I'm looking just to move. Guys, can you put the laser? I have another one if that's. This is this one?
Yeah, this
one. Okay.
This is central.
Yeah, no, but just to go. Okay, thanks. So let me try again. Wow. It's still not moving. Ah, yeah, it is. Okay. So thank you. Sorry for this patient. Mr. Chairman, 1 more minute. Huh? Okay, just for the laser. Okay. So so my group does what a lot of organic chemists do. We like structure, we like function, we like reactivity, and hopefully methodology. When we talk about structure, we always talk about 3 things. We want compounds which are chiral. We want compounds, for instance, which are 3-bladed propellers or helicenes. We want compounds which are easy to make. 1-step synthesis. That's actually 1-step synthesis, 80% yield, or 20-gram scale. This is 2-step synthesis from 1,3-dimethoxybenzene. And we want charges. We want cations and the anions, because the first property that we ask the system to do is to do actually stereoselective recognition and hopefully stereoselective synthesis. We heard a beautiful talk about photocatalysis and how ruthenium tributyl complex are important. We like the ion complex more because they are labile, they are racemized rapidly. But if you put 2 of these anions with 1 of these cations in a low polarity solvent, single diastereoisomer, single enantiomer. And with that, you can do now, for instance, ultra fast circular dichroism, picosecond CD, and then all the spin crossover dynamics we heard actually this afternoon, okay, very rapidly, becomes actually much more simple to decipher. And this was actually published like a few months ago. And then you can now even like work on powders, not crystals, which are single enantiomer. And if you use actually linear beam lines are 7.4 electrovolts, okay, you can actually view even decipher the helical dichroism. You have a difference in actually, let's say, absorption between these 2 types of materials. So this is actually much more physics than chemistry. Now, what I like to show is actually how we and many others go about the so-called late-stage functionalization of dyes. It's really important to have a core and be able to functionalize after the fact. So the kind of compounds we like to work with are going to be cations, and we make them very simply from these building blocks. So in fact, in fact, we do the ortholithiation with butyllithium TMEDA, and then we use actually 3 equivalent of this for 1 equivalent of a soluble form of CO2. The first addition gives you an ester, second addition gives you a ketone, the third addition gives you the alcohol that we ionize with any acid to the carbocation that we isolate, okay? And then this is the discovery of Bo Larsen some years ago, that very simply in a solvent like DMF or NMP, you add an amine, even 1 equivalent, and you're going to substitute 2 of the methoxy groups by the amine to form the acridinium dye, thanks to the electron withdrawing capacity of the carbocation. Very simple, 1 hour room temperature. And the reaction stopped there. And what he discovered is that if you go to 90 degrees, and just for kinetics, we put actually 25 equivalents of the second amine, you can start to substitute the 2 more methoxy groups, and you form the quinacridinium. Closing it to the triaza triangulinium is much more difficult also at this stage. So you can isolate this type of compound with 80% yield. And when we saw this paper where the molecule was actually represented flat, okay, we immediately imagined that this compound would be chiral due to the repulsion between these methoxy groups. There will be a right-handed enantiomer with a P configuration or a left-handed enantiomer with an M configuration. And this is actually from the X-ray structure from this original paper. Actually, after we asked for the crystallographer, you can see these 2 methoxy groups are well, like separated by 2.8 angstroms, and we can, resolve this derivative. And actually, initially, we used the chiral ions of the group to resolve these compounds, and we discovered that the racemization for this very small 4-helicine and these 2 methoxy group is actually higher than the 6-helicine. So these compounds are extremely conformationally stable. We were happy with this. How do we resolve these compounds? Well, we use the chiral auxiliary, a classical sulfoxide that doesn't interact, of course, with the cation. But if you deprotonate these compounds with LDA, it becomes sufficiently nucleophilic to add to the center, and you get a 1-to-1 mixture of diester isomers. Sorry if it's not very clear. This diester isomer, this is its solution. This is the second one. So it means that you can really separate this compound on very large scale. And then you have 1 diester isomer in your hand. How do you actually break the CC bond? And we basically discovered a reaction that did not exist before. This is the Pummerer fragmentation. When you will cleave a SO bond by adding an electrophile or an acid, usually you need to provide to the sulfur the 2 electrons that it loses. And this is by a loss of a proton. These carbocations has a pKa plus of 19. It means that they're 10,000 times more stable than a proton in solution, or they are 1 lakh more stable than actually a proton in solution. And that makes it the driving force to form the cation, which is then an enantiopure. So I'm going to skip many, many years to essentially show you only very recent results with this chemistry. Okay. So what we have discovered, and I hope it works, is that these compounds, despite the positive charge, are extremely nucleophilic, and I'll come back to this. So when we add electrophiles, they will come kinetically on this position. And if you take the kind of Ola type conditions or Phil Eaton's superacid conditions, the electrophile very often comes out and recomes at this kind of position. And this is actually quite intriguing in terms of mechanism. What I will present actually now at the end is results which are actually in revision, where we go not only to the cation, but even to the radicals and the persistent radicals nowadays with this kind of chemistry. But before all that, I need to actually give you a bit of an update on another class of compound, which is the 6-helicines, which are here. And we call them, and then you will see that this part usually is nucleophilic, which means we can add 2 electrophiles. This part at the bottom is electrophilic, and you can add nucleophiles. This is actually, and you can completely change also properties. Okay, let's start with this. So this kind of carbocation is really made by really standard organic chemistry. It takes 5 steps. We usually start with the 10 grams of the 1,3-dimethoxy benzene. We finish with 5 grams usually of the carbocation. It takes 5 steps, really done in a week in the group. Then it looks like horrible conditions, but these conditions are still extremely practical. well, okay, in order to form, for instance, the dioxocarbocation. It has already a relatively low energy absorption, low energy emission. The properties here are not very good in terms of actually lifetimes. But when you substitute it by a nitrogen, you start to improve. The stock shift is better. But the workhorse of the chemistry usually is done with the dinitrogen compounds, which is actually a relative low energy absorption, low energy emission. But now the properties, the lifetime is really good, like 10 nanoseconds. For photocatalysis, it's very important to have also a long lifetime, of course, in the excited state. Quantum yields are always given in my group in polar solvents in presence of oxygen. We don't play tricks to go to cyclohexane and degas 10 times. We want to give, in a way, real values, which are actually useful. Then, okay, just this is the pKr plus. Again, these values which shows how, in a way, carbocationic, how electrophilic a carbocation is. Then when you compare these extreme values, extremely stable derivative, and then this one, this compound looks like not so stable. I'd just like to remind you the pKr plus of the compound, which is usually presented as one of the most stable compounds, the compounds of Ron Breslow, or for those who like physical-organic chemistry, Moss, who was one of the genius of physical-organic chemistry, with the cyclopropyl compound is just 9.4. So we have extremely stable carbocations. Okay, so now we form this 6-adenosine with the 2 nitrogen. If you imagine now this kind of compounds, you have one ring which is much more activated by donor group with the 2 nitrogen than all the others. And in fact, it will react with classical electrophilic conditions to put 2 chlorine, 2 bromine, 1 iodine, 2 nitro groups. So we can do regioselective functionalization. And this one is actually one of the first papers where with adenosine, you can really target and put groups at really specific positions. Now, in my group, very often I like to challenge students with things which are impossible. And then I told the students, hey, look at this compound. This ring is nucleophilic, but this ring could be electrophilic. Okay, I know there's a nitrogen, but this one feels more the positive charge. And we found one set of conditions where we could add nitrides, okay, add cyanide to make nitrides, but we tried, we failed essentially after this example. And again, it's because the carbocation is essentially very stable. Now we dial up the reactivity, the electrophilic reactivity by going to a strong pKr plus, and we started to discover that C-nucleophile like indoles start to form actually the CC bond. We add a bit of oxidation, of course, and then after 3 hours, actually, we even started to see the double addition, and that immediately led us to imagine a self-immolating process when a single step you're going to make a cyanine. We can even start from an imine like Unix base, okay, to form the mericyanine. This is a one-pot, four-step process where the cation is both the electrophile and the oxidant. But better, thank you so much for presenting this chemistry, okay, we can use indolenine, and depending on the conditions, we can stop at the first addition or even go to this double addition, and I will show you this. So mechanistically, I'm just going to concentrate on this first step, just to show this is the carbocation, this is the tritar group. It can obstruct an hydride, and if it does this on this kind of amine, you form the enamine. Okay, so the first equivalent just for the oxidation. The second equivalent here is as an electrophile, and you will have the enamine attacking immediately here at the para position to form the de-aromatized helicine. So we cannot see this intermediate. This compound immediately wants to get reoxidized because this sp3 carbon is not favorable, and we have a third equivalent of the cation, which gives you now actually this intermediate, this iminium ion, with the excess of Unix base in solution, just is deprotonated to give you the enamine. And now you have a donor acceptor compounds. And so, not surprisingly, this is the initial carbocation and its absorption. What you see is a hyperchromic shift, okay, as you expect, and also a batochromic shift actually toward the low energy. These two compounds behave more or less the same, but of course, when we reach this derivative, we start to have a relatively strong, of course, absorption. And here, the emission is very, very, very weak. We had to go to very sensitive, actually, machine to measure it. But when we do the electron density difference plot, we see for this carbocation, it's essentially a localized carbocation as we expect. When we add the donor group, we start to see actually the donor accept the situation. And here, for the last derivative, we clearly see a cyanine character being developed just in one go, okay? So now, it's not only a cyanine, but it's a carocyanine. We looked in the charoptical properties. We can have now delta epsilon values, which are actually at low energy in the near infrared, which are not negligible at all. Actually, but if you remember the epsilon values, whoops, sorry, something is missing. The G-apps remains relatively small. It's not bad, but we can probably do better. And I would like to make diester isomers. Maybe we can talk between Pune and Geneva of a collaboration, okay? Now, these 6 allicin have a one dirty secret. The resolution cannot be done with the sulfoxide chemistry. It has to be done by HPLC. And at the end of the day, it's 5 or 6 steps. So how can you do better? Is to go back to the 4 allicin chemistry. And this took us some time to understand how to solve the situation of the functionalization. When you treat this compound, and I just realized I'm missing one slide, with NBS, you get 10 compounds in solution. It's a horrible mixture. And the main reason for this is these compounds are so nucleophilic, is after one bromine, it has a second bromine, and then you get regioisomers. You see a third bromine coming in, you get mixtures of compounds. So the trick, and it took us some time to find it, is make sure that the first substituent that you add is a strong electron withdrawing groups. You kill the next reaction, which is the next substitution. So then you can put an aldehyde by a Wiesmeyer-Hack process. Actually, we do it on 5 gram scale. It's 85% yield now. And once you have an aldehyde, you can get a nitro group. You can get a Heuer-based Knoeveler Wittig chemistry. The best group to introduce is just really a nitro group. Okay, the nitrations are quantitative. Of course, you can reduce it. You can do Heschweiler-Clark chemistry, reoxidation to azide. You can do click-type chemistry, and so on and so forth. I will not go into the properties induced by these various substituents. I will just show you one supramolecular actually applications. Once we have the aldehyde, we can do a pinic oxidation to the acid, and then we can, for instance, put a relatively well-organized squalene type chain. And when these compounds are dropped, whatever the counter ion in pure water, okay, on the strong spinning, we form lipid droplets. Not vesicles, we really form purely lipid droplets. This is TEM, this is cryo-TEM, this is the dispersion actually that we have. And what is very interesting, these nanoparticles, we don't see the size evolve over time. There is no Ostwald repeating for these compounds, and that's probably due to their actually essentially cationic nature. They repulse each other once they've been made. And I think this is actually also a very interesting result. Okay, now, for those who knows, I love carbines, okay? And this is the other side of my group. There are 2 groups. It's a bit like schizophrenic. And so one day, the Swiss National Science Foundation said, okay, we give you money, but try to find a way that the people doing like the helicin chemistry talk to the people doing the carbene chemistry. Okay, so we took this helicin, and we had the idea is, can we functionalize this type of compound, reduce selectivity again, but also chemoselectively, and do the addition maybe once, twice, 3 times, 4 times, and then control, for instance, the acidity and all the properties. And we were able to do this very recently. We used malonate, actually, a diazo compound as precursors. And if you look at it, we just add the rhodium, basically catalyst that we saw with Anbarasan, 60 degrees, 3 hours, and we get a horrible mixtures of derivative, 1-to-1 ratio here, and even a lot of the double addition process. So we failed in our initial attempt. But when we do usually carbene chemistry, we have a trick. We love the CP ruthenium compounds, not the CP star, not completely like Anbarasan, but these compounds, and with this ligand, we can also modulate the electrophilicity of the ruthenium. What we discover is that this carbene chemistry is totally reduced selective, complete monofunctionalization. The mechanism is very interesting. I have no time to discuss it. But if you remember that with the rhodium, it's possible to access actually the position here. So we put a first compound, we put a second one, and no problem, we can put mixed derivative, we can do things one pot. In one pot, we even make this compound 80% yield. And then by going to even more acidic rhodium, we can put a third compound. The fourth one is difficult, but we could make it. So, okay, how do I fare with time? 5 more minutes. Now, at the end of the day, we can put substituents here, we can put substituents actually these kind of positions. And all these positions, if you look at it, actually are where there is actually density for the HOMO and a node for the LUMO. So in terms of HOMO-LUMO gap, we are playing essentially on the HOMO, and we're not touching the LUMO. However, if you imagine that you can put substituents at these positions parallel to the positive charge, we will do exactly the opposite. Playing with the LUMO, not touching with the LUMO. So can we do this? And of course, to do this chemistry, we just realized that the position highlighted here in purple are the less hindered position. And when you want to do CH functionalization on the steric conditions, you think about the beautiful John Hartwig chemistry with the iridium catalyzed actually process with B2P2. And here in our case, we don't want to deal with rigid selectivity. We just put 3 boron derivative. This was the easiest for us. Once you have formed this B-pin, you can do Suzuki-Miura coupling, okay? But we thought much more important to put polar groups. So in one pot, in 90% yield for the 3 borylation, for the 3 hydroxylation, on the 5-gram scale, we can introduce 3 hydroxyl groups. It's a bit more complicated to do the Yoshinori Yamamoto, okay, of Sendai chemistry. We can do it on a 500 milligram scale, 1 gram scale with carbon monoxide and then methanol, but we can make the 3 esters in one pot, okay? Now, once you have the hydroxyl group, you can just alkylate, nothing special with this. You can make a triflate, but a triflate is a great living group. So look how we make chlorides now. We just put tetrabutylammonium chloride, and we can replace the triflate by addition elimination. We had beautiful chemistry, thank you, Suresh, with sulfinates. Here, this is not radical, but this we just alkylate with the sulfinates in order to make these compounds or many others. So now I'm going to tell you for the last 5 minutes a story, whoops, sometimes it goes too quickly, with these 4 derivatives in comparison with the precursor. We put electron withdrawing groups, and unlike actually, even if I have not shown you the previous substitution, when we put this group here, we have a very strong, actually, redshift. The quantum efficiency, which was 14%, goes down to 5%. It's not very good, but it's not that bad. When we look at emission at 700 nanometers, it's okay. But now, when we put this donor group, we are blue shifted. This is the opposite. But the quantum efficiency of these compounds is absolutely amazing. We have really 70% quantum efficiency. And for small tritar group, it's not too bad, actually. The chloride are tricky. And if you just look at the optical gap, it looks like they're just like donating group. But of course, I will show you that the electrochemistry will tell us a different story. So these compounds, and sorry again, these compounds are, now really pretty different, actually, optical absorption properties. In the emission, again, this is in this series that we're actually doing better, not so surprisingly. Sorry. I thought you have to be patient. You have to press, and sometimes you have to wait for the next speakers. Okay. So the take-home lesson is, sorry, you don't really see the colors. There is the absorption spectra in the back. We do the circular dichroism, some weird stuff going on. But globally, we have relatively weak GAPs. And this is quite classical with the 4-adenosine compared to the 6-adenosine. But you will see how we make a difference. This is actually the carbocation. And this is actually the gap we see in cyclic voltammetry for the reduction here on the left, the oxidation of the right, which is purely reversible, okay? When we put the electron withdrawing group, not surprisingly, the reduction is much easier, either with the sulfone or with the esters. This is much better. The oxidation becomes more difficult, and that explains the electronic gap, which is reduced This is not so surprising, and hence also the optical properties which are shifted. Now, by putting the donating group, we do exactly the opposite. Reduction is more difficult. The oxidation doesn't change so much. The HOMO doesn't change, so it's not so surprising. And so the optical gap increase. And as usual with the chloride, do the electrochemistry before you conclude everything from the optics, okay? Because this time, of course, these are stabilizing agents, but it's just that the HOMO is more destabilized than the HOMO, and hence the optical gap, which is actually higher than the group. So there is a very strong focus nowadays on open shell molecule. If you do material science, if you look at the OLED field, for instance, people are doping essentially most of the OLEDs with really minimal amounts of chiral fluorescence radical. So we wanted, for instance, to study this. 2 minutes, 3 minutes? Oh, it will be done. Okay, so Larsen published this compound in 2014, and we decided to look at the spectroelectrochemistry of this compound. So we decided to do a reduction and do an oxidation. And what you see here, this is not reversible. So what happens now with actually the triester group? So this is the cation at the part. We reduce. We see a very clean now spectrum, and we reoxidize. And we can do this 17 times actually over 1 hour, either for this band, which is purely, mainly the carbocation, or this bench, which is purely actually the radical, and it's really, really clean. Now, we have done also, of course, the same thing for the sulfone. I don't show you the spectra for the sake of time. But look at this absorption now for this kind of compound. The absorption are totally shifted in the near infrared. And very importantly, the G-apps, we gained a factor of 10 actually by making the radicals in terms of chiroptical actually enhancement for these kind of radicals. The radical is most essentially the SOMO to LUMO transition. We see a little component from the HOMO-SOMO actually in this kind of actually transition for the radicals. More importantly, we did the APR. We can really completely actually explain by theoretical calculation the APR both on the trisulfone and the triester. And the final, scientific slide just shows actually that once we made this measurement, we open to air actually the samples, and the half-life is around like 5 to 6 hours, either for the sulfone or the esters. So for these compounds, actually in presence of air, they are not stable radicals, okay, but they're pretty persistent radical for this kind of really, really like strongly bridged compounds. So I hope it was interesting to you, this type of chemistry, okay, for these kind of new carbocations and new radicals. The people who've done the chemistry, which is more important, are actually Johan, Romain, Bibiana, Luca, Géraldine, Yana, Pao, Simon, and Frank for the chemistry I showed today. This is the group this summer. There was a picture of the group this winter with beautiful snow, not so far from Geneva. Funding comes from essentially the Swiss National Foundation, University of Geneva. Thank you again for the invitation. Okay, Siva, thank you for your kind attention.
Excellent presentation and the beautiful chemistry. We have time for just one question. Yeah, please. You can go. Me? Yeah.
Yes, Sankar.
So I was thinking, why to waste 2 equivalent of your costly material by hydride acceptor? Why don't you use oxidant?
Well, we can. Oh, the best is I didn't show this. I went very quickly. We just put light. We can reoxidize. However, we don't get byproduct, and it's much. You get a much.
You are reoxidizing it.
Yeah. If we put light, we just actually and then an oxygen. You reoxidize the compound to the cation.
And you can.
But at the end of the day, the yield only goes to 50 or 60%. So you get your 33% yield, exactly 33% yield. You separate, you do it again, and you do it again. And after 3 cycles, you have 70% of yield.
Okay.
So it's actually much cleaner.
But one pot oxidant is not working.
Well, we use iodine. We use sometimes some other trityl derivative as themselves. So the 1-methoxytrityl or the or paratrityl or this There is a ChemCom paper on this kind of process. So you can trick the system with another triethyl as an oxidant. Okay, but here it was just so beautiful to use the same compounds to do everything. Actually, the referee didn't mind.
One more last, related one. This cyclic enamines, when you use the cyclic one, the indolines one, the double bond geometry, have you checked?
So
carefully?
I went very quickly on this. The NOE is perfect. Okay, the NOE is perfect, and the indolinyl ring, is really, really strong. However, what I didn't say, there is motion.
Okay.
And so even if the helicin is M, we see both P and M configuration. So we have a conformer little issue. We have several ideas to solve this through diisomeric, maybe compounds with even longer chain could also help. Maybe change some of the geometry of the things. We have to engineer things. But thank you for this.
Yeah, I have another question that we'll discuss later on the rhodium carbon things.
Yeah.
Nitrine things.
I would be very happy to see that.
Please give a high upload to Professor Jerome for his wonderful presentation. Okay, we have the next speaker again from IISER Kolkata. He is in fact second speaker from IISER Kolkata, Dr. Suman Desarkar, who received PhD from University of Munster with Studer. Then he had a couple of postdocs in Basel and University of Göttingen with Professor Lars Ackermann. He joined IISER Kolkata on 2015. Then he is right now associate professor, and he has received numerous awards, including Theme Chemistry Journals Award in 2023. Then he is also a member of Early Career Advisory Board of ASIAN Journal of Organic Chemistry. So with this short introduction, I request Suman to start his talk.
Thank you very much, Professor. It's a really great pleasure to be here, and big thanks to the organizers to arranging this such a fantastic forum to discuss the science. Special thanks to Siva, Suresh, and all other colleagues. I'm really touched with the hospitality. When we reached the airport yesterday, he personally went there to receive us. He accompanied us in the dinner, and this morning also during breakfast he accompanied us. I think the whole way we'll stay. We'll see this hospitality. I'm really touched. And this is really a perfect example of, in Hindi, it's called Mehman Nawazi. Yeah? So it's something to mention. All right, so coming back to chemistry, although I put a very fancy title, but basically, as you can guess, I'm going to tell you about the chemistry of enamines during electrolysis. All right, so this is the thing I'm going to tell you today. Before going to the exact topic, let me briefly introduce our group. We called ourselves as a Redox group. This is our group logo, and the theme of the group is develop organic methodology based on two transformations. So red means the reduction, and then ox is the oxidation. So we focus on these two basic transformations and develop organic methodology. And in terms of redox, there are 4 different tools that we are using. The one is the photoredox, the redox using light. Thanks to Suresh, he already introduced this chemistry to the audience. Second is this hydrogen transfer chemistry, because by definition, giving hydrogen to a molecule is reduction and taking out is oxidation. We make use of it and then use this chemistry to develop several methodology. The third one is more classical one, using stoichiometric amount of redox reagents and develop methods. And the last but not the least is doing redox using electricity. Okay, so and now our major focus is on this field where just by switching on the current, you can really do redox chemistry and develop methods. Today time is very, very short, so and I'm not good in telling too many things at the same time. So I will restrict myself in this northwest corner and tell you a couple of stories that we developed in our laboratory. So let us start. We have already seen a couple of presentations on electrochemistry, but our electrochemistry is quite different from those. So basically,
specifically mentioned what we are doing is organic synthesis. So that means we call this electrosynthesis. And the setup is like this, like an electrochemical cell where there is one anode and one cathode. And as you know, anode is the positive end, so it's hungry for electron. And when it passes electricity, it takes the electron from the substrate, generate this reactive radical cation, and in subsequent step, it can give the product. And exactly opposite things happens in cathode, which is rich with electrons. When the substrate comes close to the cathode, it gives electron to the substrate, form this radical anion, and in subsequent step, it can give the product. And it may happen that sometimes that this direct electron transfer through the substrate is difficult. It's a high energy process. In those cases, we need some mediator, which is basically nothing but the catalyst. So this mediator can take electron from this radical cation and then go to the bulk solution and then interact with the substrate and generate the very similar radical cation type thing, and then subsequent step it form the product. Okay? So this is the very basic concept of electrosynthesis that we are practicing. Now the next and obvious question comes is why electrochemistry, right? So this morning, Professor Essien was mentioning about sustainability. So this is one answer is, of course, in terms of sustainability, because if you open the textbook of any standard organic chemistry, so you will, as an oxidant, you will see all these permanganates, dichromates, and so on and so forth. And using these, it's really generate lots of byproducts, right? So here, as you can see, we can really take out electron and then give the electron and doing the redox chemistry, oxidation and reduction. So you can, in terms of green chemistry, it's really a solution, right? So these things are there. But when we started our journey on this field a few years back, we asked, of course, we can do that. So we can make the processes, organic processes, much more greener. But what else? Can we make something more out of this electroredox chemistry? Okay? And one of the major focus of our research is always rely on this to develop or find out new reactivities and chemoselectivity. Okay? So which is not possible based on reagent-based chemistry, but we can make it possible using electrochemistry. Okay? So with this notation, I'll tell you a couple of stories. As I mentioned, one of my very talented research scholar, Minmoy, so he focused on one functionality and tried different reactivity, find out different reactivity under electrolysis. And that functionality was nothing but these enamines. As you know, the enamines are known as electron-rich intermediates, so where the electron density relies on nitrogen and carbon, and in presence of suitable electrophile, it can react and form these, and ultimately the enamine part is functionalized, right? So this is also part of organocatalysis that Professor Sekhar was mentioning this morning. Alternatively, what you can do, you can take out one electron from enamine and can generate this kind of radical cation, which is now not nucleophile anymore. Rather, it behaves more like an electrophile and prefer to react with different nucleophiles and give some chemistry. So when we started this project, Minmoy's job was to utilize this functionality or these reactivities of enamines and check can we extract new reactivities, and especially in the formation of new heterocycles, useful heterocycles under electrochemistry. Okay? And one thing, as I mentioned previously, one focus of our group is always there is to find out chemoselectivity, which is not possible under reagent-based chemistry. So in terms of chemoselectivity or achieving chemoselectivity, we took one initial project that was very challenging. We focused on the synthesis of these pyrroles, but these are the special kind of pyrroles. As you can see, the C2 position and C5 positions are functionalized, but one side is aryl group and the other side is alkyl group. Okay? And this special functionalization or substitution pattern is common in many biologically important molecules, including this blockbuster drug, which is Lipitor. Okay? So we realized the importance of this and checked the literature, and there are reports, of course, because they're important molecules, there are reports to prepare these. One of those to mention here by Zhao group. So they use a beautiful photoredox cycloaddition chemistry to break this bond and prepare this unsymmetric pyrrole moiety. But the problem here is the unavailability of the starting material. The starting material itself is very fancy and it takes 4 or 5 steps to prepare. So it's not practical. So what's the solution? Solution can give our old good friend enamine. Okay? So it's known that this enamine can react with each other under oxidative condition. 2 of the enamine molecule can dimerize and form a pyrrole. But problem here is it's a dimerization reaction. So there is a bunch of report under oxidant, it can dimerize, but problem here you see both sides, because the dimerization, both sides it will be symmetric, right? So symmetric pyrrole you can make, but not the unsymmetric one. Our target is to prepare unsymmetric ones. So we tried our luck and put some reagent chemistry that can this semiacidic ammonium nitrate. And what we found by mixing 1 equivalent of this aryl substituted enamine with 1 equivalent of alkyl substituted enamine, of course, we got some desired product, but there is a hell lot of byproduct, which is the dimerization homocoupling of enamines. Okay, so we realized that it's a challenging task, and that the solution is like this: that when we are using 2 enamines, we should not allow both the enamines to get oxidized. So there must be a chemoselective oxidation of one of the enamines, and then once it gets oxidized, it's becoming more like an electrophile. Then the nucleophilic addition of the other enamine should not be the same one, it's the opposite one, okay? So that means the chemoselective addition. And the third, of course, the quite obvious, the cyclization and release of one ammonia molecule, okay? So this is the challenging task, which was, as I mentioned, was failed with CAN, that means the reagent-based chemistry. But I'm glad to mention that we could achieve that using electrochemistry. We solved step by step with thorough background study, and then a lot of control experiments. We solved all these steps and ultimately achieved the selectivity with very good selectivity, and then this homocoupling was reduced to a very negligible amount. But this is a beautiful chemistry we developed a couple of years back, and then in recent forums I already presented. I think many of my colleagues already heard me in speaking the details of this study. So today I decided not to discuss this thing in more details. Rather, interested people can read this paper for the details. What I will do, whatever time left I have, I will tell you a couple of more stories on the reactivity of enamine that Minmoy developed. So the next target that Minmoy took was another heterocycle, that was this triazole. And once the triazoles, I say, probably you are thinking about click chemistry. But in click chemistry, as you know, whatever triazole we are making, there the aryl group or the substituents is on the terminal nitrogen. But here you see, these are N2 aryl triazoles. That means the substitution is on the methyl nitrogen. You cannot make that using click chemistry. So what's the solution? People use diazonium salts to prepare that, and there are quite some report. But if you use diazonium salt which has 2 nitrogens, so there is a mandatory requirement of one's NN bond coupling. Okay? And people largely depend on metal catalyst and then use the reductive elimination here to form this NN bond. And copper was extensively used there. But in our research project, in terms of sustainability, so we really wanted to avoid metal. So what's the solution? So we wanted to have a completely different mechanism and rely on to generate a radical cation intermediate. And we thought that this intermediate will enable us to make this NN bond through radical cyclization and without any metal. Okay, so that was the hypothesis. With this idea, we started our optimization. Okay, and this is, I don't want to bore you with this. So this is after a lot of optimization, we found this is the best possible combinations of electrodes and all these things, other parameters. Once the optimization is done, we're good in cooking organic chemistry, we're good in cooking, we cooked up a lot of stuff. And there are many, I just showed you the selective ones. And here we varied the enamine substituent. We also cooked molecules with the variation of the diazonium salts. You can see essentially we can use any diazonium salts. The alkyl one we cannot use because alkyl diazonium salts are not stable. But in terms of aryl, you can use anything. Even this bulky mesitryl, you can see with very, very high yield, very, very, very effective method this is. And look at the reaction condition. It's so simple. So you just take the material, put it in a beaker, dump it under air, put some acetonitrile, and put some electrode, switch on the electricity. 1.5 hours later, you'll get the product. Okay? With very high yield, so the separation is so easy. All right. So what's happening here? Whatever our hypothesis of radical cyclization is actually happening. So we did some mechanistic studies, which are always we prefer to, and we give importance to the mechanistic studies. What Minmay found was some observations are important and interesting, that if you use a base, then the reaction yield becomes very low. And then he checked the pH of the reaction. And then he found with the progress of the reaction, the pH really goes down, I mean up to 3. Okay, so he started at 6.5 and with time it really goes down. Few more observations, because what he found that when he took these materials without electricity, without switching on, some precipitate is coming out. Okay? So before switching on, some precipitate is coming out. And then he waited for 30 minutes, more precipitate came out, and then he isolated. Okay? And then we really fully characterized that we found that before the electrochemistry is starting, these two guys are combining each other and forming this salt. And this salt he took and then did the electrochemistry and found very high yielding outcome of the desired product. Okay? So that means this is basically the intermediate that we have, which is actually getting oxidized. All right. And he also did different, because as I say, open to air, we did the reaction. So he did in presence of oxygen and argon, and both cases these results are quite identical. So basically, we need electrooxidation. It's an oxidative process. It's not via air or the aerial oxygen. So that is what we proved. So this is the mechanism. I will go quickly. So there are two different possibilities. I will go my favorite pathway. So this is the thing we isolated, right? So this is happening initially. And then there's the 2 tautomeric form is possible. This part is more electron rich, is like a hydrazone type thing, so electron rich. This is getting oxidized. And this is the key intermediate, the radical cation. And as I mentioned, that base is reducing the yield. That means this protonated version of this enamine, the iminium ion is important or necessary for this radical cyclization, which is happening the NN coupling, and then from this, and then after that it's trivial, one more oxidation. And here, as you can see, if you match the stoichiometry, we are releasing one molecule of HbF4 molecule. That's why the pH is slowly going down. Okay? So with this, the last story I will share, which is on another heterocycle. Okay? So what so far I showed you. So this is the pyrrole story, this is the triazole story. Then after these 2 intermolecular coupling, we thought to do some intramolecular coupling. And this alkyne, we tethered with the nitrogen of the enamine, and thought that once we oxidize these, we form this radical, and Professor Ramana already beautifully showed us some cyclization of win alkyne using nitro. So we thought we can do that, a radical cyclization, and then form these pyrroles with a keto group or carbonyl group at C3 position. Right? So that's the idea. But the problem here we found when we charge this molecule under electrochemical condition, so our child is giving us trouble. No? So we developed this method of making pyrroles through the heterocoupling or homocoupling of enamines. So 2 molecules of this is coupling and giving us this kind of pyrroles. Huh? So not the desired intramolecular one. It's there, but pretty low yield. So we realized that we need some activator to activate the alkyne to make this cyclization more preferable. Professor Ramana has a lot of money, he can use gold, but we are poor fellows. Just kidding, we also use gold for some other project. But this particular one, our focus was on using develop a metal-free method. So what we did, we plan to use these seleniums, okay? Selenium catalysis. So these seleniums are known to be catalyzed and used as once under oxidative condition, it forms these selenium cations, okay? And those are very good pi-Lewis acids. So it's very selectively activate triple bonds, and we wanted to make use of it. Even under electrochemical condition, there are reports to activate this alkyne. So basically it's a hydrolysis, okay? So normally alkyne hydrolysis we do using mercury or so. So using this selenium catalysis, you can really do it using very selective and sustainable way. So this is our hypothesis. So that thought we will generate this selenium cation under electrochemical condition, and then this will activate the alkyne, and then cyclization will take place, and then we'll form this intermediate, and then further oxidative hydrolysis will give us our desired product. But here also the challenges are there. As you can see, this chemistry was developed by May, that the triple bond can get hydrolyzed. So before cyclization, it can get hydrolyzed. So this is a byproduct formation. And of course, our old good friends are there. I mean, this dimerization of enamines, that's challenge is also there. Okay, so with these things in mind, we started the optimization. Again, so I will not bore you with all the details. So what we found, only 10 mole% of diphenyl diacetylide, which is commercially available. We put there, the reaction becomes very easy, and then the desired product was formed in very high yield. And good thing is that undesired pyrrole, the homocoupling of the enamine was not observed. Again, once the optimization done, is the part of cooking. 18 example we cooked, few of them were shown here. So here is, I can see that here we basically varied the group on alkyne. So we formed all the aryl and alkyl group. We formed the ketones here. Okay, so this carbon is actually coming here. Okay, so all different kinds of carbonyls. I mean, specifically mentioned the ketones we prepared, and even the aliphatic ones. Next, we tried the terminal one. Terminal one will give us the aldehyde. So, I have to mention here, this carbonyl, the aldehyde on pyrroles are quite sensitive. Okay, so because it's very easy to oxidize. Pyrrole ring itself is electron rich, and it's quite difficult to prepare using other method. But in our case, we found very easy access to all these derivatives with high yields. Okay. So something more, actually, this is out of enamine, but kind of enamine equivalent. So you can again activate and then cyclize to form these oxazoles. To make it more practical, yes, yeah, I'll finish in 4 minutes. Make it more practical, we can use, so previously what we did, we used this pre-made enamines with alkynes, right? So we can really do it one pot. We can mix these two, okay? So you just mix these two around evening, go to home, have party with your friends, and then have a good sleep, dinner, sleep, and the next morning you come. Yeah, so then, but before breakfast, you come and then put 10 mole% on the same reaction pot, put 10 mole% of diselenide, put some solvent, switch on the electricity, then you go for breakfast, chat with your friends around 1.5 hours or so, or 2 hours, 2.5 hours, and then come back and then do the column. So then you get all this in very good yields, okay? So that's the suggestion. And we can always do that in higher scale. So making in larger scale is not an issue here. What's in terms of the mechanistic study? So we did the CV, and we found that diselenide is getting oxidized before the enamine. And some more mechanistic study quickly, that as you can see, there is oxygen coming in the molecule. Then what's the source of oxygen? So what we found that basically if we use dry acetonitrile, then the reaction is not working, and even under air. So we concluded that this oxygen is not coming from air, rather is coming from water. And then as we are claiming this as a selenium catalysis, so we thought to use a stoichiometric amount of selenium, and we indeed can isolate the intermediate of the after incorporation of selenium, and then under oxidative condition we can generate the product and release the diselenides. Okay, so I'll finish in a minute, and just to mention that electrochemistry is really necessary here. Other oxidants, the chemical oxidants, fail to give us the product. So here's the mechanism quickly. This diselenide is getting oxidized, activating here cyclization, and then we are getting this intermediate that we have already isolated, and then we believe that there is a anodic oxidation and basically oxidative hydrolysis, and the water is coming and then adding here, and ultimately the release of the selenium cation and tautomerization giving us the product. Okay? And in cathode there is a hydrogen is going out to maintain the electricity. So far, just to conclude here, so this is the story I have told you. This is the story I also told you, the selenium catalysis on alkyne I have mentioned, which I did not get, and I also did not plan to show you in details that the chemistry of alkynes, which is quite obvious after alkyne, but we found the outcome is completely different. Here we got this carbonyl, but here we could prepare these beautiful bicycles, 3,5 and 5,5 depending on the R group here, And here also selenium catalysis did not work well, rather this iodine catalysis we have to use to make these bicycles. Okay? So this is under consideration, soon will be published, and please check in our website for the updates. With this, I'll finish, but not before thanking my students. So I'm really fortunate to be surrounded by these very talented individuals. All the chemistry I've shown done by single-handedly by Minmoy. This was part of his thesis. Thanks to my collaborator, Lisa, she did a lot of DFT studies, which I did not get time to show, but she is always helpful to give us insight of the mechanism. They're the funding agencies, and of course, thanks to my parent institute, IISER Kolkata. Thanks again for your patience hearing.
Sustainable chemistry. So we have time for just one question. Ramesh.
Yeah, fantastic work. Yeah.
Thank you.
So when you discussed about the enamines with alkyl and aryl substitution, how different is the oxidation potential so that you can distinguish really, during the oxidation?
You mean these two? Alkene and alkyne?
So you had
the... Oh, no, the initial one.
Yeah.
There is the trick, actually.
Because it's, for me, it doesn't look like too much difference.
Yes. But actually not. Actually not. It's quite close.
But how did you manage to selectively oxidize only one enamine?
A very simple solution. Ultimately, we found it's a simple solution. We just had to add an additive, trifluoroethanol. And trifluoroethanol really worked as a magic for us. Okay? So what happens that it goes for non-bonding interaction with the pi cloud of aryl 1 and really dragged that the oxidation potential lower, much lower than the alkyl one.
That's very interesting.
Yes, yes,
and
yes.
So maybe, you can probably add a little bit more comment on why not, using the photoredox. Will it, do you see any difficulty in handling with the photoredox system?
Photoredox, of course, there are advantages, disadvantages. We are also practicing photoredox, as you can see. But in terms of chemoselectivity, in this particular case, we found it's difficult because, if you use a photocatalyst and then it has a certain oxidation potential, and then whatever below that, it will oxidize. And very difficult to, when there is small difference between two potentially oxidizable substrate, it's very difficult to distinguish. And it's very difficult to get something in between,
Yeah, that's true.
Yeah.
And by the way, how did you identify?
But electrochemistry, you can really tune the current flow and then the potential. It's just by, tuning.
Probably we can discuss more in the dinner time.
Yeah, definitely.
So with this, I would like to thank again Suman for a wonderful presentation. So there is a small gift from the organizer side. Yeah, we have also a next speaker from IISER Kolkata, Professor Raja Sanmuham, who obtained PhD from IIT Madras with Professor Damodaran. And he had a postdoctoral studies from University of Massachusetts, USA. Then he joined IISER Kolkata in 2008. Then now he is a full professor. He has got a Ramanujan Fellowship, which is a very prestigious one. Then he had also multiple times he received a national award for technology innovation under the polymeric materials category. Almost 3 times he received runner and winner awards. So with this short introduction, I request Raja to start his presentation. Thank you.
Thank you, Chairman, for the very kind introduction. Very good evening to all. First of all, it's my pleasure to thank organizer Professor Shiva for this great opportunity. I can see the friends coming all over the country and also teachers, respected colleagues. With that, I start my presentation. Today, I'll be talking about engineering functional polymers for hierarchical self-assembly. Before I start my presentation, let me introduce what we have been doing in our research lab since 2008. Basically, I'm a polymer chemist. We practice making a lot of polymers in our group. We develop polymers for drug delivery application, and there are two categories there. When I mentioned covalent approach, we attach this drug to the polymer backbone through the stimuli responsive link, such as enzyme or pH. These are the stimuli responsives. When I mentioned non-covalent approach, we make amphiphilic polymer. We teach them to self-assemble into the very interesting structures like micelle and vesicle. Then we encapsulate the drug. That is called the non-covalent approach. We also make polymers for sensors, for example, heavy metals like arsenic, which is very heavily contaminated in the West Bengal and Bangladesh. We have developed polymers for not only for sensor, we also make material to trap arsenic in the drinking water. We have done a lot of research in this area. We also made a lot of polymers for sensing poisonous gas. Recently, we have started making porous polymers for channelizing the ions, for example, anionic and cationic channelization, so that these polymers can be used in the energy applications. So with that, today in my presentation, I'll be demonstrating a small work that we started with the sensing work, but that ended up with a very interesting hierarchical self-assembly structure. That story I'm going to tell. This is particularly for the students. We all, the self-assembly process, we try to mimic Mother Nature. So for example, chaperonin protein, if you remember the structure, it has a 5 protein unit nicely organized into spherical structures. Based on that, a lot of synthetically mimicking applications were developed. Similarly, Newcomb's structures and mushroom-like structures and Samstorm's antibacterial structures. These are all classic examples for mimicking the Mother Nature, and we develop synthetically important structures. And such example is listed here. And what are the driving force? When you make amphiphilic polymers, and based on the solvent condition, you can dictate these amphiphilic molecules into very interesting self-assembled structures, and that is listed here. For example, spheres, rods, lamellae, and cylinders, and so on. The driving factor is you need to have amphiphilicity in your polymer chain, and also you need to have a very nice environment so that you can dictate these polymer chains to behave as you desire. And particularly the rod shape self-assembled structures got a lot of attention due to the extraordinary surface volume and tunable thermal and properties. So the rod-shaped molecules recently getting more attention towards the application. With that, today's objective, we wanted to develop a polymer, and in the presence of analyte, can we fine-tune? That was the question we asked. Why H2S and sodium hypochlorite? I'm giving you the reason, quite well. We all know that H2S means very pungent smell, right? That's the immediate thing comes in our mind. That is coming due to the decomposition of all these food and animal bodies. That's how the pungent smell comes out of these things. But we never thought about its importance in the biological things. I found out these interesting data when I was looking back the literature on H2S. Up to 1980, the H2S was well known for its toxic smell and its pungent smell nature. But the historical manuscripts coming out that demonstrate that H2 has a huge biogenesis in our body, right? That's how it evolved, and that is listed in this particular graph. Particularly, the main sources for H2S in our body is cysteine, homocysteine, and 3-mercaptopyruvic acid. These are all sulfur-based amino acids that commonly used in our biogenesis. Particularly, if you see these amino acids role in our body, you can think of their application in the heart and brain, all nervous-related things, right? So these 3 proteins are very important, and that generates H2S in our body. But everything has its own limit. When it is overexpressed, then it causes the damage in your body. So what causes the overexpression in our body? Sorry. Yeah, the food habits, particularly the plant-based food keeps your side chain fatty acid level more and it reduces the H2S level very low. But if you eat a fat-rich food, then that increases your side chain fatty acid more and it causes the increased H2S in your body and it causes the outcomes are, we know, the disease and damage. What is the allowed level? That is listed here. When it is in the 1 to 10 ppm level, you can smell and that water comes in this region. When it is getting between 20 to 100, the eye irritation and those things. And when it is beyond 100 ppm, your heart disease, dizziness, and even leads to the death. So this is the allowed level of H2S exposure that one can avoid, okay? That is listed here. So it is necessary to sense the H2S. Of course, there are a lot of existing methods like colorimetric, chromatographic, electrochemical methods are there, and which is also listed here. The problem associated with the existing system are the limitation in detecting the H2S, and also these are all not capable of imaging at the cellular level. So we wanted to develop a sensor that works the lower ppm level, and also it should work in the biological level. That was the objective of designing this molecule. With that objective, we came up, sorry, I'm doing this mistake again and again. So we came up with this Narbonine system. Why we choose Narbonine system? Because it is polymerizable under the very, the catalyst that we use in this polymerization has a functional group tolerance. The Krebs catalyst, which has a Nobel Prize, has a functional group tolerance. It has 3-generation catalyst. You have G1, G2, G3, you can utilize. And what is the functional group tolerance? If you have a rich functionality, the catalyst will not interact and you can get the desired molecular weight. That is called the functional group tolerance. That's why we choose Narbonine as the backbone. And we make the sensing monomer. To make the system water dispersible, we also make polyethylene glycol functionalized monomer. After characterizing this thoroughly, then we go for this polymerization. This is a copolymer having both PEG-containing and sensor-containing molecule. We can vary the feed ratio. In that way, you can generate these sensor-containing polymer. So this is how we characterize the sensor-containing monomer. The NMR looks perfect for all these functionality. Similarly, this is the PEG functionalized monomer that we confirm through the NMR. Then this is the the NMR for the final copolymer, where you can see the signature of both monomers. After confirming the polymerization, we went for this selectivity of sensing the H2S of the sensor molecule. This is the, I'm so sorry. This is the absorption spectrum of the sensor molecule, and this is the emission spectrum of this small molecule, that is a monomer. And it is the detection limit where you can say that how lowest level you can detect. And this is the picture of emission of this monomer functionality. After confirming the selectivity at the monomer level, we use the polymer. And the reason for the selectivity is the excited state intramolecular proton transfer. That is the reason. When the sensor molecule is exposed to the H2S at the excited level, this keto-imine formation, that causes the reason for the emission. That is the reason we see the response after the sensor molecule exposed to H2S. That is the reason for the observed color. So after confirming the sensing capability, we used the same molecule in the polymer backbone. We also did all the selectivity and the varying pH. We have observed the same emission property for the H2S in the polymer backbone. The next aspect is a very interesting curiosity questions. Since this is an amphiphilic polymer, both polyethylene glycol and sensor molecule, which is rich in amphiphilicity, so we ask the question, do they form any self-assembly structure? And the second question, if it forms self-assembly, what is their role after exposed to the analyte? That was these two questions we asked. And as this is the amphiphilically rich in nature, we could see from the critical aggregation concentration, these molecules are self-assembled in water. And the same solution is tested for dynamic light scattering that shows the size of about 150 nanometer. And when these solutions are casted in the SEM and TEM analysis, you can see that these are all, oops, again, this. These are all spherical in nature before get exposed to the analyte. After passing it to the hydrogen sulfide, you can see that there is a complete change in the structure from spherical to twisted rod-like structures. That is a huge change from the point of self-assembly, right? And the reason we believe that after the exposure, the OH present in the molecule that is responsible for this hydrogen bonding that intercalate with the other chain forming this spiral-like ladder formation. That is the reason for this. And that observation is, this is the discussion summarized in this particular slide. Okay. So the next discussion, why we choose sodium hypochlorite? Because when there is excess H2S exposure, the antidote for H2S is hypochlorite. Sodium hypochlorite is given to stop the H2S, the excess H2S. In addition to that, our body also generates sodium hypochlorite in our body. And how we get overexpressed with the hypochlorite? There are several occasions. For example, when we do the root canal, the anesthesia, the anesthesia is given as sodium hypochlorite is given as the anesthesia. So in that way, our body gets exposed to the sodium hypochlorite. And in addition, from the food habit, hypochlorite is being generated in our body. That's why when it is overexpressed, the hypochlorite damage the DNA. Due to that, the bone-related and other diseases are happening. That's why we need to monitor at the cellular level the overexpressed level of sodium hypochlorite. And we designed this particular molecule for sensing sodium hypochlorite. I did not go through this detail because in the previous section I discussed in detail how we start from the monomer and we polymerize, then characterize those that I skipped in this section. And this is the polymer we have developed for sensing hypochlorite. And I will straight away show you the results. As you can see, this molecule also rich in amphiphilicity. You can expect this molecule to self-assemble in the aqueous condition. As we expected, it is also forming critical aggregation concentration. The same solution is tested for dynamic light scattering, where you can see the observed aggregates are about 150 nanometer in size. When it is tested in the SEM and the TEM, these are all spherical in nature. And after this hypochlorite exposure, again, it is very interesting to observe that these also becoming twisted rod from spherical to twisted rod structures. This prompted us to explore the hypothesis, what would be the reason. Again, the OH present in the polymer chain that induces the hydrogen bonding and it forms the twisted rod. And we also checked the pH, what is the influence of pH in the observed hierarchical structure. And by varying pH, you can see that at low pH, these are all spherical, but in the basic condition and above pH, it become rod-like structures. And this is particularly, this is SEM, and we have also observed it in the TEM that clearly shows in the normal below pH, it is spherical in nature, and above pH 7, particularly 9 and above, it becomes twisted rod. The reason for that, you can see that it is very well supported with our hypothesis. There is in the low pH, the hydrophobic nature dominates, but in the high, in the basic pH, the proton in the related to OH gets removed, and the anionic nature of that sensing molecule is forming, which is relatively hydrophilic compared to that before sensing the analyte, right? So due to that, these chains are exposed to the water molecule, and the hydrogen bonding is favored effectively. Due to that, these spiral structures are happening. That's why from spherical to twisted rod structure happening because of this OH. The proton in the OH gets absorbed in the basic condition. That is the reason for that. That's our hypothesis. And our ultimate objective is to detect these analytes at the cellular level so that we can directly use in the biological system. And we can do that from the MTT, say, and the cellular structure. You can see that these molecules are not toxic, and you can even detect these hypochlorite and H2S at the cellular level that we have demonstrated. And this is our proposed hypothesis. These molecules are spherical in nature before analyting, exposed to the analytes. After exposed to the analyte, it becomes twisted rod. And what is the future direction? We have demonstrated that we could sense H2S and hypochlorite at the cellular level. If we have both molecules in the same polymer chain, the same polymer can be used for detecting both hypochlorite and H2S at the cellular level. Our further hypothesis is it is beautifully forming twisted rod, and these analytes are damaging the DNA. So if we encapsulate the DNA repairing small molecule along with this twisted rod and inject that, when it is exposed to these analyte, these polymer will help to become self-repairing DNA. So this model will help to repair the DNA. That is our hypothesis. Of course, this has a long way to go, but we are working towards that direction. We are collaborating with biologists. With that, I conclude my presentation, thanking all my past and present group. This particular work done by Narayan and Momita, who carried out all the work. I thank all the funding agency, and thank you all for your kind attention.
Full presentation, and we have time for one question, quick question. Yeah, please.
Your helicochirality is really like at the 50 nanometers scale. How can you translate really this really torsion at such a scale on the molecular basis? Where do you see the origin of your twist at the molecular basis?
Yeah, so this is a great question. So that's what we believe in. This origin happens. This OH in the polymer chain originates the hydrogen bonding. So in each chain, this OH will be in a number of units. That OH binds with another chain. There the hydrogen bonding happens. Because of that, the twisting happens. And this is the particular cartoon that explains.
It's racemic, I suppose.
And this is the prediction of this chain coming together and entangle.
But globally, it's racemic mixture.
That 3D spectrum we have to do, then we can comment on that particularly, definitely. But that is a great question. We will look into that 3D spectrum.
Yeah. Thank you. We have a small presentation from the organizer. Yeah, so we have the next speaker, and Professor S. Velumadi from NIT Trichy, who received PhD from University of Madras in 2001. Now she is a full professor at NIT Trichy, and she received numerous awards from various organizations, including Tamil Nadu Scientist Award and CRSI Bronze Medal for the 2023. and some more awards. So due to time constraint, I'm just cutting her introduction, but I request Professor Velumadi to start her presentation now.
So good evening, Anandam. So first of all, I would like to thank the organizers, Dr. Sureshkumar, for giving me an opportunity here. So today my presentation will be synthetic modification of natural products and the diastereoselective synthesis of spiroxoindoles and their activity studies. At NITT, we do a lot of research on sensors and some amount of organic synthesis and catalysis. About sensors, I have talked in many occasions, so I thought this time I will present the other work on the modification of natural product and their activity studies. So the content of my talk will be this. So as a music director used to say that he is equal to God as he creates lots of tunes with the 7 swaras. We chemists can also be proudly say with the elements in the periodic table, we create more and more of molecules searching for a very good with activity and other things. From morning today also you could have seen the slides are with a lot of molecules synthesized by various research groups in India. So we are molecular designers, so we design and synthesize new molecules and new materials. So when it comes to drug discovery, so there are a lot of stages involved in the drug discovery, starting from idea and then synthesizing the molecule, identifying the lead molecule with the potential activity, and it should come to the market as a drug molecule. It has to cross the various stages, and each stage will take around 2 to 3 years and also involves billions of dollars invested in that system. Okay. So this is the various steps. So from the molecular target selection and screening the n number of compounds to identify a lead and structure activity relationship like that, and until getting the FDA approval. So a lot of steps are involved. So for each step, see for target selection, it takes around 2 years. These are all tentative thing. So for final product, it will take totally around 9 to 16 years and also cost about $1 billion for a successful product. So it's not a easy thing. So as a chemist, if you start with 10,000 compounds, you take a library of molecule, and then after the pharmacology and safety assessment, only 1,000 compounds will pass in that, and only out of that 10 compounds will come for the clinical trials, and after NDA approval and so on, only 1 compound will hit the market as an actual drug. So if you see the drug database, so of the total 1,562 drugs that are available in the market, 420 are synthetic and 101 are vaccines. So most of them are either natural products or derived from the natural products. So this pie chart will clearly show you that B stands for biological. So out of the 1,562, 250 molecules are biological, generally large peptides, and natural products from a botanical drug, naturally derived. So almost everything will be either we are inspired by nature. So plant species provide a potential source for starting material, and some of the microbes and then the marine invertebrates are also be the source for designing lot of drug molecules. Okay. So we know these are all the historically important natural products. Morphine, which is known to be a painkiller, and then quinine derived from the cinchona bark is an anti-malarial, and penicillin from an antibacterial activity. So either they are extracted from the natural products or total synthesis in a lab. And from the earlier days itself, the derivatives of these are in practice. For example, the morphine derivatives like codeine or heroin, they were having a reduced drug dependence, because morphine, you know, if you take it becomes you are addicted to that. So they have a reduced drug dependence than morphine, and this salicylate derivatives, they overcome the stomach burn of the salicylate. So in order to have a better activity or to nullify the disadvantage of the existing drug, the modifications are always in interest. And also the bacteria or the disease causing terms also, they became mutant and they become multi-drug resistant, and they are clear to keep on changing their thing. We know in COVID, phase 1, phase 2, or we had different variants. So the one drug which is active in the first phase become inactive, or the bacteria becomes more active, or it resistance generates. So many things are there. So we need to identify newer molecules to attack the disease. Okay, so these are all the synthetic drugs. So first, the target protein for the disease has to be discovered, and then a high throughput screening of a large library of molecules done to find a lead molecule. Then lead is then modified to different analogs, and it's not a single task. We need the help of computational chemist, we need biologist, we need synthetic organic chemist to synthesize that molecule. So it is like an interdisciplinary field. So we have taken natural products as a lead molecule, and because they have interesting molecular templates, and they have already known to have some better activity. So in order to identify a more active molecule than the parent, it is easy to work. We just modify some of the functional groups which are responsible for the particular activity. We can change and we can find a new molecule. So we, in this objective in mind, we have taken the natural product that we have chosen is piperine. So we know for many years there will be no house without rasam. So we all use pepper as an important condiment in our as a spice in our cooking. So the source for piperine is wall milagu and milagu, this piper longum and piper nigrum. So the India composition is volatiles will be around 2 to 4%, and some of the alkalites, and these are all the things. But the major constituent in the piper will be piperine. So if you see the structure, we think that this is a well-known compound, so a lot of work might have been already done like that. But when we do the actual literature search, not much work has been done on the modifications of the piperine. If you see the structure, there are three groups, three places where you can do the modification. So either you can deprotect this this bond so that you can create a catechol type linkage, or you can saturate the double bonds, or you can do some changes in this position. Okay. Whenever this linkage was cleaved, the molecule loses its activity, and it is not active than the starting material or the parent piperine. So we thought let us not touch this part. And similarly, when the hydrogenation, this unsaturation was reduced, then also the molecule was not having any activity. So these two functional groups are inherent, or it is very much needed for the better activity. So the choice that we are left out with is changing this group. So we changed this cyclic amide into various esters and other amides, and we developed some library of molecules and tried their activity. So from the literature, okay, and why piperine? Here an important point is it is proven to be a bioavailability enhancer. So what is meant by bioavailability enhancer is whenever we take some drugs, for example, if we have some illness, we take some drug, our brain will instruct the thing that some foreign particle is entering the body, try to remove that. So for that, it will generate the CYP450 enzyme will be started doing its function. So it will try to eliminate or discard the drug molecule. It doesn't discriminate whether the drug is purposely given for the goodness of the body. Anything that is coming from the outside, it considers as an enemy, and it tries to move out. But in this piperine, it knocks out the CYP450, it stops the functioning of CYP450, so that the drug molecule that you are taking will be fully available for the body, and it will be useful, the disease will be cured. So that is the main thing that piperine is doing, and it is also having some anti-cancer activity and other works against multi-drug resistance. So different drugs also, the microbes, if they generate the resistant, that will not affected by this. So we started our work with isolating the bioactive molecule from pepper, and then different analogs with aryl and alkyl esters and amides were done. And then we did the molecular docking studies to make the drug, to understand the drug likeliness of this anti-lead molecule, and then the ADMA properties. Then we studied the antibiotic activity of the molecule to find a suitable or a better molecule than the parent piperine. Also, we did the molecular docking studies to find what is the protein which it is binding and what is the reason for the enhanced activity. So we have taken so this work we did in collaboration with an industry where they are working on various isolation of natural products. They do a lot of work on curcumin and others. So we got the unripe black peppercorn from them. And then after all these process, so if you take 3 kilograms of peppercorn, you will end up with 3 grams of piperine. So after purification, the pure piperine crystals were obtained. So we converted the piperine into pipric acid. Then different esters were created, both aliphatic and aromatic esters were done. Either you would take directly acid and then convert, or you can isolate the intermediate thionyl acid chloride also. And these are all the different analogs we have synthesized, and all are obtained in good yield and had been completely characterized. So the antimicrobial studies were done. The bacterial strains were both gram-positive and gram-negative strains were taken, and all the 12 analogs were tested against this. So out of that, so I am not giving the entire details. The consolidated results is the pipric acid and then the 3 esters, one with the fluoride ester showed best activity among all the analogs that we have taken, and P3 works for all the strains, either gram-positive or gram-negative, both are found to be active, and they are better than the parent piperine. That is the main thing. So the analog show better activity, that all used concentration from 10 microgram to 30 microgram. We did all the trials, and all the compounds are having better activity than the piperine. So we did the docking studies and finding the binding energy for the 12 analogs, also which protein it binds, trying to identify the best disease against which it will be active. So this is the pharmacophore of all the analogs, and then all the molecules were following all the 5 rules, that it should have the hydrogen bonding and then molecular weight lesser than 500, like that. For the drug likeliness of any molecule we have to do, and it is not violating any of the rules. So the binding energies, and these are all the proteins for which these analogs have been docked. So the next is the amide. So instead of this cyclic one, we converted into aliphatic as well as aromatic amides were synthesized. So totally 15 amides were synthesized by a single step synthesis, and this is the pipric acid. So they were studied for their antibacterial activity. Here piperine showed no inhibition zones for any of the strain except for the Streptococcus aureus, and whereas the analog PA1 and PA14, the one with the nitro and another with the methyl, were exceptionally well against all the strains, whereas for Acetobacter baumannii, except PA1, all the other analogs work well. So these are the 2 analogs were having better activity than the parent compound piperine. This is the docking studies, and then the 5 Lipinski rules and all other rules were found to be abide by the 14 analogs. So this is the binding energy study calculated for them. So finally, what is the conclusion is the smallest changes in the molecular skeleton could result in the binding methods. So when you change the molecule, the small change could result in completely changes target protein and changing its mechanism of action. So similar to sulfur drugs or any other drug, they were also keep on changing the protein by which it is binding. So as expected, if you simply change one ester group instead of the cyclic amide also, there is a pronounced enhancement in the activity is found. So there is a lot to be done on this, because isolating and then doing you start with 3 kilo and ending up with 3 gram and you have to do all these studies, it takes more time. So currently we are working on some of the spiroxyindole derivatives and their anti-diabetic studies. So normally, you know, the they are an excellent biological active agent because of their numerous cellular receptors, and these are all some of the molecules which are known to be available in the market with the functional group of spiroxyindoles. And diabetes, we know it's increasing now more in the current India. So we have to find a new drug for this anti-diabetic activity. What is this? Okay. So we have taken the multi-component reaction as a strategy for designing or synthesizing these molecules. They have lot of advantages like lesser reaction step, shorter reaction time, and higher actime economy, and 1,3-dipolar cycloaddition using chalcone and then isatine and proline or thioproline or sarcosine as a amine. We have synthesized the spiroxyindoles. So this is the synthetic scheme. So we have taken the benzodiazole anchored chalcone with the different substituents, and we have formed around 24 examples. These are all the list of compounds synthesized, and all the molecules were obtained in a very good yield. Okay. So one of the compound is also single crystal has been done. So this is the mechanistic pathway. So the 1,3-dipolar generated react with chalcone, and you see there are two pathways. The one that is favored is due to this interaction between these oxygen. So this is the most favored one, and this is isomer we got in 100%, I mean full yield. This is not at all formed. So we studied the anti-diabetic activity of this 14 analogs with acarbose as the standard drug, and docking studies were also done. So this is the details used for the docking analysis. So here, out of the 14 drug, this one was having a better activity, more close to acarbose, which is minus 8.6, the binding affinity is. This is almost all the analogs were having a more or less similar one. So they were good anti-diabetic activity, and out of this, the compound 6I showed a very good, excellent activity compared to standard sample. So in this one, the next set, we have changed the chalcone into the amino benzothiazole appended chalcone, and all the other components remain the same. And we have developed, synthesized 18 substrates. All the substrates were got in around 80 to 93%. Yes. So this is the substrate scope, the same mechanism similar to the previous case. And this one was showing even better IC50 value than the standard acarbose. So this could be, if taken for further studies, this could be a very good potential for a good anti-diabetic drug. So this is having 25.25, which is lesser than the 30. So a good IC50 is very much important for preclinical trials and so on. So this is the other data related to the binding affinity and number of intermolecular interactions, total number of hydrogen bonds. Okay. So we synthesized 18 spiroxyindole derivatives, and they were tested against alpha glucosidase and alpha amylase enzyme. So compound, one of the compound exhibit excellent activity, and it can act as a potent diabetic agent. So the last set of molecules that we are doing is vanillin T3rd, and these compounds are found to be good, a very good anti-cancer activity. So this is the substrate scope. This is the mechanism. So the anti-cancer studies have been done against HCT15 cell line and MDA, and this is the cytotoxicity studies. So they are very good activity against at all concentration level. So here, if you see the synthesized compound among all the compounds, the 6F was found to be a potent and stable modulator. So this work is still under process. We have to complete further for communication. So the 6F increases the percentage inhibition of proliferation, and both it is acting as a lung cancer cell line as well as prostate cancer. Okay, so this is another substrate we are currently doing. This is a substrate scope. The activity studies for this is underway. So to summarize, we have taken piperine as a natural product and isolated piperine from the peppercorns, and different modifications of piperine has been attempted. We got 26 modifications, and out of them 4 modifications are having a better activity than the parent piperine, and other 70 spiroxindole derivatives have been designed. They are having a good anti-diabetic as well as anti-cancer agent. And I acknowledge my group members. The work on natural products and its modification is done by Ms. Aarti, and the spiroxindole is done by Ms. Niveda. She has graduated and she is currently writing her thesis. And I thank all the funding agencies for the support. And I thank you all for your kind attention.
Colorful chemistry. And if there is any questions, maybe we'll discuss during the dinner time, or maybe quick questions if anybody is having. Okay, thank you very much, madam. So once again, please join your hands to presentation, wonderful presentation. Yeah, we have the last talk of this session, and the talk is given by Professor Palaniswamy from VIT Vellore, who has completed PhD from IIT Bombay and had a couple of postdocs in Germany, University of Würzburg. Then he joined as a faculty in VIT at 2010, and now he's a full professor over there, and he got a couple of postdoctoral research fellowship awards. So with this short introduction, I request Professor Palaniswamy to deliver his lecture now.
Okay. Thank you, Chair, for your kind introduction. At the outset, I would like to thank the organizer, especially Dr. Siva and Dr. Suresh, for the opportunities and their kind invitation. And also, it is always to visit the alma mater to recall our memories. So once again, in this aspect, I thank the organizers. So now I move to the topic second order nonlinear optics. On ferrocene based linear X and Y shaped chromophores, in general, nonlinear optics means the frequency increases or wavelength decreases. In terms of second order nonlinear optics, exactly the frequency doubles and wavelength reduce the half. So where the process starts, it is based on the electric field strength. If you look at the particular location in the molecule, it will be 10 power 7 to 10 power 10 volt per meter. The conventional light, which is having 10 power 3, which will not disturb anything on the molecule, whereas if you use instead of laser light, okay, the strength is around 10 power 10 volt per meter, which disturb the electric field, which is called nothing else the polarization. So it is the polarization happen by laser, which is called the induced polarization. So it can be expressed in the Taylor series for time factors. Here, if you look at the two terms, one is the chi, which is in the bulk second order nonlinear susceptibility. That means in the bulk material, whereas in the beta is related to the molecular polarizability, hyperpolarizability. So this animation, the second order nonlinear optics, particularly the photon, the two photon combined together gives the frequency doubles. Okay, for this, the important criteria for the second order nonlinear optics, it should be non-centrosymmetric. So further, the things for at the bulk, we need you can create the activities through chiral centers or non-covalent interactions or steric factor. In general, centrosymmetric molecule will have the poles opposite to each other, whereas non-centrosymmetric, all the poles on the same direction. So, but at the molecular level, we need we no need to worry about the chiral other things, but it is here the important thing is donor acceptor strength along with how the length of chain. So it should be a polarizable material. That means the donor acceptor and the charge distribution. So here the importance of nonlinear optics, there are several applications, particularly see in the signal processing, if you, nowadays the virtual reality, if you know about the Apple Vision Pro, recently it was launched, there the nonlinear optical material which plays important role for the signal processing. So the earlier studies on the nonlinear optical studies, particularly on the inorganic semiconductor, but inorganic semiconductor, it is expensive and also absorbs in the strong visible region. So it gives the poor quality. In the latter part, the organic molecules was developed in 80s, but the problem with the organic molecule, the thermal stability. So to overcome these things, to combine the organic and inorganic, when you take the organic part, it is polarization happening, but inorganic things, the metal having various oxidation states, that organic ligand approaches to the metal, the splitting of orbital, which is nothing else the crystal field theory. So the which facilitate the polarization. So the metal having the advantage with the organic ligand. So in this aspect, ferrocene is a perfect molecule which is having nice one electron redox process as well as good transition in the UV visible spectroscopy. So the transition can be explained if you look at the ferrocene molecule, the structure in the textbook chemistry, the 12 electrons from the cyclopentadienyl ring and 6 electrons from the iron atom. The 12 electrons come to the bonding orbital, the 6 electron to the non-bonding orbital. So these 6 electrons, these 12 electrons involves various transition, the metal to pi star within the ferrocene or to the acceptor in the nonlinear optical system. So this makes the fascinating to the nonlinear optics. For example, so based on this, the first report was appeared in 1987 by Malcolm Green from the University of Oxford. They reported a simple ferrocenyl vinylene group where which shows 62 times, particularly the cis isomer shows 62 times higher than the urea, the standard. Okay, this is because of which crystallize in the non-centrosymmetric. That means all the poles are in the same direction. But in that, if you look at the trans isomer, which is the dipole, which opposite to each other, which cancels, there is no activity in the bulk. At the same time, if you look at the molecular level, the trans isomer shows higher than the cis because at the molecular level we need the donor acceptor strength and also pi conjugation. So compared to this is more steric, so which restrict the charge transfer process. So based on this, we have synthesized ferrocenyl pyrosols and characterized structurally, and also we have done the absorption and emission studies which shows all the characteristic and also nice one electron transfer process. Particularly if you look at the crystal structure, here we observe some twist angle. That means the pyrosol ring is not in planar. In general, in this kind of system, the heterocyclic ring actually act as a pi linker between the donor and acceptor, but here it is deviated. Okay, so here instead of it acting as a bi-donor, it acts as an additional donor. Okay, so you can see the resonance structure of this molecule after the charge transfer process. This reflects in the nonlinear in the molecular hyperpolar stability because compared to the organic system, which is here shows higher value because of the pyrosol ring act as an additional donor instead of this. Instead of the bi-linker, which makes more high values. So with this, we'll so after that we have reported a few systems, and also recent. This is our recent report. We reported in the chiral molecule also. This shows very nice, very interesting results. And also with this, if you have additional donor from our the past experience, if you introduce, you can have more charge transfer process which will enhance the activities. So based on this, we have synthesized Y-shaped heterocyclic chromophores, quinoxylene, ferrocene based on the imidazole things and structurally characterized, and also done all the basic characterization. The important thing is the activity. If you look at the things, it is higher than the linear system because of the more charge transfer between the donor and the acceptor molecule, and also particularly the trifluoromethyl shows higher value than the other things because our theoretical studies shows the n-pi star transitions are effective than the other systems. And also these molecules we introduced into the polymeric film like PMMA or polystyrene chromophores, which shows particularly the quinoxylene derivative in PMMA, which shows higher value around 5.27 picometer per volt. This is the highest value reported in the nonlinear in particularly organometallic system. Sorry. And also interestingly, after 4 months, the degradation also considerably less. And then further, we worked on the X-shaped systems. Okay, so we synthesized the X-shaped system based on the methoxyphenyl and ferrocenyl. Why we made it? Because of the oxidation potential of these two molecules. These two moieties are comparable. So we have synthesized and also the solidochromic studies, that means the charge transfer process, we observed the better charge transfer process in the ferrocenyl derivative because of the one electron transfer, and also the cyclic voltagram ferrocenyl derivative shows the redox things, but here the anisole derivative shows only the oxidation, and also these things reflect in the nonlinear activities in the bulk as well as at the molecular level. The ferrocene derivative shows higher than the anisole because of the one electron effective charge transfer. With this, I conclude my talk. The lack of planarity, that means which enhance the nonlinear activities in molecular level in the linear system. Y-shaped molecule shows higher than the linear system, and also X-shaped molecule also we reported. Okay, so and I acknowledge the fundings and all former students and also V8 infrastructure and our collaborators at the finally, thank you for your kind attention. And also, I thank the audience. This odd hour, lot of members are present. I thank you once again for your kind support. Thank you.
Yeah, thank you, Professor Palaniswamy. It's a nice talk. We can have one questions quickly. Anybody is having questions? Yeah.
Professor Anandasan. Yes. Okay.
State you may need non-crystalline state, but when it goes to amorphous state, sometimes we see SSG, like second harmonic
Yes, sir.
integration,
That
right?
is
Non-linear properties.
yeah. That is called the residual SH in general. Depends upon the various factors. Suppose the molecules are bulk. In general, it is the SHG is based on the alignment. Okay. But if you have the bulky things, non-covalent interaction in the solid state, which will disturb the non-parallel alignment, which create the residual SHG, so it will show some values.
Residual, because the intensity was compared to the crystalline one, it's
Okay.
like much higher. In the crystal, actually, we don't see much signal actually.
Okay.
It's non-centrosymmetric arrangement is there. But when we go for self-assembly based arrangement, we had a better enhancement actually, SIC signals.
In amorphous, you mean?
Yes.
Okay, maybe it may be the due to the because if it is SHG means it will disturb the centrosymmetric. There are various factors.
In sometimes like we have a centrosymmetric molecules, but we cannot expect that it should be like a nonlinear material.
Yeah, there are some cases the centrosymmetric molecules also reported, but on that you have to break the symmetry for some way. Then only it will show the activity. Otherwise, it is not possible. Even your Professor Chandrasekhar also reported.
Yes, that's what.
Yeah.
Yeah, thank you. I thank all the audience for patience, and also I thank Professor Palaniswamy for his wonderful talk. So with this, we have a small gift from the organizer for you.
Okay.
A kind note, I request the presenters to display your posters in the allotted place before you leave. If you haven't, kindly do it, and the evaluation will be done in the upcoming days. We all outstretch our gratitude to all the nobilities of the day for a great brightness of their intelligence. Many thanks to everyone. See you all tomorrow. Thank you.
I thank Professor Jayakumar for this wonderful chairing the session. Thank you very much. Students, those who are, accommodation, no, the vehicle is waiting outside. You can get down, okay? So tomorrow we'll meet at 9 o'clock sharply.